Good morning. I am Balaram, Dean Faculty Affairs of JNCASR. Welcome to one and all who have joined this annual faculty meeting. It's my great pleasure to specially welcome Professor Giridhar Udupi Rao Kulkarni, who took over as President of JNCASR in January 2020. This is the first annual faculty meeting which is going to be chaired by Professor Kulkarni. Professor Kulkarni, special welcome, and we look forward to your leadership in taking the center to greater heights of glory. I would also like to take this opportunity to place on record our appreciation to former President Professor V. Nagaraja and in-charge President Professor K.S. Narayan. I now invite Professor Kulkarni to start the annual faculty meeting and brief us on the activities of the center.
Good morning and thank you, Professor Hema. I welcome you all to the annual faculty meeting and the in-house symposium 2020. I welcome all my faculty colleagues at the center, as well as colleagues and dignitaries associated with the center from the past who are also present online. I welcome all the students on campus to these events, including the newly admitted students. Most of them are participating online from their homes. Welcome also to R&D personnel, research associates, technical persons, academic and administrative staff. Today and tomorrow are festive days for JNC, where all come together to celebrate science on campus. This year is special in some sense. JNCASR just completed 30 years, and this is the time to reflect on our achievements and targets equally. As you may have noticed from the program, we will have a couple of technical talks in the forenoon session of the annual faculty meeting, which we have some way we have clubbed it with in-house symposium. We have deviated from the regular format. The IHS starts afternoon and continues till tomorrow evening. This is interlaced with the degree award ceremony, which is going to take place this evening. And poster presentations have been taking place online for the last 2 days. They are still online. We will have a session on posters tomorrow as well, along with the poster award event. I hope you will all enjoy all these events. A warm welcome to you all again. On this occasion, it's my pleasure to read out a few greeting messages received from our mentors. Bharat Ratna Professor C.N.R. Rao sent a message. He is not online at present, but he will be joining us soon. It is great that annual faculty meeting is being held today. Immaterial of COVID and other problems of today, we decided to have the faculty meeting. It is customary to have certificates issued, and more importantly, the center as a whole is contributing a generation of students and teachers to the nation. It is the day the outcome of all results is being made public. While I continue to congratulate the successful candidates, I am equally concerned about the have-nots. I think he means in the country. Thousands of people in India would have enjoyed the fruits of education, and the country would be brimming and shining with education. I also congratulate the postgraduate diploma holders, the latecomers to this shining pedestal of knowledge. Professor Rao. We have the best wishes for both the events from Professor P. Ram Rao, former chairman of the Council of Management of JNCASR. We also have wishes from Professor Govardhan Mehta, the present chairman of the Council of Management. Congratulations to JNCASR on successful completion of 30 years. I am happy to note its academic developments and progress on many fronts of scientific research. My best wishes to all members of JNCASR community on this occasion. I wish you all a safe and healthy life. That was Professor Mehta. We received a greeting message from Professor Ashutosh Sharma, Secretary to Government of India, Department of Science and Technology. It's a great pleasure to note that there is a spectacular growth of JNCASR since last 30 years. It stands with its head high as a center of excellence among all DST autonomous institutes and as a part of its family. I always enjoy the annual day program, particularly the poster sessions of students, which is a living testimony to the thriving research environment of the center. JNCASR is now globally renowned for its stellar scientific contributions. I also note that the teaching program of the center are of a very high order, not only at national level, but also at international level. While extending my warm greetings to JNCASR fraternity, I'll be delighted to participate in the forthcoming annual faculty meeting. I wish a great success to JNCASR in its future endeavor. Taking advantage of the online format of the meetings, we invited all past honorary professors, adjunct faculty members, and mentors who have been with us from the very early years and have contributed immensely to the growth of the center. And many of them are online participating in the program. I'll just run through the list if you don't mind. Many of them, I think a number like around 80 or so were invited, and almost all of them have responded, and many of them have been online, and many also have sent greeting messages to the center. These are the people who were invited, who have been invited to this event. The list goes on. We couldn't read the names here, right? So actually we have the greeting messages as well as the details displayed on all screens across the campus today and tomorrow. And we also have the messages posted on the website which we created for this purpose, for this AFM IHS website. The links have been sent out to all. Kindly visit and look at the greeting messages received from all these eminent people associated with the center. I'll now move on with a report on the center. First, let's look at the institutional ranking of JNCASR 2020. Nature Index annual tables listed JNC as 4th in India under life sciences, 10th under chemistry and physical sciences categories, and across the world gave us 469th rank and 11th among Indian institutes. Skymago institutions ranking with the first in India under higher education sector and 3rd across all sectors in India. I'll now go through the recognitions, accomplishments of our faculty members and students. Professor C.N.R. Rao. Very recently, Stanford University put out a list listing out top 2%, top I think 0.5% of people who are most cited in the scientific literature. Professor Rao ranks number 3 in the area of nanoscience, nanotechnology globally. Web of Science also has listed him as highly cited researcher. He is also recipient of the TV9 Lifetime Achievement Award. We'll have an occasion to applause in the end. Okay. Professor Radha Narasimha, he received the Lifetime Achievement Award in the year 2019 in Nature Award for Mentoring in Science. And he is also National Science Chair under Mode 2, and this award he received this April. Professor Subi George and Professor Rajesh Ganapathy both have been recipients of the CSIR Shanti Swarup Bhatnagar prizes. Professor George in Chemical Sciences and Professor Rajesh Ganapathy in Physical Sciences for this year 2020. Professor Subi is also Associate Editor of the Chemical Science from RSC. Professor Tapas K. Kundu, recipient of Sri Om Prakash Basin Award 2019 in the field of Health and Medical Sciences. Professor Radha Narasimha got elected as an international honorary member to the American Academy of Arts and Sciences. She is also the recipient of the Anna Boyksken Fellowship of the Technical University of Munich, Germany. Professor Manisha S. Inamdar was elected as a member of Gene Therapy Advisory and Evaluation Committee of ICMR, member of Education, Engagement and Empowerment 3E Working Group to the WHO Expert Advisory Committee to develop global standards for governance and oversight of human genome editing, member of the Statement Working Group on Regenerative Medicine of the Inter-Academy Partnership nominated by INSA. She is also nominee of DST Secretary for the National Apex Committee on Stem Cell Research and Therapy. Professor T.N.C. Vidya is a member of the editorial board of the journal Frontiers in Conservation Science. Professor Santosh Anshomali received the Craze Dr. APJ Abdul Kalam HPC Award 2020, instituted by the Hewlett-Packard Enterprise under High Performance Computing category Researcher and R&D in HPC applications in India. Professor Sebastian C. Peter, recipient of CRSI Bronze Medal from the CRSI. And Professor Jayant Haldar received his project sanction from the IUSSTF, and this is the Indo-US Virtual Network for COVID-19. Dr. Sarit Agasti is Young Associate of the Indian Academy of Sciences, Bangalore for the year. And Professor Amitabh Joshi got reappointed as the Adjunct Faculty of ISER Mohali, and also he is recently recipient of the Silver Jubilee Professorship donated by C.N.R. Rao Education Foundation. Professor A. Sundaresan is a fellow of the Indian Academy of Sciences, Bangalore, and also he is recipient of the C.N.R. Rao National Prize in Chemical Sciences from CRSI. He has also been selected to receive the Professor C.N.R. Rao Oration Award Lecture 2020. Professor Anuranjan Anand and Professor Kaustubh Sanyal are recipients of the DST ACRB J.C. Bose Fellowship 2020. Professor Umesh Wagmare is a member of the Editorial Advisory Board of ACS Central Science. He also got elected as a Fellow of Indian National Academy of Engineering, National Academy of Engineering India, Maharashtra Academy of Sciences. Professor T. Govindaraju, the recipient of the National Prize for Research on Chemistry of Peptides and Nucleic Acids, donated by C.N.R. Rao Education Foundation. Professor Chandrabas Narayana, recipient of Platinum Jubilee Lecture Award of Indian Science Congress 2020, is also a member of the Editorial Advisory Board of Journal of Applied Physics. Dr. Biva Saha, Young Associate of the Indian Academy of Sciences 2020, and also Young Scientist Research, recipient of the Young Scientist Research Award from DRNS of the Atomic Energy. Professor Ravi Manditaya is the joint recipient of the CDRI Awards 2020 for excellence in drug research in life sciences category, and also he is recognized as an exceptional scientist on the prestigious Journal of Molecular Biology. Professor Kanishka Biswas is recipient of the ICSE Material Science Annual Prize from MRSI, Swarna Jayanti Fellowship by DST, Editorial Advisory Board member of Journal of Materials Chemistry A from RSC, Editorial Board member Journal of Solid State Chemistry from Elsevier, and also from iScience Cell Press. He's been elected as a Fellow of Royal Society of Chemistry in Leaders in the Field category for his outstanding contribution in solid state chemistry, thermoelectrics, and 2D materials. Professor Tapas K. Maji, the team under the mentorship of Professor Maji for their invention of zinc air batteries won the Silver Award in KPIT Sparkle 2020 iInnovative contest. He is also the Associate Editor of the journal ACSAMR. Professor Ranjini Vishwanatha got featured as a woman in the forefront of energy research in ACS Energy Letters. Dr. Kushagra Bansal received the Wellcome Trust Department of Biotechnology, India Alliance Intermediate Fellowship under Biomedical Research category. Myself is the recipient of Professor C.N.R. Rao National Prize for Chemical Research 2020 and also Dr. Rajaramana State Award of the Karnataka State Council for Science and Technology. And I'll just go through the student awards and medals for the 2020, which came out very recently. Professor C.N. Rao Medal for the Best Thesis in Physical Sciences category goes to Dr. Manisha Samant of NCU. Professor C.N. Rao Medal for the Best Thesis in Biological Sciences category, Dr. Krishnendu Guven. Professor Radha Narasimha and Family Award for the Best Thesis in Engineering Sciences category goes to Dr. Muhammad Atif of EMU. Professor Radha Narasimha and Family Award for the Best Thesis in Engineering Sciences category of the MS Engineering category goes to Mr. Prashant Ramesh. Srimati and Sri Bapu Narayan Swamy Prize to Mr. Ritendra Singh of NCU of the INT PhD program. Bapu Matru Prasad Scholarship to Mr. Animesh Das, NCU of INT PhD. Dr. Indumati Rao Prize to Mr. Acharya Yash Sanjay of NCU in the stream MSc Chemistry. The selection criteria are listed out there, as well as the details of the awards and prizes. And these students will be receiving the awards, I think, this evening in the degree award ceremony. Right? Yeah. So I think this is the time to give a big round of applause to for our faculty colleagues and students who received the awards. What you got to hear the applause on the internet was all from our participants. Let's move on. Appointments. Myself as president of the center, and Dr. Banikant Sarma got appointed as faculty fellow. Dr. Bani must be there online somewhere. And Deans, Professor N.S. Vidhyadhiraja as Dean of Fellowship and Extension, Professor Chandrabas Narayan, Dean of Research and Development. Of course, he is on deputation now. And a few chairpersons for different units, Professor Manisha S. Inamdar for MBGU, Professor A. Sundareshan for CPMU, Professor Subi J. George for NCU, and Professor T. Govindaraju for ETU. Professor Hemalatha Balaram has been nominated as the Honorary Resident Professor. Promotions, Professor Subi George became full professor, as well as we have Professor Govindaraju and Professor Kavita Jain, they became full professors. Dr. James Chalaya became associate professor, and Mrs. Chitra in administration got promoted to assistant administrative officer of SG grade. Professor Chandrabas Narayan has gone on deputation to RGCB of Trivandrum as director, and Dr. C.P. Rajendran left us to join NIAS of Bangalore. And there are several individuals who have taken additional responsibilities. Professor M. Ishwarmurthy is the associate director of ICMS, Professor Jayant Haldar and Professor Shiba as warden and associate wardens respectively, Professor Ranjini Vishwanatha as the chairperson for Daycare Center, and Mrs. Nabonita Guha as media coordinator, Dr. R.G. Prakash as liaison officer of OBC, Mr. P. Venkatesalu, liaison officer SCST, Dr. Paneerselvam, coordinator of R&D as well, in addition to his other responsibilities, Mr. Srinath V as the coordinator for health, safety and conservation. There have been contractual appointments including a visiting professor, Professor Jayant H. Arkeri to EMU. We have with us Mr. Narayan, Mr. Vinayak Pattar, Mr. John Thomas and Mr. Godson. Several committees got reconstituted. This is the IPMC committee chaired by Professor Radha Narasimha. And we have nominated external members to help us with the IPMC committee. The Building and Works Committee also got reconstituted. And now there are some academic matters which have been passed on to me from the academic office. There are several numbers here. These are the admission details for the August session. We have also taken up admission for the mid-year term as well. So you see number of students listed out under against different units, again different programs. We just note that 55 students finally got admitted, out of which 34 are boys and 21 are girls. And summary of students on roll, again there are several numbers listed out, again different units and different programs. In all we have 335 students with us, and next table tells us about the degrees being awarded this evening, which was approved by the Council of Management held in September. So in all, we have 58 degrees being awarded through different streams, 21 PhD and 13 through in PhD, 1 of MS PhD, 6 of MS Engineering, MS through in PhD 12, MSc Chemistry. This is a new program from NCU. We have 5 students. I'll just briefly go through the R&D activities of the center, which were passed on from the R&D office. Several patents have been filed, Indian patents, international PCT applications, national phase patents. The numbers are listed out there. And several other patents got granted, which were filed years ago. Indian Patent Office granted 7 patents, US Patent Office 5, European 3, Brazilian 1. In addition, there is a table on Memorandum of Understanding signed with various agencies. These include other DST organizations, Center for Nano and Soft Matter Sciences, in respect of a piece of land at Nelamangala campus, which should belong to JNC, and a new structure is coming up there. And we also have several other agencies, including AstraZeneca Hospital and ISRO, CDAC, DBT itself, Indo-Swiss agency. The list goes on, including some private industries. So our faculty colleagues have signed up agreements and have been carrying out joint works under these agreements. There are also non-disclosure agreement and other type of agreements, even sharing of patent costs, that kind of agreements with various agencies nationally and also internationally. And the details are given in these tables. The list, I think, concludes here with the most recent one by me with Sastry. Outreach activities. JNC is very proud with its outreach activities, both through Educational Technology Unit and also through the Fellowship and Extension Office. ETU conducted several programs. I'm telling you a time period before COVID broke, and so even then you can see the numbers are large. They held around 11 programs, and number of students participated 2,882, and number of teachers who also participated in the same programs are 273. These numbers could have been bigger, but for the pandemic issue. And through the F&D section, many programs have been coordinated, including institutional visits. Again, there are large numbers there. Student buddy programs, 86 students and 7 teachers visited the center, and we observed the National Science Day and also International Women's Day. I must tell you that this kind of programs require intense activity, where these young students and all, they visit the campus. We had to suspend abruptly because of the pandemic, and this year we are not having any of the programs except for a few online sessions we have held, and we will be holding few more, right? I must take a minute to tell you about the COVID-19 preparedness. As any other institute, JNC also underwent a lot of issues related to the pandemic, and we had to lock down the campus, restrict the entry, and we had to send out our students to their homes and continue interactions online, teaching also online. And gradually, as the government norms relaxed, we considered getting back the students with intense participation from Dean Academic and Administration and all. And then we worked out the guidelines, SOPs, how to be on campus, what kind of medical tests they have to go through. We had a big team, including the nodal officers. And in fact, 9 committees got formed for this purpose. I must mention proudly that the entire center participated in this with all faculty members, and they intensely worked behind what to do, because it's a very unusual situation, and I wanted to keep everyone in the loop. And I must say that all of them contributed, and the SOPs were worked out and guidelines were worked out, and even today we are observing seriously all these practices, new norms on the campus. And we also brought out quarantine facilities, because as we get the students and young researchers and even visiting faculty from outside, our own faculty coming back, we had to quarantine them. So we created facilities. To begin with, we had our own hostel. Student residence itself became a quarantine place. Then we have had these institutional quarantine transit facilities and whatnot. Several other things got created. And if anyone who has not visited the campus for several months now visits now, you get to see a lot of posters and signages and all the SOPs across the campus, including number of people allowed to sit in this hall. You can see very few are sitting in this. This total capacity is 150 or so, but we hardly have less than somewhere around 50 or so. So that is the kind of life we are living, and so most of the interactions have turned out to be online, but I think we are doing well in terms of getting back our young researchers and conducting all the programs, including the courses. Our newly admitted students are all attending courses online. And on this occasion, we normally bring out JNC second edition of the newsletter for the year, and this year we decided not to print. And so you just see the first page which is being displayed, and this issue will be available through email. It will be sent out on circulation, and also it is posted on the same site, AFM IHS site, and also on the JNC site for ready reference. And most of the things what I narrated now, these are all briefed in the newsletter. And I'll take only last 2 minutes to actually take this opportunity to thank, by and large, and particularly in organizing this event, thanks to the speakers for the annual faculty meeting. We have 2 outside speakers, so thanks to them. And then we have deans and their offices who have helped us greatly with all the activities, including feeding material to this presentation. Professor Hema Balaram, Dean Faculty Affairs, Professor Umesh Vagmare, Dean Academic Affairs, Professor N.S. Vidhyadhiraja, Dean Fellowship and Extension, Professor Chandravas Narayan, former Dean R&D. We are yet to appoint Dean R&D through a formal process which is awaited. I must thank my colleague Professor Anuranjan Anand, Chair of Neurosciences Unit. Neurosciences Unit, though it is small, they undertook to convene this particular event, particularly the in-house symposium. A great deal. In fact, all the things have changed now. It's all maximally online format. So they had to work really hard along with a team of volunteers. So I really sincerely thank them. And Professor Subir Das, head of CompLab, and his team. I must mention that the Internet Lifeline, they have kept it live, and this is the lifeline of JNC today. A very important component, thanks to them. And as it is raining through today and probably even intensely tomorrow, there's a weather prediction. I hope that the internet connectivity will survive. They are working hard behind. And thanks also to Mr. Jaideep Deb, Administrative Officer, and for his team for all the efforts, including hall management team under administration. My sincere thanks to Department of Science and Technology for all the support they have been offering through the years, and also under the difficult times. Even this year also we have received decent funds. Thank you all, and let's continue with the program. Thank you very much.
Thank you, Professor Kulkarni, for the lucid report on the activities and progress of JNCASR, and also for informing us on all the efforts made by the center to resume functioning during these difficult times of the COVID pandemic. The annual faculty meeting concludes now, and I thank all the honorary faculty, the faculty of the center, and other invitees for joining the meeting. Thank you very much. And it's my great pleasure to introduce the first speaker of the in-house symposium, Professor Premkumar Sanyal. Professor Sanyal was Director, Saha Institute of Nuclear Physics, and currently Emeritus Professor in the same institution. He is also Emeritus Professor in S.N. Bose National Center for Biological Sciences, Calcutta, and Adjunct Professor at ICMS at JNCASR. Professor Sanyal has received several awards and fellowships, such as the J.C. Bose National Fellowship, Radha Narasimha Fellowship of DAE, to name a few. He is also Fellow of all 3 Academies of Sciences in India. He is a Fellow of the Third World Academy of Sciences too. Professor Sanyal has research interest in synchrotron X-ray and neutron scattering studies of surface and interfaces. He has made substantial contributions to develop understanding of growth mechanism and structure property relationship in low-dimensional materials like quantum dots, nanowires, and ultra-thin films deposited on solid and liquid surfaces. Professor Sanyal will be talking to us on winding of spin stripes to skyrmions and dipolar magnetic thin film.
Thank you, Madam, for this nice introduction. And of course, I would like to start this talk thanking Professor G.U. Kulkarni and his team for giving me this chance to listen to this enormous achievement of JNCASR. As always, is very proud. I'm proud to be associated with this institute. I thought today I'll talk about something on quantum materials, and it's a very interesting topic which is really taking a good shape in recent years. And my topic here will be winding of spin tribes to Skyrmions in dipolar magnetic chain film. Why I have chosen this topic will become clear by the end of this presentation. Okay, so now the plan of the talk is the following. It is actually thesis work of three of my students for quantum dots, in these quantum materials. Manjula Sharma and Orko Vikas they worked on quantum dots on silicon germanium and aluminium gallium arsenic quantum dots. And Arnav Singh, he worked on this magnetic ordering, which I'll be mostly talking about. So introduction I'll give with a couple of slides saying why this is fascinating to use synchrotron scattering techniques in understanding quantum materials. And then I'll make brief, one slide presentation on semiconductor quantum dots on which we work, but primarily concentrating on the magnetic, topological magnetic phases on which I'll be making the presentation today. So the Skyrmions and stripe phase will be the primary issue in my talk today in iron gadolinium amorphous multilayers. And then I'll finish with concluding comments, and I can assure the chairperson that I'll be on time. Okay. This is fascinating subject which is unfolding over a few years now. This is the field of quantum materials. Nowadays, throughout the world, everybody is talking about applicable material, and quantum material is one such thing because it gives properties on demand. That means you can tune the property of a material using quantum mechanics. So quantum materials are defined in a simple way, where quantum mechanics plays a very pivoting role. And there are three very interesting mathematical concepts which comes very handy to understand this property-structure relationship. And these are symmetry, of course, then topology, and also dimensionality. And what people do is now to manipulate these properties by external stimuli, which gives the practical control to get various applicability of this quantum material, like photonic, electronic, and energy devices. So it is a very fascinating field, both from basic studies and applicability. Is it okay? Am I audible? There is some echo. Okay. So, evolving synchrotron techniques, I'll be basically concentrating on today, is actually comes from new four properties of synchrotron which are really improving over the last 10 years or so. This is how to make the beam nano-sized so that you can see the material in great detail. And then you can do the energy tunability and polarization tunability so that you can do magnetic scattering, because most of us are familiar with scattering of X-ray from electrons. But X-ray scattering is also sensitive to the spin or the magnetic aspect of the scattering process. And that happens, or that becomes very prominent when you tune the X-ray beam to the to the energy age of a particular X-ray fluorescence energy age, which is sensitive to the magnetic scattering, and the other phenomena which is becoming very interesting and important is the coherence of the beam, of the X-ray beam, and associated correlation technique, which I will be talking about. So as I have already told, in our group we are working on quantum dots and Skyrmion, but today I am going to talk mostly on Skyrmion, but let me give one slide on quantum dots on which we work. So, quantum dots is very... Yes?
Can you press on that hide?
Okay. Yeah, so that's coming in the way, I can see. Yeah, fine.
Yeah, thank you.
Thanks. In quantum dots, actually, you have a atomic-like energy levels, and you can tune these energy levels by tuning the composition of the quantum dots, which separates out these electron and hole levels, but keeping the individual distances unchanged. Or you can tune this photoluminescence spectra by changing the size of the quantum dots. When you change the size of the quantum dot, then the distances between the higher energy levels actually changes, keeping the initial gap unchanged. So by these two, you can tune a quantum dot to get a particular luminescence line, and that is why it is property on demand. But it's still to understand why whether the composition and the size can be tuned continuously, because these properties come from not from one dot but from multiple of them, and there is always an uncertainty about whether it is spread because of the the difference in the luminescence energy for multiple dots, or it is due to the compositional variation within one dot. So this is the subject on which we work, and we work with grazing incidence X-ray diffraction technique, because as you can see, this is only one monolayer of quantum dots on a substrate, and as a result, the conventional diffraction doesn't work, because conventional diffraction, the incident angle becomes very large, and as a result, you get only scattering from the substrate, not from the top layer, which is having the quantum dot. So you have to restrict the penetration of X-ray inside the bulk by having a very small incidence angle of the X-ray, and instead of doing the conventional scattering, you have to do in-plane scattering. So instead of having 001, 002, 003 kind of diffraction peak, you will have 100, 200, 400 kind of diffraction peaks, and you have to scan your detector in plane to get such diffraction things. And this is what we do, and we have several publications. I have only given the last two. Here, the first one is done in POH at Petra 3 with Orco, and this is actually correlating the photoluminescence and structural property of uncapped gallium arsenide and capped epitaxial indium gallium arsenide quantum dots. So this is very interesting. We have done micro luminescence study and also the X-ray diffraction study to see how much it is varying between the dots and within a dot, and what is the composition and stuff like that. But as I said, you cannot do this thing by conventional diffraction as the penetration of X-ray goes in the substrate. But recently we have done a work where although the penetration of X-ray is more, but if you concentrate on the a particular element which is absent in substrate, let us say in this case it is indium, the substrate is gallium arsenic, and if you look for the X-ray fluorescence of this particular species, indium, then you can basically follow that. For example, here I have shown a typical 111 diffraction peak, which is of course having mostly from the substrate, but you can see the fluorescence of indium, how it is picking up across this particular diffraction peak. Indium, as it is only on the substrate, so it becomes extremely sensitive to the to the composition of quantum dot. And this is a very new technique we have done for the first time, and by doing a systematic study in different crystallographic direction, we can actually figure out the indium atom, how it is how it is shifted from the expected position, and how much it is shifted, and how it is related to the growth condition and the cap layer condition and stuff like that. So this is a detailed study which we have done in collaboration with Mike Bedzik of Northwestern University, and this paper has just come in his material, and we have given a new name of this technique. This is X-ray atomic mapping of quantum dots, and this is really beautiful. But so far, what we have not done is same study, similar study, using single quantum dot. Remember that when we are putting such gazing incidence diffraction or this X-ray standing wave technique, we are actually eliminating multiple quantum dots and seeing the average picture, which is giving rise to this photoluminescence. In future, what we like to do is cut out one or few, the quantum dots by using ion beam techniques and stuff like that, instead of coming very close to the quantum dot, which alters the interfacial structure, and that is why it is not successful or cannot be done with electron diffraction technique. But we can do it. We can take a cutout which is farther away from the interfacial area and do X-ray scattering from single dot. Just to prove this technique is working, I have recently worked with Professor Kulkarni on his beautiful gold nanocrystal, which is also catalytic. And in PO6 in Petra, what we have done together is scan this gold crystal with a 50 nanometer by 50 nanometer beam. As the synchrotron improves, this 50 nanometer will go down to 10 nanometer very soon. And this is this kind of diffraction microscopy which we can do in X-ray, and this will be ideal to study our quantum dots in future. So what we have done today, I'm not going to talk about this, but it's fascinating work which we did, scan the entire thing with such beam, and then you will realize how these different phases, cubic and non-cubic phase of gold, is distributed over a grain. It's a single grain which is studied in this way. So in future, we want to extend our quantum dot study in same particular this kind of matter. And after doing the entire scan, we will get all the diffraction spot and also X-ray standing wave measurements. And this is our future plan. Anyway, now let me go to the actual topic of my presentation today. And as we all know that recently there is a fantastic interest in two-dimensional magnetism, and it's a topological magnetism, and although we say it is two-dimensional, but one should be very careful that the spin direction in this kind of Skyrmion, boron and anti-boron systems are also in the Z direction. So the spins not only is in plane in a particular way, but it is also looking up or looking down depending on which structure you are talking about. Topologically, you can map it on a sphere, and if the sphere is completely covered, then we get into the skyrmion. All the spin direction are restored back in the real space. And in fact, if you are half filled in this, you get a moron structure, and if the upper half is filled, you get the anti-moron structure. And people have now also figured out that depending upon whether it is skyrmion, moron, or anti-moron, their interaction decides whether you will get a 4-fold symmetry or a 6-fold symmetry. For skyrmion, it is always 6-fold symmetry. I must mention here that the spin direction is also in Z direction, so it is not really ideal vortex structure. It's a two-dimensional magnetism, but the spin direction involves all three X, Y, Z. In vortex, you have a different arrangement. You don't, unless you go at the center, the spin is not really looking up. It is all in plane, and there is a series of theoretical work starting from 60s, where people have shown that this, the vortex, anti-vortex can be collapsed, and there have been defined of decay temperature. We work on this using Langmuir project film, and but today I'm not going to talk about this. So let me concentrate on this skyrmion structure and associated spin arrangement. We were interested about the magnetic scattering from this skyrmion gadolinium iron multilayer, and the technique we are using, which was developed in Brookhaven long back, in 90s or late 80s. As I said in the beginning, that you have to tune the energy of the X-ray to a particular absorption age of a material for which you are trying to extract the spin arrangement, so either gadolinium or iron, and then you can get the information. For example, this beautiful resonant X-ray scattering immediately tells you that the spins are organized in a 6-fold symmetry, and this gives you the organization of the skyrmion. So for the work which I am going to present now, we have used 80 layers, and this was developed in a beautiful growth facility of Eric Floreton in San Diego, and this is grown on silicon membrane, silicon nitride membrane, and we have only 4 angstrom or 3.4 angstrom individual layers, 80 such layers, and of course they all get mixed up. So compositionally it is almost amorphous, but the spin arrangement is beautiful. So the magnetoforce microscopy, Lorentz TEM, and the resonant X-ray scattering all was done before even I got involved in this project, and this is published in APL 2016. So with Arnav, our interest was to use the coherence property of X-ray beam, and this structure comes from a stripe structure, which is a one-dimensional structure. I will talk about it in next few slides. So essentially, stripe structure gets winded into the skyrmion structure, and the X-ray magnetic scattering peak from 2-fold symmetry becomes 6-fold symmetry as this transition happens. And our interest is to study this transition and how it happens and why it happens. This is applicable material because this transition occurs around room temperature, unlike the DMI material on which people have studied skyrmion from the beginning, and that is happening at much lower temperature, so it's not applicable in that sense. However, I'll come back to that a little later. So our first study was published here in Nature Communication, and what we have done is we have used the coherence property of X-ray beam at advanced light source in Berkeley. Here what you do is basically take the picture of the diffraction spot, all 6-fold or 2-fold spot, and analyze the intensity at a particular pixel of this detector. And just do this correlation spectroscopy kind of work. In correlation spectroscopy, people do such work as a function of time, but here what we do is scan very slowly the magnetic field and then do such correlation calculation between the adjacent frames. For example, as you scan the beam very slowly in magnetic field, the intensity pattern changes from this to that, and as the change is not much, as you can see, the calculated correlation remains very close to 1. Well, if there is a substantial change, not substantial, little bit more change, then what will happen? The correlation drops. And if there is a dramatic change in the 2 successive spots, then there is a big drop in the correlation. So this is how you collect the data. After collecting all this frame, you calculate this correlation and plot it out. And what we found is this kind of big jumps signifies the domain movement of the magnetic phase and how it moves and things like that. And we noticed that if the magnetic field is above 200, where the Skyrmion phase sets in, this thing doesn't appear at all, this kind of spikes. Well, let me give you more detail. That was our first data which we collected. So to make it more systematic, what we did is we also collected near the beam a typical scattering spectrum which is not magnetic. It's a arrays fringes. It is independent of the magnetic field. So this gives us a hold on our calculation, whether correlation calculation is correct or not, and then compare that with the stripe phase where you have 2-fold symmetry, or the Skyrmion phase which is 6-fold symmetry, and then go on doing these measurements in great detail, and this is what we published as I showed before. And as you can see here, this black line here is basically the array fringes, which is remaining almost close to 1, no change, and here it is exactly 1. And then you have such big jumps when you are in the stripe phase, and as soon as you go into Skyrmion phase, these jumps vanishes. This is the first time we have shown that topological protection of this Skyrmion 2D structure actually arrests the domain movement. But note here that the correlation is not 1 here, it is slightly less than 1. So although there is no big jump in the magnetic domain, there is a continuous movement of the domain in a very slow way as a function of magnetic field. I'll come back to this in the towards the end of my talk. Okay, then of course you can do all this in great detail. I will not spend much time, and this is all published. I will spend more time on our unpublished data. This work we could map to this beautiful concept of Professor Sedna in crackling noise, which is a review in Nature paper by him. And here basically 2 statistical parameters which are important, that this has a kind of decay, a exponent, and also has a mean beyond which the avalanche size drops out. And this concept we use to calculate our data and the scaling collapse of the predicted by Sedna et al. And we could show that the scaling collapse indeed works for the stripe phase, and all the data could be collapsed in a single curve, both below the Skyrmion phase and above the Skyrmion phase. playing with the temperature and the field, and also it works for Skyrmion phase, and this is what we got. Of course, these two are two different universality class, and this is what we said in our paper in Nature Communication. Now the question is, the statistical picture is beautiful, but we wanted to study in more detail how this transition occurs from stripe to the Skyrmion phase. And as I said, this is initially it was studied in a DMI films, and in DMI films it is known that it is before you apply the magnetic field, it is helical state, and as you apply small magnetic field, it becomes chiral solitron lattice, and because of the DMI interaction, this is basically decided by chirality of a particular material. So like our left hand and right hand, they don't, you can't map one to the other. So theoretically it is predicted that one particular material will have one particular chirality, and then it will go into this Skyrmion phase as you increase the field. In fact, the transition of this from chiral solitron lattice to Skyrmion has been studied in great detail. I have listed 4 such papers. There are plenty of them. And in chiral solitron lattice, what happens is this solitonic dip, which is not along the field direction, this number reduces as you apply the field higher and higher. For example, here in this schematic, I have shown it is from 2, it comes down to 1, and then there is no soliton as you increase the field further. And then these discrete jumps have been studied theoretically also, and there is a very simple concept which comes from the chirality, that the length of this stripe and associated magnetization, they will show such discrete jumps. And these discrete jumps can be predicted from how many solitons and how far they are apart. From this thing you can easily calculate. Now the basic concept is that DMI is very important here. Although people have seen in TEM study that if you plot the spin direction, it doesn't remain this complete 4 pi rotation of the rather 2 pi rotation of the spin direction. It can change halfway through, so the chirality can change. In our system, it's more complicated, although in DMI system, in a science paper in 2013, people have shown that the stripe-like structure gets into this Skyrmion-like structure, and people have used the concept of magnetic monopole in the junction of these stripe phases as it converts into Skyrmion phases. So we wanted to study our system, which is frustrated Skyrmion. This is a new terminology people are using, frustrated Skyrmion, because it doesn't follow a fixed chirality. It's actually mixed chirality, because DMI is not the interaction here. It is the dipole-dipole interaction which is important. These are non-DMI film as we are studying. And how does this concept of soliton comes into picture? There is uncertainty. But we have now recently showed, this is the last part of my talk, that even for our iron gadolinium film, which is non-DMI dipolar film, we find that the Skyrmion, before the Skyrmion phase appears, when you are in the stripe phase, you get the solitonic spectra. How do you know it is solitonic spectra? Because when the up spin and down spin are equal in number and equally spaced, then you don't get the second order peak. You get only first order, third order, like that. This is similar to our concept of BCC, FCC kind of structure factor. But as you deviate from, as the amount of spin which is opposite to the applied field, decreases, and as it goes away, so you start getting increase in the second order intensity. This is beautiful mathematical physics, the soliton physics, and we use this old paper from Soviet Union, and this is a 1984 paper who have done this Fourier transform of such soliton lattice and could figure out the intensity in terms of elliptical integral, first and second times, and this is beautiful, and this is what we have used with some modification to show that the intensity of the first order peak and the second order peak indeed follows the elliptical integrals of first and second times, and this is how, as a function of magnetic field, it changes. Magnetic field is written here, and the parameter chi square is written here, and this is how it behaves. The intensity pattern is this we have just finished and submitted for publication. That solitonic physics, which is applicable in DMI, is also applicable in the non-DMI dipolar film. This is important, as I told, because it occurs near the room temperature. Well, as I showed before, the period of this satellite also changes with field, and it changes discretely, and that also comes out from these Euler equations. Only when we go at higher temperature, we find that very old good paper where the film thickness becomes important, then it deviates from the soliton physics and goes into that kind of thing only at higher temperature. Because the whole film doesn't behave like a single structure, it actually breaks into different kind of magnetic phases. But those are detail. I'll not bother about the general talk here, where people are from different fields. But both the intensity and
Sanyal, can you conclude in another 2 to 3 minutes?
Yes, I'm almost done. Can be explained in this thing, and then as it goes in the Skyrmion phase, observed in TEM as well as in X-ray diffraction, we find that it goes through a bipolar, rather bi-Skyrmion structure, which is not only Skyrmion structure is repulsive, that is why they form hexagonal thing. Bi-Skyrmion has both attractive and repulsive interaction. So to summarize, as my time is out, so we have shown that stripes in non-DMI dipolar film gives us the CSL, and also discrete jumps, and then in higher field the stripe gets into Skyrmion through formation of mixed phases, and this is bicarbon structure. Discrete jump somehow goes away as soon as we go from one-dimensional structure of CSL to the Skyrmion structure, which is two-dimensional. Discrete jumps goes away. We have to do more study, of course, the future studies, to understand the frustrated Skyrmion and how it is formed and why this kind of soliton physics is coming in the dipolar film, which doesn't have the DMI interaction, and this is important for spintronics application. And in fact, it is fascinating that the mathematical physics is working so beautifully to understand the structure we have seen. A new debate has started again since the Nobel Prize of Professor Penrose, and I will end my talk with that slogan: whether mathematics is a human discovery or a rather human invention, or it's a discovery which was always there in the world, and somehow we have found that it works for our physical worlds. And thank you very much for your attention.
Couple of questions, can you take them?
Yeah, sure.
Yeah. Anybody from within the hall? Any questions?
Yes, Milan, at the phase transition from stripe to skyrmion phase with magnetic field, do you see any changes in the spin gap or the edge effects of your 2D materials?
Actually, as I told in the beginning of my talk, that this is a kind of 5 micron beam which is illuminating the entire, structure. So to know, and as you can see in the data, that the transition is occurring across the film continuously as we switch the field. So to get the detail such structure as it happens needs scanning of the beam, which we plan to do in future.
Thank you.
Hello.
There's a question. Yeah.
Yes, sir.
Yeah, Milan, very nice talk. Is there effect of strain on this transition? For example, if you deposit on some other substrate, like a biaxial strain or a uniaxial strain, do you see any, or is it known to have effect on this transition?
Yes, it is very nice question. Actually, for BMI material, particularly Japanese group have shown that the strain plays very important role. And we are concentrating on amorphous material here, so the lattice strain is not coming into picture, and this has been tested. So in this particular case, which is non-DMI, the strain is not playing much role. At least we have not detected anything so far. However, for DMI material, people have seen the effect of strain, and in fact they have done the strain engineering to space out the phase of skyrmion from the stripe phase little bit higher temperature or higher field, simply by using strain. There are papers on that, and it's very interesting.
Does this stripe to skyrmion, is it a phase transition, like a first or second order, or is it just a change of morphology?
No, it is a phase transition, but as I have shown, it's a kind of phase coexistence. It's a kind of first order so far we are finding that it coexists. But there are some, we need more study. For example, whether this biskyrmion is an intermediate space which has some information of the stripe as well as skyrmion or not. That's a different thing. It requires more study. So in that case, what we will find is a second order transition from stripe to biskyrmion and then biskyrmion to skyrmion in our field. But we have so far not traced that because we have not having enough data. So right now we are saying it's a kind of first phase transition where mixed phase exists.
Yeah, Professor Sanyal, we'll take two more questions. One from a YouTube online participant, and the second will be from Professor D.D. Sharma. The first will be from the online participant on YouTube. The question will be read out to you.
What behavior would you expect in an XPCS type correlation? Won't thermal entropy play a role in perturbing the system?
Yes, that's a very good question. I don't know who is asking, but it is actually, yeah, please.
Anirban Ghosh.
Okay, so actually we plan to do another study where the field is not swept. It is actually stationary and temperature is stationary. Then we do the conventional correlation spectroscopy just to understand whether it is stable. But our preliminary result shows it is stable, and that is why we have gone into this kind of sweeping the field. And the correlation which we have shown here is, as I said, is as a function of magnetic field, but it is very slowly changing.
Professor D.D. Sharma?
Milan, very nice talk. A quick question that this is an amorphous material you mentioned, crystallographically amorphous, right?
Right.
And would it imply that the magnetic interactions between the local moments in some form would also have a range of interactions, or rather distribution of interaction strengths, correct?
Yes.
Will that not have some consequence compared to Skyrmions on a very ordered lattice, where we have the interactions are also, in some sense, follow a certain symmetry? Because you have magnetic interactions which will be all kind of ranges of values.
Yes. In fact, that's a very good question, Dipolar. The magnetization study has been done. There are 2-3 PRD where I am not involved. I just took up those data and found that dipolar interaction is the most dominant interaction. You are absolutely right that there will be more interaction, but the dominant one here is the dipolar interaction. The amorphous thing, although we are depositing the material layer by layer, gadolinium and iron like that, but as the individual thickness is so small, 3 to 4 angstrom, so basically they get mixed up, and we couldn't get any reflectivity data where you can see the distance, there is a distribution or a spatial ordering as a function of depth. The long-range order of Skyrmion is really surprising here, but we find it very nice. That's why this new term called frustrated Skyrmion has come. This is happening in various other films also, not only this iron gadolinium. People are seeing the long-range Skyrmion ordering and long-range stripe ordering, instead of the fact that they are basically having a out of plane, anisotropy in magnetic interaction, and the interaction is dominantly dipolar. But that's why this is very important technologically. This is room temperature and long range order, and that is applicable. That's why we are interested to understand why it happens and how it happens, and we plan to do more work on this. Thank you.
Thanks a lot.
Thank you, Professor Sanyal. Now I request everybody to join me in thanking Professor Sanyal for a very lucid and informative presentation. Speaker for this morning's session is Professor Ela. Professor Ela did her PhD from IIT Kanpur and subsequently went on for a postdoctoral research at Purdue University in the US. She started her independent career at CDRI in Lucknow and then moved on to Northeastern Hill University in Shillong, where she was there from 1977 to 1995 as assistant professor, associate professor, and then full professor. In 1995, she moved to IIT Kanpur and was there till her superannuation in 2007. Thereafter, she's been at JNCASR and she's continuing here her research as honorary chair professor. Her research area is in design and development of new genetic models for biologically important heterocycles, and she has more than 250 research papers in international journals. Professor Ela is fellow of the Indian National Science Academy, Indian Academy of Sciences, and Indian Academy of Sciences. In 2019, she was awarded the CRSI Lifetime Achievement Award. Today, Professor Ela will be talking to us on new directions in synthesis of biologically important heterocycles.
Hema for the introduction, and I thank Professor Kulkarni to give me a privileged chance to speak about my work which I have done at JNCASR. And I first of all take acknowledgement besides students. I thank the most important person in my life, Professor C.N.R. Rao. You know, he is the one who gave me first entry to chemistry research. I am talking of 1964 when none of you were born. You know, I was just MSc from DAV College, Kanpur, and I went to him. They were not taking me, biology student. Now biology has become so important, that time PCM. So, sir, I want admission. He told, okay, we can try her. She can take mathematics for chemists. So that was the beginning of my career. And then he gave me entry in 2010 when I was 65. So thank you, sir. I pray for your health and long life. besides my husband, and these students who are working. See, just now, because JNCASR, I see it is mostly physical science or biological science oriented. Chemistry is there, but not so much visible. And you had quantum material and all, but I will be speaking on materials which are most close to life. Okay. So I thought before I come to my topic, let me tell in general what I am doing and how I am doing, why I am doing and how I am doing. So I have given one slide on organic synthesis from glorious past to brilliant future. Organic synthesis, people think it enables other branches, giving molecules to biology, to material science and all. Okay, it enables other branches, but first it empowers itself by discovering new routes and designing new this thing. So this modern life on this planet would be inconceivable without the contribution of organic synthesis. It is difficult to imagine another discipline that has a greater impact on human life. This is Israel Journal of Chemistry has published thematic issue on organic synthesis, impact on human life than chemistry. Synthetic organic chemistry is the primary driver for the creation of all those advances that depend on substances that have never before been created. One of the most impactful contribution of organic synthesis to humankind, I mean after this thing, is discovery and introduction of semi-synthetic steroid, not the natural steroid, stenol and norethynol, that is contraceptive pills to control human reproduction. The fact that the contribution of this significance has never been recognized by a Nobel Prize is clearly an egregious oversight. While we agree that Nobel Committee certainly missed the discovery of oral contraceptive, they should take credit for recognizing other synthetic feats in organic synthesis, peptide synthesis, supramolecular chemistry, fullerene, conductive polymers, asymmetric catalysts, metathesis reactions, cross-coupling reactions, and it should be molecular machines actually. This again goes as synthetic organic chemistry is indeed and will always be an inexhaustible source of new molecular structure and assemblies aimed at satisfying the evergreen society needs. The creativity of chemist will be measured by his ability to design, but also prepare new molecules or molecular assemblies with desired properties which will be further engineered and produced by industry for benefit of mankind. Okay. So I told you I am a synthetic organic chemist. I synthesize small molecule heterocycles. My area, I find out new synthetic methods and design new strategies for small molecule heterocycles. So before I come to this, I have taken how small molecule heterocycles, especially they play a very important role in early drug discovery in biology and chemistry, and they are very important in chemistry and biology because they modulate the macromolecules function in living system. And I think this is not the first slide, something is, this is the one. No, I think I have skipped. We get small molecules. The first source is natural product. I mean nature gives libraries of natural products and other things which can be tested against various biological actions. But the difficulty is you get very small quantities, isotonial techniques, and then there are commercially available libraries of small molecular compounds. One can buy them. Pharmaceutical industries, they keep it in million. But the only thing is here, it is diversity is limited to variation in appendages, means only some functional group. The core is same. So the problem associated with the use of natural products and traditional commercially available combinatorial type libraries in screening experiments have spurred the development of variety of synthetic approaches for the de novo creation of small molecules. So here does a synthetic organic chemist plays a role. There are many terms which have come up. One has introduced biologically oriented synthesis, biology inspired synthesis. According to him, you take the pharmacophore part in natural products and then you synthesize library of those compounds. Then there are target-oriented synthesis, where you synthesize a particular target drug candidate, natural product, or focused library. But the most important is Schreiber introduced this term into MIT, diversity-oriented synthesis, DOS. I mean, a general consensus that is in place that library size is not everything. Library diversity in terms of molecular structure and thus function is very crucial actually. So, diversity-oriented synthesis aims to generate such structural diversity in an efficient manner. Recent years have witnessed significant achievement in this field, which help to validate usefulness of DOS and tool for discovery of novel biologically interesting small molecule. So this is my area, diversity-oriented synthesis of heterocycles. So diversity can be many kinds. It can be appendage diversity. The building block you are starting, they can have diversity. Functional group diversity, you have one core, you can decorate it with various functional group. You can have stereochemical diversity, which is important. Then scaffold diversity. You can generate methods, you can generate a library of various scaffolds. This is also very important. And these are the ones which are responsible. You don't need a big molecules. Earlier they were taking natural products and small molecule. By using this kind of diversity, you can generate molecular shape diversity. I mean, which is very important. Not only this, we also, your molecules should not also be complex so that it can bind to macromolecules in many ways. So now what is the main challenge to synthetic and medicinal chemists? How to get this diverse variety of molecules? So the key bottleneck in this screening-based discovery process, the chemist's inability to efficiently synthesize large collections of molecules with high levels of complexity and diversity. Meeting this formidable challenge is the goal of diversity-oriented synthesis. Means how to get in a unit time a large number of compounds with diverse structures, diverse functional groups, and diverse scaffolds. So many technologies have come, like solid phase synthesis, microwaves, organic synthesis, flow chemistry. Okay, they will multiply the compound, but they will not generate the new reactions. What we need, in addition to developing new technologies for increasing speed and efficiency of compound synthesis, organic chemists are looking at exploring new chemistry. In order to design all new innovative methods and strategies leading to new source of diversity. So here comes the role of synthetic organic chemist. It is not that it enables other areas, biology and material science. How does it empower itself? By discovering innovative reactions, designing new innovative strategies, groundbreaking reactions and other things. So I will show now, I start some, but another thing, we have more restrictions. How to synthesize? Synthesis is not, my students, they get frustrated, especially in JNCASR. I mean, so many people are publishing in Nature, Enzymes, JACS. We have to be satisfied with some ACS journals only. It's a very difficult science. I mean, a solvent will not, if you change the solvent, you will get a product. If you change the time, you will get a product. If you change the temperature. So, I mean, these are the rules which have been created, they call green chemistry. But the holy grail is, I mean, for organic synthesis, ideal synthesis, you get the compound in 100% yield in one step and with zero waste, because greener chemistry doesn't want waste, and 100% selectivity. And also easily available starting materials, because ultimately it has to go to industry. It should not be very costly method, and catalytic methods, because you can pick up the catalyst. So now I come to my work. Our means chemistry is based on generating first new class of building blocks. They are mostly organic sulfur building blocks. You design new building blocks and design new reactions and new strategies around those building blocks to generate series of, usually make library of 25 compounds, but if you want, we can make hundreds of compounds. But because for publication, 20 to 25 compounds are enough. So some of these, building blocks which we used earlier, and I will be speaking on these ones. actually recently. And what are the strategies we use? See, 2010 Nobel Prize has gone to, palladium catalyzed cross coupling reaction, means since then transition metal catalyzed cross coupling reactions have become very important. Then atomic NOMI reaction, Bedrost has introduced zero waste. You just, you require just CH, I will show you functionalization. Then domino reactions are very important. How earlier you used to do one reaction, you protect a group, another 100-step synthesis, and you will say, oh, it's a great. Now, how can you do all reactions in one pot in 1 or 2 steps? How can you make many rings and many bonds in one pot reaction? So that I will show you. In fact, domino reactions. Then sequential multi-component reaction. You put everything together either in sequence or other thing, and you generate the product. And then latest, discovering new reactions. Now again we are coming back transition metal free coupling reactions. So now are there. I'm starting my work. Anyhow, so that's what I do. That's what I have told you, that what I am doing. Now I will, and why I am doing. Now how I am doing, maybe many of you, because none of you are synthetic organic chemists, you might not appreciate, enjoy, but otherwise you can just listen to me. Oh, okay, enough time. Okay. So this is the work Vijay Kumar, the first student to get PhD. This is all transition metal, cross coupling reaction. These are the intermediate which we have designed. I don't tell you why we have designed, because bromine and halogens are good to do oxidative addition with transition metals like palladium, copper. We generate this kind of inaminonitrile in situ. Again you see it is 2-step 1-pot reaction, and this is a copper catalyzed reaction. Copper is cheaper, less toxic, so it is replacing palladium. Then you have to use ligand, L-protein. Okay, it's all right. And we get a library of indoles, and indoles is called king of heterocycles. So many I have shown, indomethacin, pindolol, many of the drugs have indole nucleus. Okay. So here I have shown you, by doing this cross coupling reaction, I have shown you usually make 20 to 25 compounds with, you can have aromatic ring here, and you can have pyridyl. Pyridine is supposed to be very important pharmacophore, indole ring, alkyl ring, you can make thiophene fused indole, all kind of compounds. Okay. Now I go to next reaction. Why bromine? So according to, again coming to, how to, efficiency of reaction, you have to, starting material, you have to introduce halide to do oxidative cross coupling. Can't we do reaction without bromine? This becomes a simple starting material. So this is called now transition metal catalyzed CH activation. You can make a CC bond, a CN bond, and all kind of bond. And this is called atomic NOMI reaction, because here you are losing only a hydrogen molecule, H and N. Here you are losing HPR. So it is a waste, only hydrogen waste is coming up. Okay. So we follow also CH activation. This is another student from here. We have to, this you need not worry, this is a palladium catalyzed reaction. To generate palladium we use again, palladium 2 we use cupric acid as oxidant. These are the reaction conditions. Sometimes it takes weeks and months to optimize. See, most important in synthetic chemistry is to get optimized reaction condition. So once we have optimized reaction condition, the spiridopyroles are very important, thienopyroles. I have shown you only sim methods, but you can generate again hundreds of compounds you can generate by this. Okay, so this is better method than earlier. Instead of bromine, we are having hydrogen, we can have easier method. Okay. Now this was indole. Now we come to another. Can we make CS bond? Sulfur is supposed to poison transition metal, but it is possible to make CS bond again by intramolecular cross coupling. We generate benzothiophene, which are also important biological molecules. Raloxifene is a drug, selective estrogen receptor modulator. This azoxyphene is used for breast cancer, and tubulin polymerization inhibitor, these compounds. Okay. So what we do, these are the intermediates. I mean, this is our dithiester, nobody has explored. Again, you generate this thiolate anion, put copper catalyst, you have CS bond formation, very good yields. And so here again I have shown by doing this cross coupling reaction, we can make the library of benzothiophenes. Not only aromatic ring, we can have predyl ring here, and indole ring, thiophene ring is fused. So like this we can go on making as many compounds you want. Okay. So again here you see bromine is there. We are doing cross coupling with bromine. So again, to make our method more marketable, better, can we replace bromine? It becomes a more simple starting material. So we just do CH activation, this is called, I mean same strategy, you thiolate anion, but you have to do now, that is oxidative CS bond formation, and again you can generate the library of benzothiopene, not only CN, diversity, you can have CO aryl, you can have a carboxy group, 2 position you see the diversity, you can have indole, substituted aromatic ring, alkyl ring, furyl, I have not seen, you tell any group we can introduce. Okay. So your method becomes still better if you can make some target compound. So here we have shown utility of our method by generating synthesizing reloxifene precursor, which has been known in the literature to be converted to reloxifene. So we take such kind of desoxybenzoin, follow the same strategy, generate the thioenol, palladium catalyzed CS bond formation, and then removal of paramethoxy benzyl group. This has been converted. Similarly, we generate this tubulin polymerization inhibitor. They are very potent tubulin polymerization inhibitors. Same strategy, only thing is substituent are different. Okay. So this was the story of benzothiopene. So here, this is earlier work, I am not going to speak, Vijay Kumar's work. We can generate scaffold diversity through building block. We can generate a series of building block. We have shown earlier, we can make oxazoles with different substituents, we can make thiazoles, we can make imidazoles, we can do a domino reaction, but I am not speaking about it. I will speak about next. See, this is a very simple, I mean, thio group intermediate, beta diketone. Usually here unfortunately there is no synthetic organic chemist. 1,3-diketones are very popular in synthetic, making 5-membered heterocycles. But nobody has explored 1,3-monothioketone. The difference is here you have a 2-keto group. Here you have a C double bonded CO group which differ electronically. And usually if you treat with phenylhydrazine, you get mixture of 2 regioisomer, 1, 2, 3, here you have a 4-chloro, here phenyl, here you have 5 position. And you see regioisomers, one regioisomer is so active, pyrazole, other is inactive. So how to get a particular regioisomer? And all pyrazoles are also very important, COX-2 inhibitor for rheumatoid arthritis and anti-inflammatory agents and all. Okay. What happened? It's not working, eh? It's working, eh? So we taking this in situ, we generate these thioketones and just react in reflux in phenylhydrazine. We get only one regioisomer. You see, 4-chloro is at 5 position phenyl and 3 position phenyl. But if you just modify the reaction condition, generate SME, you get exclusively regioisomer where 4-chlorophenyl group is at 3 and this 5. So using this strategy, they have again one pot reaction. We have generated again the library of these pyrazoles. I have shown only 3. I mean, depending on what ketone you take, you can generate, you can decorate your core with either indole group, predyl group, like different groups. Okay. So not only this, we have developed regioselective synthesis of isoxazoles. I am not going detail. Okay. So another, as I told you, regioselectivity is very important. This is also a very good academic problem. I mean, students, if I say you take this another kind of sulfur intermediate which we use, from this, how will you generate 2 regioisomer? You see here R is at 5 position, acyl group is at 4 position, here R is at 4, 5. So, I mean students will come up, we have designed halogenation, amide copper catalyzed cross coupling, or you do 1,4 conjugate addition, you can have, see both regioisomers we have prepared, 5 position acyl, here 4 position acyl, R group at 5, okay. So here I have just shown you, I mean it's a big paper, huh?
3 minutes more.
Only 3 minutes left.
We're running behind schedule.
No, please give me at least, because I have to finish just whatever time I have been allotted. Okay, so this is the synthesis of thiophene using same methods. I'll go fast of course, because these things people might not enjoy. Okay, so thiophenes also are important, I mean course, in medicinally important course. So we develop one pot synthesis of thiophene. This is again functional group diversity, it shows how many functional groups we can introduce. At this position, acyl group, nitrile, ester, and this thing, I mean this just shows diversity oriented synthesis, various functional group. Not only group, we can make highly fluorescent thiophenes if we increase the conjugation. I mean you can go through the paper where we have shown the fluorescence spectra studied and all, okay. This is also very nice recent work, this is the only unpublished work, thiazole based, I mean they are all important. 75% of drugs have heterocyclic core. So thiazole core based we have this compound, and please note this compound, this is a very potent tubulin polymerization inhibitor with the comparator-statin capacity, okay. So you see this is also functional group diversity we have shown. I mean this is the method we generate it. Here we can have C and COAR and all groups, and here NH2 is constant, and you see we have generated the library functional group, this is functional group diversity, CN, COCH3, COPH and CONH2, and this group so many, here you see so many groups we have shown. Not only this, I showed you first slide, this is a very potent, I mean tubulin anti-cancer compound through tubulin polymerization inhibitor. It has been prepared from same starting material in 3 steps with moderate yield. We have prepared it in 1 step in very high yield. So that's how yield is also very important. I think another 2 minutes I will finish there. This is another reaction. Now I come to multi-component one-pot reaction. We do sequential one-pot reaction. I will try to finish fast. So, I mean you see first we standardize the reaction. You react with amine, sodium nitrite, nitroso, potassium carbonate, you get imidazole. On the other hand, all you can do after standardizing, you can generate inaminone, nitrite, this thing in one pot, and we have made imidazole, which are also important. So this is the, I mean, again this is not working. So this is Imidazole Library I am showing, okay. So this is also multi-component 3-step reaction we have generated from same intermediate, this intermediate benzothiophene, okay. So from same intermediate, such a simple intermediate you see isoxazoles, thiophenes, imidazoles, benzothiophene, pyrazoles we have generated. This one, since Mary has shown the this thing poster, I don't take, but only thing I'll show, it's a new reaction. Again isoxazoles, you see we have prepared this isoxazole of oxacillins also, and see those reported methods, they are dipolar cycloaddition or hydroxylamine, they have inbuilt NO bond. There is no methods in the literature where we can build a NO bond. So we have made, you can go through this, when we react it with sodium nitrite, we get isoxazoles. So this is the library of isoxazoles we have prepared. This is a new reaction, and this is the unit present in oxacillin, this thing, We have also prepared this hexaxazole unit. Okay. Now again coming to new reaction. See, I started my lecture with transition metal catalyzed reaction. Now transition metal catalysts are costly, toxic. So can we do reactions? Many papers are coming. I mean CC bond formation or C heteroatom bond formation. It goes through single electron transfer reactions. I have shown the mechanism. Okay. So this is CN bond formation. You can make heterocycles. So this is also latest work. We developed this strategy for CS bond for making benzothiazoles. So Yogend's work, I mean this is one step. I mean we generate benzothiazole with so many diversity, so many functional groups. Here is the mechanism. This goes through single electron transfer reaction. I mean iodine gives a radical and dimerization. Okay. This is again benzothiophene without, I have shown benzothiophene with transition metal. This is just you take sodium hydride, same starting material, room temperature 3-6 hours. Some of them are quantitative, very good means reaction. Okay. This is the last. I come to domino reaction. Our group the first to start domino reactions in this country because I work with Professor Titze. You know, here just like nature also from squalene it makes a steroid, from how you make so many rings and bonds. Just put acid, ring, cyclopropyl ring open, it again joins to give one cyclopentene ring, two cyclopentene ring and a keto group hydrolysis. So this is a very nice example of domino reaction, and this is also, and I am also coming to scaffold. Till now I have shown you functional group diversity generation. See, this is also a, I mean serendipitous domino reaction. When you react with this thing, you get ring expansion and pyrrole annulation in one step. Just I am finishing. So you have so many new scaffold diversities we have generated. Okay. So here also this is a scaffold, we design a reaction and I will just skip it. We generate from simple starting materials. See, just taking this starting material, 10 new scaffolds. This is a very good example of scaffold diversity generation. And this is the last. It's we know alkaloids have this beta carbonyl ring, which is important. So many alkaloids. So we annulate. I mean we annulate different by through using synthetic technique, and we annulate various rings. So we have made these names are given. Indoloestic acid. See, just this old Niniscu reaction, we can, I mean, two rings we can annulate. This is also very important ring scaffold and functional group. So from same one starting material, again this is a very good example of scaffold diversities. This is the end of my lecture. I have thanked all students in the beginning. So this is my last journey, I will say, in research. So I can see this path, I really like it, and thank you so much.
The first session comes to a close. I once again thank Professor Sanyal and Professor Ela for their lecture.
Hello everyone, welcome to the second session of the annual faculty meeting in-house symposium, and I'm happy to introduce the first speaker of this session, Professor Hemalatha Balaram, and I'll give a short introduction to the speaker. So Professor Hemalatha Balaram is currently the Dean of Faculty Affairs and Professor at the Molecular Biology and Genetics Unit at the JNCASR. And she did her PhD from the Molecular Biophysics Unit at the Indian Institute of Science in 1985. And she did 2 postdoctoral fellowships at the Indian Institute of Science and the University of California, San Francisco. And she joined JNCASR after a short stint at Astra in 1996 as a faculty fellow, and since then she has been associated with the Molecular Biology and Genetics Unit of JNCASR. She has also held 2 dean positions. Apart from the current dean position, she has also been the Dean of Academic Affairs and Faculty Affairs. And her areas of research and research interests are molecular parasitology, molecular enzymology, metabolism in parasitic protozoa, and protein engineering. Her work has been recognized by several awards and recognitions. I will name a few. She's a fellow of the Indian Academy of Sciences. She won the Dr. Rajaramana Award for Scientists from the Karnataka State Council for Science and Technology. And she's been awarded the J.C. Bose Fellowship recently, last year. And today she is going to talk about living with enzymes. So I welcome Professor Hemalatha Balaram.
Thank you, Raja, for the introduction. To begin with, I would like to thank Professor Kulkarni for giving me this opportunity to present some of the work that's going on in my laboratory. We look at metabolism in the malarial parasite Plasmodium. Plasmodium causes malaria, and it is a major clinical problem despite the fact there have been numerous efforts at curbing this disease. Metabolism in any cell, in any living organism, is a series of reactions, transport systems, and other processes, each of which is catalyzed largely by protein molecules. And we've been looking at two aspects. One is the flux of metabolism itself in the parasite, and other are these individual molecules, the protein molecules whose structures are shown on the slide, which catalyze each of these processes or which facilitate each of these processes. And today's talk, I'm going to focus only on these molecules and not on the flux of metabolism. I'm going to focus on 2 or 3 of these molecules that that's shown on this slide as to how they function. And that should give you an overall view of the diversity in both in the nature of enzymes, the mechanisms that they use, and the dynamics that operates in these systems. So, brief introduction: enzymatic reactions show tremendous rate enhancements compared to the non-enzymatic counterparts, and they catalyze a whole range of reactions. And if you look at any metabolic chart, you'll find that you have crisscrossing pathways, and the kinds of reactions that take place in a cell are extremely diverse. Their catalytic performances, mechanisms, global folds, active site architectures are also very highly diverse, suggesting that enzymes are shaped by an entire range of physiological demands, evolutionary constraints, as well as by chemical and physiological constraints. To phrase it, as Jim Naismith says, enzyme mechanisms are chemistry's prodigal child. So, two key aspects when you look at, shown in the slide, are 2 key aspects when you look at catalysis itself, whether it is catalysis by inorganic complexes that Professor Ela mentioned, or by enzymes. You have stabilization of the transition state, activation, lowering activation energy barrier, leading to acceleration of reaction rates. 2 things. One is this classic transition state, the diagram, the reaction coordinate diagram. And other thing that one uses widely is the classic Michaelis-Menten equation. And now you have variations of this equation. And shown here are pictures of people. There are many people, but I've shown here pictures of key people who I think laid the foundation of our the understanding that we have today. And in my view, I would like to quote from Haldane's treatise, which is titled Enzymes, which is the forerunner, I feel, to whatever we understand today. And what Haldane said is as follows: an enzyme substrate complex, substrate is the molecule that is getting converted into a product. An enzyme substrate complex requires a certain additional energy of activation before reacting. And he said that, he suggested that Emil Fischer's famous lock and key simile be amended to allow that the key does not fit the lock quite perfectly, but exercises a certain strain on it. And this is a very profound statement, because with this statement he introduces the notion of substrate strain and substrate distortion, which is so fundamental to enzyme catalysis. We accept enzymes now. We know we can purify them, or we can study in vivo in the system. But in the beginning of 1900s, this was not thought that it's just not possible to pull enzymes out. And it was the group of Willstatter who believed that you need intact cells or lysates of intact cells, and you can never purify enzymes. And in 1946, people who had worked hard towards purifying enzymes and actually, like organic chemists, crystallizing them, didn't solve structures, but it crystallized them the way organic chemists do to purify a compound where Sumner and Northrop both got the Nobel Prize in 1946. And the Nobel citation says this monumental work was of very great help in bringing the scientific world to admit that enzymes can be isolated in pure and crystalline form. Now you have enzymes which are even used for therapy, but way back then it was thought that you can never take them out of cells. In his Nobel lecture, Sumner says, which is a very profound statement, he says someday every enzyme in living matter will have been discovered and described. Every chemical reaction which goes on will have been recorded. We have indeed gone way ahead from the days of early 1900s. Second major discovery in our understanding came actually from India with regard to what are the allowed regions of conformational space that a polypeptide can adopt. And this was the fundamental discovery. After having solved the structure of collagen, it is the discovery of Professor G.N. Ramachandran sitting in Madras University, where he applied stereochemical constraints to show what are the allowed regions of conformational space in a polypeptide. A polypeptide is a protein. So a polypeptide is a polymer of amino acids, and they are linked to one another by a peptide bond, and the peptide bond as shown in the slide can be either in trans or cis geometry. The trans geometry is most favorable, but when you have a proline residue, which is an amino acid, you do have cis peptide bonds. The other 2 degrees of conformational freedom are the 2 dihedral angles shown on the slide, phi and psi, rotation of which gives rise to various secondary structural features in proteins. And the Ramachandran map, which is shown on the right corner of the screen, is the classic map which now every structure that you solve has to comply with the Ramachandran guidelines, otherwise your structure is discarded. And shown below are the first structure of a protein that was solved by Kendrew and Perutz was that of myoglobin, and shown here is the structure of hemoglobin at different levels of structural hierarchy, the secondary structure, the folded tertiary structure, and an assembly of multiple subunits which gives rise to the quaternary structure. The first structure of an enzyme, which gives you an idea of what is the active site like, does it mimic, is it a complementarity of the transition state, came from the structure of lysozyme. That was solved by D.C. Phillips, and shown here is the Royal Society lecture delivered by D.C. Phillips, where he has the string of amino acids hanging down from the roof of the hall and the folded structure. And this structure for the first time gave complementarity, gave the visible view that the active site mimics is a complementarity of the transition state. And with this brief introduction, I'll go on to show you how there is, these structures, all that you see in textbooks or in papers, are all static structures. But enzymes do not function as static molecules, they're highly dynamic. We've been looking at different aspects of catalysis itself, right from stabilization of transition state to structures and so on and so forth. But I'm going to touch, because I have only a few minutes, I'm going to touch only upon an aspect that is dynamics. How critical is dynamics in modulating catalysis itself and regulating catalysis. Shown here is an early enzyme that we worked on. We don't work on this enzyme anymore, but we did a lot of work on this enzyme, which is hyperxanthine guanine phosphoribosyl transferase. This is in one metabolic pathway that we study, and that enzyme I abbreviated as HGPRT. It catalyzes the formation of nucleotide monophosphates. Inosine, guanine, and xanthine nucleotide monophosphates, which is very fundamental process in generating nucleotides within the cell. And this is through a salvage pathway. Enzyme, there are 3 structures shown here. One is that just of a monomeric unit. The enzyme assembles actually to a dimer, and in the presence of substrate, the falciparum enzyme associates into a tetramer. All reactions, you can monitor them, and shown here in the inset of the bottom curve is what is called a reaction progress curve, and that's how typical reaction progress curves looks. But there are enzymes which show a lag, and this behavior is known as a hysteretic behavior. They show a lag, they don't immediately catalyze a reaction, and the question is, why is there this phase where there's no catalysis that takes place? And we also saw that if we pre-incubate the enzyme with certain ligands, it shows a typical reaction progress curve. There is no lag. So we did many aspects with regard to this to investigate what is the conformational transition that is happening in this enzyme, which takes it from this inactive state to an active state. We did structural biology, enzyme kinetics, a lot of biochemistry, and also a lot of molecular dynamics in collaboration with Professor S. Balasubramaniam in the Chemistry and Physics of Materials unit, Meher Prakash from the TSU unit, and Tarak Karmakar, who was a Bala student, who also contributed to this project enormously. So what is the change that is happening? One key change in this is, as I said, all peptide bonds are trans, except when you have a proline. But in this family of enzymes, you have a peptide bond which involves a non-proline residue, a leucine and a lysine, which flips from trans to cis and cis to trans back again with every catalytic cycle. This is a large energy barrier conformational transition, and this provided a framework for carrying out molecular dynamics, well-tempered metadynamics, to understand what exactly is happening. To cut this long story short, I'll show you two videos over here. Dynamics is all about visualizing motions, and one needs videos over here. And shown in red is the loop which closes over the active site during the process of catalysis to enable the water from to prevent water from getting in, so that the transition state intermediate is stabilized during catalysis. But with regard to the dynamics in the protein, which involves the peptide bond isomerization, shown here is the transition from cis to trans, by which you can see this side chain which goes back and forth, flips back and forth, by which it opens up the active site so that substrates can bind. Catalysis takes place and it opens back again to release the products. So this is one example of, as I said, I'll focus only on dynamics. This is an example of dynamics which involves loops, which is very common, but most uncommon feature is a dynamics which involves peptide bond isomerization. Yeah. So peptide bond isomerization, where a proline residue is not involved, is very, very rare. And you find them occurring only in very important regions of the protein, usually next to active sites. And I've shown here examples of enzymes which play a very fundamental role in metabolism, cell division, DNA replication and everything, which do have this kind of flipping of peptide bond isomerization, which is a large energy barrier transition. It is not just there in the phosphoribosyl transferase that I showed you. Nature has conserved this mode of regulation in all phosphoribosyl transferases. The large family of enzymes is conserved everywhere. So this is an enzyme which is involved in an anabolic process where a nucleotide is made. There are enzymes which maintain just homeostasis in a cell. And homeostasis, by the term homeostasis, what I mean is it holds complex systems together invisibly, and we notice them only when systems fail. And that's something that I've taken from Siddharth Mukherjee's article in the New Yorker. So not just complex systems like the human body that is shown over there, all cellular systems need to maintain homeostasis. You need to have a steady state. And the enzymes which play a role in this show diversity in substrate specificity, that is the molecule on which they catalyze the reaction. They show enormous regulation, that is, they respond to metabolic cues from the cell. They have diversity in sequence, the diversity in structure. We were looking for one such homeostatic enzyme from Plasmodium because studies have shown that we need to modulate IMP levels in the cell, and we didn't find counterparts of what is there in bacteria and what is there in humans. But what we found was an enzyme which is there only in the fungal kingdom, which is there in certain parasitic protozoa. And shown here are results from our studies on both kinds. One is what is known as cytosolic nucleotidase 2, which we call CN2 over here, and other is which is there in humans, which is there in bacteria, and other is an enzyme which is known as ISN1, which is present, as I said, in the fungal kingdom, and it's present in what are called epicomplex and parasites. And I've listed their features over here to show diversity. The bacterial enzymes, the substrate is GMP. The activators are guanine nucleotides. The human enzyme, which is very similar in sequence, very similar in structure, but shows sequence variation. Its substrate is another nucleotide, which is known as IMP. The activators are ATP and glycolytic intermediate 2,3-bisphosphoglycerate. The sequence of CN2 and the sequence of ISN1 have no similarity. The structures that I've shown here are of monomers of CN2, the tetramer of CN2 which is functional, the monomer of ISN1 which is which associates to form the functional tetrameric unit, and you can see just by looking at these pictures that these structures are very different. But I must tell you that in the active site of each of these enzymes, the pocket is completely conserved. They may show substrate specificity variation, but the chemistry that they catalyze is identical. Despite this overall, the protein looking so different, the little active site that is there is highly conserved. What I'm going to show you is that you have such sequence diversities, but mechanism of catalysis is retained. But I'm also going to show you how both show such differences in dynamics. Shown on the left here are the human and the bacterial cytosolic nucleotidases. And to enable catalysis, shown here numbers and arrowed lines which show movements in the protein which either enable substrate binding or movements in the quaternary structure which enable regulation. So I said this is an enzyme which maintains homeostasis. It's regulated by metabolic cues from a cell, and those arrows show you the directions in which subunits move or direction which domains move, which enable both catalysis and regulation. The ISN1, which we recently completed the study, shows a remarkable range of dynamics, which is so different, but the catalysis is just the same. Yeah. So you can see small motions upon the activator binding. Activator is bound ATP, and then when the substrate binds, you see a large conformational dynamics. This came out of solving more than 8 independent structures, and these conformational dynamics are needed for the loops to move out, are needed for the substrate to bind. Otherwise, the loops move in and occlude the pocket where the substrate binds, and the movement outwards is what permits the substrate to bind. And as I showed you early on in this video, ATP, which is a modulator of activity binding, brings about domain reorganization. So it's an example of how you have large structured features becoming intrinsically disordered, and then back to order to disorder transition, enabling ligand binding and catalysis. Domain movements which bring about activator binding and regulation of catalysis itself. Yeah. All the while I've been talking about enzymes. These enzymes have a single pocket where the substrate, that is a molecule which is going to undergo reaction, binds and catalyzes the reaction. But there are also enzymes which tunnel intermediates from one active site to another. And one such tunnel that is there in biological systems is a tunnel which transfers ammonia in its neutral gaseous form, not as ammonium ion, from one active site to the other without diffusing into the medium. If it diffuses out into the medium, the pKa is ammonia as such, it would immediately get protonated into ammonium, and that would not be conducive for the chemistry that is needed. So all these enzymes are complicated machineries. Shown here is one such ammonia, a schematic of one such ammonia transfer. And the enzyme that we studied is an enzyme which makes the nucleotide GMP. This enzyme has 2 active sites. It's one single polypeptide chain folded into 2 domains with 2 active sites. In one active site, which is in blue, which is known as the ATPPase, it takes a molecule of ATP, condenses it with a molecule of XMP, and forms this high energy intermediate known as adenyl XMP. In another active site, which is distal from the ATPPase active site, is the pocket of this domain which is known as GATase, which catalyzes the hydrolysis of glutamine to glutamic acid, generating ammonia. So you need to know only 2 chemistries. One is the formation of this activated intermediate, other is generation of ammonia. These 2 must be coordinated, and the term that we use in biochemistry is allostery. So there must be conformational dynamics through which we form an ammonia tunnel. Ammonia gets tunneled and the chemistry gets completed. How do we understand this? First, we do simple biochemistry to show that there is indeed ammonia tunneling. And we resorted to the use of what is known as N15 edited NMR spectroscopy, HSQC, to show that ammonia is indeed tunneled, doesn't leak out and go back in. The second was to show through what is known as hydrogen deuterium exchange mass spectrometry that there is crosstalk. There is conformational crosstalk across this large protein molecule, and both showed biochemically that it is indeed true. We hadn't solved the structure, but there was one structure available which did not provide any evidence for either the presence of a tunnel or for such kinds of large conformational crosstalks. So we took recourse to, we were studying this in Plasmodium, we took recourse to making mutants. We can make mutants by site-directed mutagenesis, which will be able to bind every single reactant but not catalyze the reaction. Our hope was we would trap some kind of intermediate high energy transition state by which we can now understand ammonia tunneling, conformational crosstalk, and formation of this high energy intermediate. And we were lucky enough to get a structure which was the first structure which showed a very large scale domain movement, and that is schematically shown over here. This is the structure with no ligand bound in it, and when you bind a ligand in this active site, this domain rotates by about 85 degrees. It's a very large domain rotation. And we were fortuitous in this because we had in our sequence 2 cysteine residues before rotation which were far apart, but upon rotation they came close by, and when cysteines come close by they can react and form a covalent bond known as the disulfide bond. This trapping it in the state also enabled the mapping of a loop which was hitherto unmapped. 5 minutes? Yeah. So the structure was not enough. We resorted to molecular dynamic simulation by which we could show that somewhere in between during the rotation at 60 degrees we have a tunnel that is forming. This permitted us to propose a mechanism for catalysis and also propose what are the elements in this structure which mediate the chemistry, and also mediate conformational dynamics and domain crosstalk. I won't go into the details of this because I don't have time. But as I said, there is diversity in nature. I showed an enzyme which has this 85-degree domain rotation to enable catalysis and product formation, which is essential for metabolism. But if I look at the same enzyme from an archaea which lives in volcanic vents at the bottom of the ocean, then it's not one single enzyme which is connected by a linker as shown over here, but it is 2 enzymes which are just separated. But they come together, dock and enable catalysis. They tunnel ammonia, they do everything, but they're 2 separate enzymes which have to come and dock. So we thought if they're going to go ahead with catalysis, I should be able to isolate this complex in solution, maybe get the crystal structure. But what we found was that the complex is extremely unstable and its lifetime is less than 400 milliseconds. So the question is, how do I know how is this complex, though it's short-lived, how does it work, how does it look, how does it work? And we took recourse to a procedure known as cross-linking mass spectrometry, and where we cross-link residues which are close by, analyze the data, which is the most complicated process, and then tease out connections which are relevant across the 2 subunits. And thereby now we have just arrived at the structure of the first picture of what this complex would look like. A transient complex which is just there for a few milliseconds and dissociates every cycle of catalysis. I told you all about dynamics, but then you don't want dynamics all the time. Systems live at abnormal conditions, biological living systems, and you find that you have to have proteins very rigid too. And during the course of investigation of this earlier molecule, we found that one of them is modified post-translationally, and this post-translational modification known as the succinamide imparts rigidity. So we solved the structure to see if there is indeed a succinamide which is predicted by mass spectrometry, and there is the electron density map here showing that there is a stable succinamide. This is a feature in a protein which is a consequence of aging. Because succinamides are unstable, they undergo hydrolysis and give you unwanted changes by which protein structures change. But here we have an example where nature has exploited this feature, a post-translational modification, and kept it there in place without undergoing hydrolysis. So the structure now tells me 2 things, that there is a succinamide in a protein, and it also tells me the environment in which the succinamide is, and what are the secondary local structural features in this protein which has a succinamide. What are the advantages of having the succinamide? It keeps the protein remarkably stable at temperatures at which the organism lives. It lives in deep volcanic vents, so the protein doesn't unfold. It doesn't unfold to cheiotropes. It doesn't unfold even when you are boiling. The wild type protein, the mutants all precipitate out. And it's active at extremely high temperatures. So I collaborated on this again with Bala, and we did not regular MD, we did what are called REST2 simulations to show that once I put the succinamide in, the protein is remarkably stable. Once I remove this post-translational modification, the protein starts unfolding. And Sudeep, who was working on this project, asked the question that if I, instead of using a succinamide, which is a cyclized residue, can I now use an amino acid which is already existing in nature itself? That's a proline, which is again a cyclized residue. Will I get the same stability or not? What we found was that we cannot play so easily around, which nature has done by over millions of years of evolution. When we do the same thing, thinking that we are indeed on the right track, we found that we replace one conformational rigidity with another conformational rigidity, we in fact end up destabilizing the protein. We were lucky enough to get this entire structure solved and the loop mapped, and what we found was a local environment is what now dictates long-range conformational interactions, and these in turn dictate the rigidity of a protein. So I've shown dynamics, I've shown rigidity, and these are results of the simulation which show that if I replace succinamide, which imparts rigidity, with proline, which is also a cyclic amino acid, which is rigid amino acid, this simple replacement, one-to-one does not work, because evolution has perfected it by placing only a succinamide, and I can't flip from one to the other. So this is just to show that there are many such modifications which are not genetically encoded, so you don't get information on them. Most of them are serendipitous discoveries, and we don't have an omics approach for this, and one actually needs such omics approaches to now cover a space which goes beyond genomics. I will conclude with just this one slide. I think gone beyond my time. I'll conclude with just quotations from two people who have contributed enormously to the field. One is Francis Arnold, who got the Nobel Prize 2 years ago for in vitro evolution. And other is Dan Tawfik at Weizmann Institute, who's been looking at dynamics and evolution from a very fundamental perspective. So let me quote Francis Arnold before I conclude. What she says is that evolutionary innovations over very large timescales have generated mind-boggling diversity. There are myriad enzyme reactions for any given biotransformation, and a multitude of transformations catalyzed by any given organism. The biological world is teeming with catalysts, and this cauldron of chemistry is a rich source for ECMO. And with regard to all the dynamics that I talked about and evolution, there's a picture that is shown on the slide, and also the statement made by Dan Tawfik. A single protein sequence can adopt multiple structures, and that is what I showed you, and functions, which can be separated by either local conformation fluctuations like the loop movement I showed you, or global conformational changes like some of the other examples that I showed you. This flexibility allows enzymes to vastly expand their functional diversity, as the incorporation of mutations can alter the conformational ensemble of a protein towards conformations that are only rarely sampled in the wild type, but allow it to bind new ligands and perform new chemistry. And that's exactly what happens in evolution. You have mutations which change dynamics in a protein, and change in dynamics in a protein brings about evolution of new biochemical functions. There are numerous questions that one can ask with regard to all these questions. A few of them are put down over here. This field is at the interdisciplinary areas of biology, physics, and chemistry. And new areas, for example, vibrational spectroscopy, are things which I feel will contribute enormously towards understanding mechanisms. In vivo NMR, which has now made very breakthrough papers, will also contribute to this, and also development of new computational techniques. So before I close, this is a slide of acknowledgements. First and foremost is to acknowledge JNCASR for providing me with the place, facilities and funding to tinker with biochemistry of living systems. I would like to thank the past and present directors, the chairs of my unit, the faculty of my unit, faculty of JNCASR for everything that has facilitated for my group to carry out this research. Listed here are numerous students, postdocs, others who have contributed to the various projects that have been running in the lab. Also collaborations within JNCASR, collaborations with other groups in the institute and collaborations with groups elsewhere in the world which have enabled this research. And funding from various sources, first and foremost JNCASR and other sources, have enabled me to carry out this research. Thank you for your attention.
Various points we are starting with quote from Holden. You're talking about the fairly strong interactions that are involved in enzymatic activity.
Strong non-covalent interactions.
Sorry?
Non-covalent interactions,
Non-covalent.
by and large.
Yeah. So does this have an effect on the degradation of proteins over time, or enzymes over time? Is anything known about it?
Dynamics itself. Is that what you're asking?
So the act of sort of having strong non-covalent interactions, which sort of are turned on and off during the enzymatic process, must potentially lead to conformational changes.
Yeah, that's a valid point. How unfolded can a protein be and still escape, degradation? There must be balancing forces which act in a cell, which, most of these unfolding processes are very, very transient. So I'm talking of processes which are in very low time scales. Catalysis itself is faster, but these are again on time scales which are very slow. I do not think that, they will be, if they are opened up completely, then they're prone to the degradative machineries. But then you have chaperones in the cell which may enable it to fold back again. But these transitions are on very small time scales, fold back and forth. And it is not that the protein is completely unfolded. But then if you keep a protein in solution, you will have an equilibrium. You will have an equilibrium and proteins will tend to, some amount of it will unfold. It will happen again and again.
Sridhar, you can ask a question.
Okay, a couple of really short questions. What is the length of the tunnel which ammonia moves through, and what is the driving force for moving across the tunnel for ammonia?
Yeah, so I earlier had talked about this driving force for ammonia tunneling. The length varies from 100 angstroms to about as short as about 20 angstroms. There are a family of tunnelers, and the length in these tunnelers vary anywhere between 120 angstroms to about 20 angstroms. Some tunnels are short, some tunnels are very, very long. So that's your first question. The second is there must be a series of interactions as ammonia tumbles down through the tunnel, which, it's going down an energy gradient. Otherwise, you will have ammonia just shuttling out short distances. There must be a series of interactions where it goes down an energy gradient, and hence it forces it to go from one end where it's generated to an end where it's utilized. Otherwise, there is no direction, there will be no forceful direction in the movement of ammonia itself. This is a question that hasn't been fully addressed, and it's a complicated question to address experimentally.
Is it possible that it may be some kind of field induced?
There are multiple, if you look at tunnels in many of these in which there's a preformed tunnel, that is, it's not a transient tunnel like the case that I showed you. In cases where you have preformed tunnel, you can actually look at the walls of the tunnel. And are there any, hydrogen bonding interactions which can put the ammonia molecule, from one location in the tunnel to the next location, to the next location, so on and so forth. I had once discussed with a faculty in IISc to look at even inversion of ammonia. What I mean is quantum inversion, by which could also play a role in finally pushing ammonia molecule through the tunnel. but I haven't actually looked at it from that perspective, though it has been there at the back of my mind.
Thank you.
Yeah, thanks, Sridhar, and thank you, Professor Balaram. So, welcome, Dr. Jyotirmayee Dash. So, Dr. Jyotirmayee Dash has obtained her PhD degree in Organic Chemistry from the Indian Institute of Technology, Kanpur, India, under the supervision of Professor F.A. Khan, and she has done 2 postdoctoral fellowships at Prague University, Berlin, and also at ESPCI, Paris, France. And she also did a 3rd postdoctoral fellowship at the University of Cambridge in UK, and she joined ICER Kolkata in 2009 as an assistant professor, and then she moved over to the Indian Association for the Cultivation of Science in Kolkata, and her work has been recognized with various awards and honors. She won the Swarn Jayanti Fellowship for the year 2015-2016, and she has been awarded the DBT Wellcome Trust Indian Alliance Senior Fellowship in 2020. She's also been selected for the CRSI Bronze Medal in 2020 and the Shanti Swarup Bhatnagar Prize in 2020. So, and today she is today she is going to speak on non-canonical nucleic acids for therapeutics and nanobiotechnology.
Yeah, good afternoon, everyone. At the outset, I would like to thank Dr. Kulkarni for the invitation, and I am honored to be a part of the Symposium series, and this is the first time I am giving a talk at JNCASR. And I would also like to thank you for your kind introduction. Today I am going to present a brief outline of our work that we have been doing at IACS. That we have been using classical organic transformations to selectively target nucleic acid secondary structures for therapeutic applications, and we are also looking into the possible applications in nanotechnology. So this is the brief outline of my talk. So first, let me give a brief outline about what are DNA secondary structures, and then I would like to talk about how nucleic acids or non-canonical nucleic acid secondary structures can synthesize their own ligands, which is also called as target-directed synthesis. So all of us, we know that DNA is double helical, where both the strands are held together by Watson Crick type of hydrogen bonding. But DNA can also adopt other higher order secondary structures. Particular guanine-rich DNA sequences can adopt secondary structures called chick quadruplexes, and they contain this coplanar arrangement of 4 guanines that are linked together by Hooke-Steen type hydrogen bonding. And the story of quadruplex started with a bang, of course not the Big Bang. It was about Dr. Ivar Bang, a doctor by a profession, became curious about nucleic acids. In 1910, he discovered that there is a 5' guanosine monophosphate, which is a guanosine nucleotide, can self-assemble in water to give a gelatinous material. So it was in 1910, and then decades later, that is in 1960, it was found out that this gel contains G-target as the basic building block. And subsequently, it was found out that these G-rich DNA sequences are present in the telomeres at the end of chromosome and promoter regions of cell genes. The complementary C-rich DNA sequences can also adopt conformations called IMs, and these are called these II motifs contain intercalated cytosine-cytosine base pairing due to hemiprotonation of one of the cytosines and acidic of both G and C-rich DNA sequences are present in human cells, and they in the regulation of oncogenes. So in our lab, we have developed different classes of ligands for selectively targeting DNA quadruplexes over the double helical DNA structures. So these are like peptidomimetics, heteroaromatic ring systems, and different classes of compounds. However, the rational design and synthesis of selective ligands is difficult and time-consuming because these structures like DNA quadruplexes and I motifs are highly dynamic structures. And moreover, many of the reported ligands show poor selectivity between different quadruplex structures. And in contrast to G quadruplexes, only a few ligands are known for targeting I motifs. Targeting I motifs is challenging due to the pH-dependent structural topologies. And we also wanted to explore the RNA secondary structures. So, in addition, many of these reported ligands are not suitable for advanced clinical trials, like they lack water solubility, they lack cell permeability, and they have been synthesized by using multisteps. So it is important to develop ligands that can be synthesized by using simple synthetic steps for biological studies. And as I have already mentioned, selectivity is an important issue. It is important to develop ligands that are not only selective for G quadruplexes over duplex DNA, but they should show selectivity between different quadruplex structures. And further, it is also important to track the localization of these ligands in the cellular systems. That is, we can design fluorescent ligands so that we can track their localization by using fluorescence spectroscopy or imaging. And finally, the most important question, that is whether quadruplex ligands really alter the transcription of a particular oncogene. So we wanted to gain insights into the mechanism of regulation of gene expression. So now I'm going to talk about what is target directed synthesis and how biological targets can synthesize their own selective ligands. In general, there are two approaches. One is kinetically controlled in situ cycloaddition. In this approach, that is, reactive fragments capable of binding the biological target can come into close proximity and then undergo an irreversible reaction to provide products that can strongly bind to the biological target. The other approach is thermodynamically controlled dynamic combinatorial chemistry. In this approach, simple building blocks assemble through reversible bond formation to generate a dynamic combinatorial library of interconvertible building blocks. In the presence of a biological target, the equilibrium of the system shifts towards those products that can strongly bind to the biological target. Thus, both these approaches combine synthesis and screening of ligands, and thus they provide unique platforms for the in situ synthesis of selective ligands for the biological targets. So now let us see how the first approach, that is the in situ cycloaddition, can be used to develop selective ligands for DNA quadruplexes and So alkyl azide cycloaddition is one of the very classic organic reactions, was developed by Wisden in the year 1900, around that time. So that is like cycloaddition between an alkyne and azide can give both 1,4 and 1,5-triazole regioisomers under thermal conditions. And metal-based catalysts have been developed to obtain either 1,4 or 1,5-triazole regioisomer. In target-directed synthesis, target's binding site is used to select two small organic reactants and then force them to react with each other in a regioselective manner. So this approach is also commonly known as in situ chemistry, which was developed by Sharpless and co-workers. So to begin with, we used G quadruplex to synthesize its own selective ligands. We have prepared a pool of alkyne and azide fragments, and then we have used the DNA quadruplex to synthesize its own triazole selective ligands. However, the lead identification was somehow difficult in the conventional solution phase synthesis. That is the HPLC chromatogram. We have observed a number of compounds, including starting materials like alkynes, azides, and the triazyl compounds. So to isolate and identify the lead compounds in an efficient manner, we have immobilized highlighted DNA targets on gold-coated magnetic nanoparticles. So we have taken G quadruplexes, they are complementary I motifs as the target templates. We have also taken control templates like single-stranded DNA and double helical DNA structures. And these were characterized by using circular dichroism, UV visible, and TAME imaging. So we have anticipated that DNA nanotemplates would accelerate the rate of reaction by providing a large surface area with more number of localized DNA templates. And moreover, DNA nanotemplates, as they contain gold-coated magnetic nanoparticles, they can be easily recovered from the reaction medium. So we have taken two different quadruplexes and their complementary I motifs. These are present in the promoter regions of c-MYC and BCL2 oncogenes. Both these genes play key regulatory roles in cancer progression. Therefore, regulation of these genes by targeting the DNA quadruplexes and I motifs could be a potential anti-cancer strategy. So we have taken a pool of alkyne and azide fragments in our approach. We have taken it in the presence of quadruplex nanotemplate. Then we have given sufficient reaction time, nearly 6 days. Then we have used magnetic decantation, that is, we have used an external magnet to isolate the DNA nanotemplate along with the newly formed products. And then the ligand-bound DNA template was heated to release the triazyl products, which were characterized by HPLC and mass. And this is the chemical library that we have used. We have taken 4 different alkynes and 17 different azides. The combination of these alkyne and azide fragments would provide at least 136 possible triazyl products, including 1,4 and 1,5 triazyl products. So then this is our approach using I motif. Similarly, the same fragment, this chemical library we have used for both G quadruplexes and also I motifs. Since I motif is stable under acidic condition, the reaction was carried out at pH, low pH, that is around 5.5. So the in situ cycloaddition carried out with the 2 different quadruplexes and I motifs generated a lead compound for each of these target. And these compounds are also identified as 1,4-triazyl regioisomers. As I have said that we have identified and isolated these compounds by using HPLC and characterized by using mass. And then we have also established the regiochemistry of these compounds by carrying out the individual reactions and HPLC analysis. And we have identified this, that the DNA nanotemplate can promote this metal-free cycloaddition in a highly regioselective manner. So then we have taken these 4 compounds and studied their binding interactions by using a number of assays. These are the assays that we routinely use in our lab. That is, we use first resonance energy transfer melting analysis to determine the stabilization potential of a ligand, and isothermal calorimetry, fluorescence spectroscopy, UV visible spectroscopy are used to determine the binding affinities of the ligand for the DNA targets. And we also study the mode of binding by using circular dichroism, and NMR and single molecule spectroscopy we study the ligand induced structural dynamics by using in collaboration with other groups. So here this is the biophysical studies summary. I am not going the details and only showing the results are quite consistent with our target directed synthesis, that is a triazyl lead shows selectivity for the DNA target that promotes its formation. For instance, the ligand 3BE obtained by the c-MYC I motif shows a high stabilization potential and a high binding affinity for the c-MYC I motif in comparison to other quadruplexes and I motifs that we have used in this study. So next we have taken these 4 ligands, and interestingly these 4 ligands are quite selective for the quadruplexes and I motifs. They show they do not interact with any of the control duplex DNA structures. So then we have evaluated these ligands in the biological system. Here also we do a number of assays. So first we have done studied the cytotoxicity of this ligand, since we have taken c-MYC and BCL2 quadruplexes. We have taken c-MYC and BCL2 overexpressing cell lines, like we have taken human cervical cancer cell line, which is a c-MYC overexpressing cell line. We have taken BCL2 overexpressing marmoset cell line. We have also taken a normal human kidney epithelial cell line. So most of these ligands are selectively toxic to the cancer cells and non-toxic to the normal cells. And the ligand for the c-MYC I motif could not inhibit the growth of either the cancer cells or the normal cells. So then we have also studied the localization of these ligands in the cancer cells, and I'm only showing one example, that is c-MYC quadruplex lead. So fluorescence microscopy images reveal that this ligand is cell membrane permeable and mostly localizes in the nuclei of live cells. We have also used immunocytochemistry using BG4 antibody. That is, BG4 is an antibody which is very specific for quadruplexes, and so it binds to the quadruplex and produces red dots, which indicates that formation of G quadruplex structures in the cellular system. And the ligand treated cells will show more number of red dots, so which indicates that thus the ligand binds to the quadruplex structure and produces a more number of quadruplex structures. That means the ligand can co-localize with BG4, as well as it can also induce the formation of G quadruplex structures in the cells. So next we have studied the effect of these ligands on the regulation of gene expression, as G quadruplexes and I motifs are considered as promising genetic switches to control gene expression. We have evaluated their effect on the transcriptional regulation of c-MYC and BCL2 genes, and these ligands, so we have done a number of assays that I have shown, like qRT-PCR, Western blot, promoter luciferase assays, and exon specific assays to establish that these ligands can downregulate or upregulate, can regulate gene expression by directly interacting to the promoter quadruplex or I motif structures. So thus we can therapeutically modulate cellular processes, and this strategy could be useful for the protein targets that are undruggable. So I would like to summarize the in situ cycloaddition. That is, in situ cycloaddition using DNA nanotemplates offers several advantages, like it reduces the time required for the conventional chemical synthesis and the biophysical screening. It enables efficient isolation and identification of lead compounds. It also prevents the wastage of expensive commercial DNA targets, and moreover, the lead compounds can selectively bind to the DNA quadruplexes and I motifs and show promising anti-cancer activities. Sure, I have shown that in situ alkyne and azide cycloaddition can be effectively used to develop selective ligands for DNA quadruplexes and I motifs, and recently we have shown that this method can also be used to develop selective ligands for the TAR RNA. So TAR RNA is an RNA secondary structure. It is found in the human immunodeficiency virus type 1, that is HIV-1 genome, and it can adopt a stable hairpin structure. So there is a TAR peptide that binds to the TAR RNA and promotes the viral replication. So therefore, the interaction of TAR and TAR is essential for the viral replication. So if we can target the TAR RNA by small molecules, then we can inhibit the TAR interactions, and thus we can inhibit the viral replication. So therefore, the small molecules that can bind to the TAR RNA and inhibit TAR interactions are considered as potential antiviral agents. So many aminoglycosides like antibiotics and heteroaromatic ring systems are known as TAR binding ligands. So in our cycloaddition, we have taken a target template. This is the TAR RNA. We have taken a control TAR RNA which does not contain this bulge region, and we have also taken the corresponding TAR DNA. So these two are control templates, and this is our target template. And due to the dynamic folding topology of the RNA secondary structures, the in situ cycloaddition could be a promising strategy to develop selective ligands for the RNA structures. So for this, we have developed a chemical library. Since it's RNA, we have developed some flexible compounds like thiazole-based polyamides, and we have taken some simple aromatic azides. So in this case, for TAR RNA, we have used biotin tagged TAR RNA, and for the isolation, we have used streptavidin magnetic base. So the process is similar, like we have taken a mixture of alkyne and azide fragments with the biotin tagged RNA, then leave it for some time, some days, and then we have used the streptavidin magnetic beads to isolate the TAR RNA along with the bound ligands or newly formed compounds, and then we have heated to release the triazole products. So this is our HPLC and mass analysis of the ligands. We could identify 3 different compounds, and like this compound was selective for the TAR RNA without the bulge, and this compound, this triamide that's containing 3 thiazole rings, was selective for the TAR DNA, and we obtained 2 different compounds for the TAR RNA. So since this was formed with the TAR RNA, TAR DNA, so we have taken this flexible ligand, was selective ligand for the TAR RNA, and they are formed in a mixture of 41:59
Hello, Dr. Das, can you hear me?
So this, yeah, hello?
Yeah, Dr. Das, you have 4 more minutes.
Yeah, so this flexible ligand binds to the TAR RNA with 1:1 stoichiometry and nanomolar binding affinity. So molecular modeling shows that this ligand can bind in the bulge region of the TAR RNA, and it can also inhibit TAR interactions. So this is thus we could develop a rapid method to develop TAR RNA ligands, and that can strongly bind to the TAR RNA and also inhibit TAR interactions. So I have shown that simple in situ cycloaddition can be used to develop selective ligands for quadruplexes, I motifs, and HIV TAR RNA. So we have also used like the dynamic imine exchange for targeting a DNA quadruplex. So in this case, we have used aldehyde and amine building blocks that reversibly react to generate imine-based dynamic combinatorial library. The quadruplex nanotemplate selects the best imine binders, which was then reduced to give the amine-based ligands. So here we have taken a carbazole aldehyde and 10 different amines that reversibly react to generate dynamic combinatorial library. And in the presence of quadruplex nano template, the system evolved to generate quadruplex selective imine binders, which was then reduced to keep the stable amines. So we could, by using HPLC analysis, we could identify a lead amine compound, and that shows very high selectivity for quadruplex over the duplex DNA, and moreover this can downregulate the c-Myc expression by directly targeting the its promoter quadruplex structure, and it is also toxic to the cancer cells and non-toxic to the normal cells. So this is the first example of a dynamic combinatorial chemistry using a DNA nanotemplate that selects its best binders from a dynamic library. So I have shown you that we can use both in situ cycloaddition and dynamic combinatorial chemistry to develop selective ligands for DNA quadruplexes, I motifs, and also we can use these methods to develop selective ligands for the RNA secondary structures. And these methods combine both synthesis and screening, and moreover, when we have used the DNA nanotemplate, we can recycle the DNA template, and that can be reused for subsequent reaction cycles. So I'll just give an overview of 42 minutes that G quadruplex DNA can also be used for constructing biomimetic materials, or we can say biomolecular devices, for instance, like ion transport systems. So when we talk about the ion transport systems, that is the insertion of a negatively charged DNA into the hydrophobic lipid membrane is energetically unfavorable. And moreover, the design of a DNA-based ion channel, like a selective DNA-based ion channel, is quite challenging. In the literature, DNA origami and double helical DNA-based ion channels have been reported, in which that DNA sequence sequences have been non-covalently modified with porphyrin through lipophilic linkers. Porphyrin stabilizes the DNA structures and the lipophilic chains promote the insertion of the DNA into the lipid bilayer. In our design principle, we have synthesized a lipophilic guanosine derivative that non-covalently binds and stabilizes the DNA quadruplex. So in a 3:1 stoichiometry. So this ligand binds and stabilizes the DNA quadruplex and also promotes its insertion in the lipid bilayer. And also we have shown that this by using voltage clamp experiments and other computational studies that this ligand quadruplex assembly can transport metal ions and selectively potassium ions across the biological membranes. And we have also used small molecule and quadruplex interactions to design DNA-based logic devices. In this system, we have taken a small molecule and DNA quadruplex and different enzymes, and this system could be programmed to design could be programmed to determine and identify non-zero square numbers up to 20 from different numbers. Like from 1 to 20, we can selectively determine and identify based on the fluorescence signature only the non-zero square numbers. So finally, I would like to give the future perspectives. That is, this in situ cycloaddition methods can be used for the rapid synthesis and high throughput screening of ligands, and this could be useful for new and challenging targets and for the targets whose structural details are yet unknown. And further, it can also be used for rational ligand design is difficult, and this method can be by new bioorthogonal reactions should be developed for generating more specific and complex ligands. And further, small molecule nucleic acid interactions should be explored for generating smart biomaterials that with applications in nanotechnology. In this slide, I have shown our group research activities. In addition to targeting nucleic acids that I have shown, we also worked on DNA-based ion transportation system and other biomolecular devices, and we used nucleic acid component like DNA and RNA bases to make hydrogels, ion channels, and other nanostructures. In addition, as I have been trained as an organic chemist, we also developed new methods to synthesize biologically active natural and non-natural compounds. So I would like to thank my research scholars for their hard work and cooperation, and over the years they could generate several drug-like candidates, interesting biomimetic systems, and also they have developed new organic transformations. I would like to thank funding agencies for financial support. I would like to thank you all for your kind attention. Thank you.
So we'll take one offline question and one online question.
So one question is, have you looked into off-target binding for other oncogenes harboring G quadruplexes in cellulo?
Actually, in cellular we cannot see, in the cellular system we cannot see that in which oncogene it is binding, but in vitro studies we have taken several different quadruplex forming sequences. I have shown here CMYC and BCL2, but we take like KRAS and HT-low like human telomeric quadruplex, and many other quadruplexes that we take and study in the lab to find out a probe that is selective for a particular quadruplex forming sequence, and then we use the cells that overexpress that particular quadruplex or particular oncogene.
Okay, the second question is, would like to know the possibility of false positive in the G4 immobilized in nanosurface strategy. It may be possible that click reaction is mediated by two neighboring G4 on the surface.
That is possible, but we have also done these reactions by using only G4s without nano support, and only thing is our identification techniques and isolation procedures are simple by using the gold-coated magnetic nanoparticles, and the gold-coated magnetic nanoparticles also give the similar circular dichroism, like by attaching the DNA into the gold-coated magnetic nanoparticles, there is no change in the structure of the DNA.
Understand this. So thank you very much for the talk, and So we'll move on to the next speaker, who is Professor Srikanth Sastry. He did his PhD in physics from Boston University and postdoctoral fellowships at the National Institute of Health, USA and Princeton University, USA. And he joined JNC in 1998. And his research interests have been in the areas of statistical mechanics, liquids and other soft condensed matter. And the issues that he is interested in are slow dynamics and routes to structural arrest, for example, glass transition, gelation and jamming, etc. He's received several recognitions, including the J.C. Bose National Research Fellowship, the Distinguished Alumnus Award of the Indian Institute of Technology, Bombay, the Shanti Swarup Bhatnagar Award, Sir C.V. Raman Young Scientist Award, Swarn Jayanti Fellowship. He is also a Fellow of the Indian Academy of Sciences, National Academy of Sciences and the Indian National Science Academy. And he's going to talk to us today about memory and loss of stability under stress, plasticity and mechanical behavior of amorphous solids.
Thank you, Raja, for that kind introduction, and I thank Professor Kulkarni and the organizers of this symposium for this opportunity to share with you something that, for the important part of this talk, is work I've been doing in the last 2 weeks. This is a somewhat rare occasion these days. It used to be that once upon a time I was always giving talks on what I did the previous couple of weeks, but that has become rarer. Okay, so as a result of this, my title effectively is going to change. I sort of put together a title which I thought will make it look familiar to the NSU colleagues who've been putting in hard work to organize the symposium, though of course the meaning of all those words are somewhat different. But I'm going to focus on only one part of this, and therefore we'll forget about memory. Okay, so here is the outline of what I am going to tell you about, right? So, so basically, I'm going to tell you. Okay, so I'm going to tell you a little bit about yielding the loss of stability under stress in my title of amorphous solids, a bit of background and why it's relevant. And this is something that we've been studying over the last few years through a particular procedure or protocol, which is to deform solids cyclically back and forth. And I'll sort of say more concretely all of this as I go along. And so I'll introduce what that means. And so then I'm going to summarize the description of yielding from a few years worth of computer simulations, both in my group and others, and that's going to sort of set the stage for coming up with a list of questions and phenomena that we should try to answer or to explain if one attempts to make a theoretical description. And then I'm going to tell you about a model that I've been working on, like I said, in the last 2 weeks, which remarkably explains most of what is observed. Okay, so in terms of the simulation work, this is a list of papers and collaborators. So there have been a couple of postdocs, P.K. Premkumar Leshankam and Himanshu Bhaumik, who's currently here, who worked on it, and a former student, Anshul Parmar, did a significant amount of this work. And okay, so now, so like I said, the sort of the overall scope of what I'm going to talk about is trying to explain how amorphous solids yield or fail. And why is that important? I mean, it doesn't need much of an explanation why it's important, because we use solids in a whole variety of ways in our technology and everyday life, and we sort of would like to know the limits of how far we can push them in our use before they break. Okay, so this is basically why, and here are a few examples. Now, a lot of the solid materials are crystalline, so there's a whole lot of
work that has been done in understanding how sort of mechanical response and failure in crystalline solids. But something that's not so well appreciated is a lot of materials that we both use in technology, industry, as well as that we need to understand are amorphous solids, or can be understood and thought about as amorphous solids. So one sort of example from technology is metallic glasses, which are multi-component alloys, which are very interesting for their properties, but they, for example, are used in making golf clubs and other sport equipment because of their desirable elastic properties, but they can break like glass, right? And that's what is shown here. But at the other extreme, I would like to point out that there's a lot of phenomena in geophysics which actually should be thought of as mechanical response of amorphous solids, right? And so here is one example. I don't know where it is. I probably took it off the net. But 2 years ago, when I was learning some of these things at a workshop in Santa Barbara, Southern California was having a lot of mudslides, and roads were closed and so on, like what is shown here. So a mudslide is a failure of a heap of, or a solid of mud which fails under whatever stresses it experiences, right? So this sort of belongs in the same category. Okay, now something to start off simple. Why, when I talk about amorphous solids or glasses, I said these are fundamentally different from crystalline solids. And what is the difference? The difference is the microscopic structure of glasses is disordered, right? So here is a schematic of a 2D version of silica, which is what window glass is made of. And you see that here the silicon and oxygen atoms in a crystalline silica are regularly arranged, whereas in a glass they're not regularly arranged. Okay. Now, of course, this is a detail that most of us maybe think we can live without, right? But it has very important and obvious consequences. One of them is a glass. When you say iron crystal, right, it really means one very specific thing in terms of structure, right? Whereas when you say silica glass, apart from the chemical diversity of composition, which is also a fact, structurally, silica glass does not mean one structure, right? It means a whole lot of different structures, and in fact, what exactly you're looking at depends on how that piece of glass got made, okay? And one way of thinking about it is illustrated here, where if I look at some property like the volume of a glass that is formed by cooling the molten glass or liquid, if I cool fast, I end up with a high volume or low density. If I cool slowly, I end up with low volume or high density. And this fast or slow cooling is referred to in common language as quenching or annealing, right? Slow cooling is annealing. So you give the system enough time to settle down into better and better configurations, okay? So this annealing is understood to be, in this context, an important factor, right? And it turns out this is one way of annealing, which is cooling down very slowly. But what I'm going to be talking about is one situation where temperature is not at all relevant, but annealing is done by the act of applying stress, okay, applying mechanical stress, okay. This is going to be a fundamental theme in what I'll talk about. Now, again, I already gave you sort of a few examples of what might constitute an amorphous solid, and here are a few more. Basically, metallic glasses or oxide glasses like window glass are one end of the spectrum of a lot of materials all of which, including things that you might not even think of as a solid, like a foam or a jello pudding or whatever. These are all in fact solids. In fact, I was listening to a talk by Gautam Menon, a colleague who sort of gives very nice popular talks, and he talked a lot about the ear. I hadn't thought about it, but the ear has every characteristic of a solid. It retains shape, you can do things to it, and it will come back to what it was originally. So, there's sort of, if you are imaginative, you can think about a lot of examples of what constitutes a solid, and a lot of these unusual examples will turn out to be amorphous solids, okay? Okay, so then at the other extreme, like mudslides, these are what are called granular matter, right? So solids that are made up of big grains of particles. So there's a whole range. And I already said a little bit about it, so I won't spend more time. There are also phenomena like avalanches, which incidentally came up in Milan Sanyal's talk, and in the context of, disordered magnets. But there are also real avalanches out in the Alps and other place in Himalayas. So these are all phenomena which have, as a fundamental physics question, the understanding of the mechanical response and loss of stability of amorphous solids. Okay, that's sort of the general picture. And so I'm going to now first talk about what we have been doing using computer simulations, right? And so this is basically an illustration of exactly what we have been doing, which is we've taken a system of particles in a simulation volume, and we shear it back and forth, okay? And now I'll try to avoid them, but I'm going to mention a few words which in case I don't explain, I want to give you a quick translation table. So when I talk about glasses, what I'm really going to be talking about is local energy minimum structures of these disordered packings of particles, okay, like what is shown here. And then we have by and large been looking at what is called athermal quasi-static shearing of these amorphous solids. So athermal means like literally zero temperature. So we simulate these systems as if they don't have finite temperature and kinetic energy. And this is a limit case but it's a limit case that describes well the behavior of very cold glasses, okay? But in what we do, we are going to be looking strictly at the athermal limit, which means that at any given instant, the structure that I'm going to be looking at is going to be a local energy minimum, okay? And quasi-static means, we've learned this in thermodynamics. When you say a quasi-static change, it means that you do things so slowly that at any instant I can think of the system as being in equilibrium, right? So all internal dynamical processes are faster than how fast you're changing the external conditions. And this is sort of what we're going to be thinking about. And shear is that, right? It's a volume preserving deformation of the system. And so here is a cartoon taken from Google or Wikipedia more precisely. And when I talk about shear strain, it's basically the ratio of how much I displace a solid over a length. So if the top plane is moved by delta x, and if the distance between the bottom and the top plate is L, delta x by L is the shear strain, and that's a unitless number. And if I'm doing so by applying a force over the top surface, the force per unit area is called shear stress, okay? And this is all we're going to need to know in terms of technical terminology. And cyclic shear is shearing back and forth, okay? Now, this leads to two types of responses. One is elastic response, which I won't explain. This is probably something that everybody understands. But a second and important type of response that I'm going to be focused on is plastic response. And this is sort of illustrated here, right, in a cartoon of a bubble raft which is being sheared. And if you focus on the central area, what you'll see is that the structure keeps changing gradually, but suddenly there's a point at which it flips, right? So this is now, and the important thing, as I'll illustrate in the next slide, is when you have a plastic structural change, when you remove the external force, that change does not go away. Okay, that's the definition of plasticity. And okay, we're going to be typically looking at configurations when I come back after a full cycle at what are called stroboscopic configurations. Okay, so here is sort of a schematic landscape view of what you might be doing. So imagine that the energy minimum that your system is sitting in is represented by this sort of two-dimensional cartoon. You're starting out here, and as you apply shear, this landscape is changing, and yeah, what happens? Yeah, and you know, at some point you make the minimum that you're sitting in unstable, and so you flip to this other minimum. But when the strain comes back to zero, you're still stable at this other minimum. That's what plasticity means. When you remove the external force, there is a change in the structure that does not change back, right? And so what we want to understand is, if we do this repeatedly, what's going to happen to the properties of the glasses that we study. So here I show one set of important results that we found. What we found is, if I start by looking at a low energy glass, which we call a well annealed glass, or a high energy glass, and we apply a number of cycles of shear, cyclic shear, what we find is that from one cycle to the other, typically the energy keeps going down if the amplitude of the cycles is small. Okay, and so this is like the smallest amplitude, the next the slightly larger, slightly larger, slightly larger amplitude. So I see two things. One is the energy to which I go keeps coming down, and it takes longer and longer to do so. Okay, but then there is a change in behavior if I go to sufficiently large amplitudes, where, you know, whether the energy goes down or goes up depends on where I'm starting from, and I'm going to a common energy. Okay, so here if you look at the blue curve here and here, starting at two different energies, I did not go to a common energy, right? Or it's more clear if you look at the green and the green, where they have saturated. This is at one particular shear amplitude, starting at a high energy and a low energy, and they go to different final states. Whereas for sufficiently large amplitudes, they always go to a common final state. Okay, and so there is a change in behavior, and what turns out to be the case is that if you look at the strain amplitude at which this change in behavior happens, and look at sort of how long it took to reach the final state, that time scale appears to diverge. Okay, so there is some kind of a dynamical phase transition, and this dynamical phase transition is the yielding transition. And so this can be seen by looking at sort of the long time values of the energies as a function of the strain amplitude. You see that, well, let's not worry about this other curve. If I start with this poorly annealed glass, the energy keeps going down as I increase the amplitude of strain, and then it starts to go up. Okay, and if you look at sort of what is happening over the cycles, this is what you see for the lower branch. The energy through the cycles keeps going back and forth and down, 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 until it reaches some final value. Whereas in the other case, yeah, what? 4 minutes? You're kidding? No, that cannot be done. Okay, so when this yielding transition happens, I'll take a few more, but not too many more. Okay, when this yielding transition happens, you also have other curious phenomena, such as shear banding. And the one point that I want to emphasize is when that shear banding happens, you have basically this red zone where all the plasticity is, and the blue zone where the system is not plastic, and the energies in the blue zones continue to decrease even at larger amplitudes, whereas the energy in the red zone jumps up to very high values. Okay, so there's a bifurcation that takes place. Okay, now this is the last simulation result before I take 5 minutes to explain the recent work. So basically, you saw that already, depending on whether I started with a well annealed glass or a poorly annealed glass, the behavior is at least quantitatively different, right? So one can ask the question, if I start with a wide range of annealing of the glasses initially, what happens? And something very dramatic happens. So this is now starting with a whole big range of initial energies and shearing them at different amplitudes. What you see, at least visually it's very clear, something is very different above this line and below this line, right? Above this line, wherever I start, I keep converging to some threshold energy value before I yield. Whereas if I am below this line, nothing happens till I hit a point of instability and yielding happens, okay? So this is now the set of all, I'll skip this. This is a set of all observations, right? I have a discontinuous strand, and with cyclic shear, I have both annealing and what's called rejuvenation, which is basically increasing the energy by applying mechanical stress, and the existence of a threshold energy, coexistence of annealing and rejuvenation, and slowdown of relaxation near the yielding transition. Okay, now this part I'm going to skip, but it's important. Let me just come to the model that I work with. So I basically, what I do is, again, skipping a lot of the physical insight needs to be explained. I can't. It's okay. Yeah. Okay. So the basic point is, you have this qualitative picture of energy minima which become unstable and go to other energy minima. But you have to really come up with a careful construction of the distribution of the energies of the minima that you have and how stable they are in terms of how far I can push before they become unstable, and rules for what state they go into when they become unstable. And one thing that I've emphasized is what we see is that the final outcome when a given minimum becomes unstable is that it can either go to lower energies under some circumstances or higher energies. And the model needs to have that feature built in. And so this is sort of, with that general explanation, this is the landscape that I work with, where, actually this is the density of states of minima, which is basically a Gaussian density of states. This is energy going to negative values from 0, which is the maximum value that I consider. And what is shown here is how the energy of any of the minima changes as I change the strain in the system. And when for a given minimum I reach, like let me show here, if I take this green curve, when I reach this cusp, it becomes unstable and I have to make a transition to some other minimum. And the condition that I use is a very simple one, which is at that value of the strain, the transition has to be to another minimum which has lower strain, okay? And that in this picture again can be either the blue guy or the red guy, but if I go trace back to where their energies were when the strain was 0, it turns out they can either be higher or lower. And this is a key feature of the model. And then you say, okay, let's see what happens, what happens when you work with this model and apply cyclic shear. And basically, I'm going to quickly go through 3 slides of comparing results. This is what we found in simulations. This is what the model finds, okay? It's qualitatively, basically, everything that we find in simulations. This is now the energy as a function of strain, one particular case from the previous slide, which illustrates something more, which is even though this is now an average over a large number of samples, And even though the energy does this business of going down and then jumping up, if you look only at the cases where the energy stayed below a certain minimum, a certain value, and cases where it went above, you find that it's actually not even continuous at the level that you see with the black points, but it's actually two populations. In this transformation zone, if you will, you have cases which continue to anneal when I increase the strain amplitude, and there are cases which yield, and it basically is a first order transition, okay? And this is now to be compared, the blue and the red points here are to be compared with these red points and these black points, which is, again, what you see in simulations. This is, I won't explain this relaxation curve, but this is basically the corresponding curves to what I showed you earlier of how the energy changes from one cycle to the other. This is exactly that, from which I can extract a relaxation time. And you see indeed that these relaxation times are changing by orders of magnitude as I approach the yielding transition, okay? Whether it actually diverges here or not is something that's under further investigation, and this is to be compared with the lower side of this curve, okay? Basically you see what you see in simulations. Now the next question is, why does this happen? You know, I just told you I have this crazy landscape and everything comes out, right? Now, so why does it happen? Okay. Now, the key question is the existence of a threshold across which the behavior changes. Okay, where does that energy come from? So in order to understand that, I do a simple sort of computation, if you will, where I say, for a given amplitude of strain, let me look at a whole range of initial energies, and I ask, where does it end up after one cycle? Where does the system end up after one cycle? So that I plot on the y-axis. So this is like a color map of the histogram. So what you find is, of course, as you expect, at very low energies, the system is always stable, so it doesn't go anywhere. It stays where it was. So you find this x equal to y line up to some threshold, right? Beyond that threshold, there's something very surprising that happens. So what you see here is data that says once you're in this second regime where you are making transitions through a cycle, it really doesn't matter what your energy is. The probability distribution for where you end up with is basically the same. Okay, so this is a very unusual kind of map, but the other important thing is this horizontal line is now the maximum energy that is stable at a given strain amplitude, and that maximum energy for small amplitudes is sort of bang in the middle of that spectrum, right? So in other words, if you're sitting at the threshold energy, or if you go a little bit above, you can make transitions to either higher energies or lower energies. And this picture changes as I increase the amplitude of strain till I reach a point, let's look at this, where I either am stable, so when I start with an initial energy here, I go to the same final energy, or if I exceed that initial energy, the threshold of stability, then I don't come back to any lower states. I only make a jump to higher energy states, right? So this is much more clear in the final panel. So there's basically the emergence of a gap between allowed energies after the transition, after a cycle of shear, and the emergence of this gap corresponds to the yielding transition. And but when that transition happens, it's very clear that I jump to this one common energy, right? So this is what you see. Okay, sorry, there's some, yeah. So this is what you see here. When the transition happens, it's a discontinuous jump and I go to the same energy. And that's very clearly seen from the behavior in a single cycle. Okay, I'm done. So those color maps are very heavy, so it takes time to get them to load. I'm sorry. Anyway, so there are basically 3 points of summary. One is I showed you a bunch of data from computer simulations, like I said, over the years, telling us what happens when I have yielding under cyclic shear. There are a number of features that needed explanation, and all these features are captured by a landscape model, and this is a part that I didn't go through. This model is supposed to represent what happens in a small mesoscale block of the system, and this is important for 2 reasons. One is it is not expected to capture the behavior on large length scales. But the other side of this story is there is a lot of effort going on currently to build models where you can, like if you look at sort of car makers, they use routinely simulations to generate the dislocation structure and dynamics of metals in order to design their car bodies and so on. There is no corresponding tool for amorphous solids. And in order to build that, you need to have a good model of what happens in one mesoscale block, let's say of 100 atoms, and then you can build a continuum-like theory. And so the fact that this model works so well is very encouraging for building that macro scale modeling of amorphous solids, which is something that we are trying to do. Yeah. Okay. Thank you.
Some basic questions. See, you talked about annealing via strain. Whether you like it or not, you cannot forgo thermal components, right?
Excellent question. So, in fact, I talked about the athermal behavior of this model system because that's what we've been doing in simulations, atomistic simulations. But one of the primary goals of why one wants to do something like this is you want to include thermal effects, which are very important. But in all the so-called mixed models, meso models, that's not built to be able to address thermal effects in any meaningful way. Whereas because the model that I'm describing is a landscape model, so it has energy in it. It has activation energies in it. Therefore, thermal effects can be studied, can be incorporated and studied. That's very much one of the desiderata in this.
And the landscape with straining is quite rich.
Well, it's not really. It looks nice and complicated, but it incorporates in a sort of an organized way a few key features the landscape needs to have.
No, if one were to compare with the pure thermal landscape, via straining is quite rich, is what I'm saying. Energy versus strain landscape, what he showed.
No, actually, no. I mean, that's what I said. It sort of looks that way, but basically, what that landscape incorporates are a few points. One is the stability range of a given configuration is bigger the lower the energy is. Very, very reasonable statement, right? And the number of minima I have per unit of strain of a given energy becomes more as I go to higher energies, right? And the third point I already mentioned, which is that it builds in the possibility that I can make transitions both to lower minimum energy and higher minimum energy structures when given minimum becomes unstable. So this is just something that I cooked up to incorporate all of these features. So any candidate landscape needs to basically obey these 3 rules, and then it'll be fine.
Thank you, Professor Srikanth, and we are very sorry that we can't take any more questions because we are running really late. And we conclude this session, and I will give a short vote of thanks. But let's first thank Professor Srikanth for the talk.
Thank you.
And on behalf of the center, I would like to thank all our adjunct faculty members, honorary faculty members and mentors for being with us on the special occasion of the annual faculty meeting and the in-house symposium. I thank Professor C.N.R. Rao for his continued encouragement, support and guidance. I also thank our President, Professor G.U. Kulkarni, for his intense and meticulous commitment to the activities of JNCASR at all levels. And I thank all the speakers of the morning session. I thank all my faculty colleagues, in particular Professor Hemalatha Balaram, Professor Umesh Wagmare, Professor Chandrabas Narayana, Professor Anuranjan Anand, Professor Shiba Basu, and Professor James Chalaya for the organization of this meeting. Our administrative officer Jaideep Deb and his team have also played a critical role in this event. Finally, I would like to thank our audio video team at the center, Professor Subir Das and his CompLab team, and the website designer and our student volunteers. Thank you very much.
Okay, I'm very glad to see some bright eyes and smiling faces. This is what I wanted to see in this auditorium today. It's my pleasure to welcome all the participants to in-house symposia IHS 2020, which is being organized by Neuroscience Unit with Shiba and James putting in a lot of hard work and me pitching in where possible with both of them. Professor Kulkarni suggested about 6 to 7 weeks ago that we begin our center level academic events, and it's a good idea. As you know, there are several of them: endowment lectures, many special talks, and this particular event, annual faculty meeting and in-house symposia. And he thought it's appropriate to begin with this one because we haven't been meeting for a long time to talk about center level academic activities. Now, at that time point, I shared with him our memories of the very first IHS AFM, which took place on this campus. I think the year was 2000, and this hall was newly built, and Dr. Radha Narasimha and myself had organized that. Units were very small. All of us, all the faculty members, could fit on one small table, and if an additional one joined, we could pull a chair and sit next to it. That was our strength. Faculty student strength was a little more than that, which is present here now, and it was not a particular unit, but people from across the units. That was the day when we put that night, whatever the day was, these curtains, and I had to make sure that for my biology colleagues, light doesn't come in because they were going to show bioimaging pictures. Today is just the reverse. We have opened it up, but I'm finding it much better this way. If you look around, it looks like as if you are sitting in a fancy resort and having this meeting almost in a tree house or something like that. So these are the memories. After that, we have had many meetings every year, and there'll be stories and recollections that people would have attached to them in one or the other way for one or the other reason. This meeting, IHS 2020, is unlike other meetings for reasons all of you know. There's a bit of ban on gatherings in large numbers. If you sneeze, nobody says bless you nowadays. To me personally, many of the things which are happening now so bizarre, so surreal, that even perhaps the strangers of the fiction beats that. But on the second thought, I think it's much like any other year, and I say that for the following reasons. The enthusiastic participation I have seen from students and faculty members in making posters in an entirely new format, which we weren't used to, by instructions coming pretty much on daily basis from James, others, and organizing team. Fixing snags in those, having them uploaded, interacting with colleagues, etc., is really something praiseworthy. The way my faculty colleagues came forward, accepted the invitations to give talks, indeed is remarkable. And this is, I think, a very strong testimony to the fact that, to the zeal of doing and sharing science. And this is one of the occasions we get to share across units, across specialities, which has its own charm, is not dimmed or coveted by the events which have happened, which have pushed us in that situation for almost whole of this year. So I'm very excited to invite all the speakers and poster presenters. We devised a format where posters can begin pretty much on Monday and are with us a whole week. We'll have them on certainly till tomorrow's evening, and if necessary even on Saturday, so that you can informally keep on talking about it. There will not be any formal interactions with them. So all these people are invited for this. This in the next 36 hours, not continuously, you'll get enough breaks. Joydeep is taking care of us, feeding us, and enough sleep. There are going to be about 30 talks and 90 plus posters, as I have indicated. There are going to be degree award ceremonies, and there are going to be student posters and talk awards. President has been very generous this time, and in terms of number of awards and the prize attached. So there are a whole range of activities that we'll get to enjoy in the coming 1.5 day or so. This is what I have to say to flag this off. Please join me in welcoming Divya Chalapathy, who along with a small team of moderators will be chairing the next session, which begins pretty much now any moment. Thank you.
Thank you, Professor Anand, for the kind introduction. I welcome all of you to the first session of the In-House Symposium 2020 here at JNCASR. Our first speaker is going to be Dr. Premkumar Senguttuvan, who is a faculty at the New Chemistry Unit and ICMS here at JNC. His group works on different areas of electrochemical energy transfer in devices and supercapacitors for portable electronics. Also, they synthesize novel electrode materials and try to understand the redox mechanisms. Today, Dr. Prem will be talking about towards high energy density sodium ion phosphate cathodes, the interplay between structure, sodium ion dynamics, and redox centers.
Thank our president and the organizers for this great opportunity. And today I'm going to talk about one of the main thematic research from our group, that is about exploring high energy density cathodes for sodium ion batteries. And I want to particularly stress about the importance of structure, sodium ion dynamics, and redox centers to develop these materials. So the battery science is not something to the modern community. And the first kind of battery was built about 1800 by Alexandra Volta. And today we have lithium ion, even more new technologies are in the promising road. And if you look at the energy density for lead acid, which is developed in 1900s, about 40 watt-hour per kg, and today we are having about 300 plus watt-hour per kg. Obviously, the technological development has originated from the materials advances. And last year, there was something special moment for battery scientists around the world. The Nobel Prize for 2019 Chemistry Prize was awarded to Professor Goodenough, Professor Whittingham, and Professor Akira for the development of lithium-ion technology. And to understand how it happened, as well as going forward the talk, I keep one slide about a design aspect of a battery. So this schematic represents the energy diagram of any battery technology. You have an energy levels of electrolyte, HOMO and LUMO, and the cathode chemical potential and anode chemical potential are placed well inside. If not, you will have a parasitic reaction. So the open circuit voltage is determined by how far you place these materials in terms of the chemical potential, and the capacity number you derive from Faraday's first law. So simply you can increase the number of electrons in the electrochemical reaction to increase the capacity, or you choose a lightweight molecule material to improve the capacity. And the energy density of the system is determined by either the function of voltage and capacity. So to improve the energy density of the system, either you push the voltage or the capacity, or both if possible. Okay, So switching back again to the lithium story, obviously it's one of the best technology from the battery community, and recently the prices for the lithium pack is falling drastically. As of now we are speaking, the pack is about $175 per kilowatt hour. Something magic number. In fact, down the road 10 years, the projection shows about $62 per kilowatt hour. So it's good news. So then why we are talking about some future technologies? To define that, let's look at another perspective of the battery application. As of today, we have a huge market for lithium in the portable electronics market. Obviously, the serious contender for the electric vehicle application. However, if you go for a larger storage application for grid or even a larger megawatt or gigawatt hour level application, you require a big technology or maybe a large amount of material. So the cost comes into the play, the material availabilities come to the play. So if you look at the relative abundance of the materials in the earth crust, for instance, lithium and cobalt, which is the major materials used in the lithium battery, they are very scarce. And if you look at, let's say, sodium or calcium, the future the materials for the batteries are really abundant. So we have to look for materials to build a sustainable battery technology. Obviously, sodium is the primary choice. The reason is not only the cost and the availability, is about its operation principle is just like lithium ion, okay, due to its chemical character similarity. So the battery have two electrodes, positive and negative electrode, which are separated by electrolyte containing sodium ion electrolyte. So this sodium ion, it will move in between these two electrodes according to a charge-discharge processes. And recently, there are enormous amount of academic activity to develop materials for this battery application, sodium battery application. In recent times, even it's superseding the lithium ion field actually. And thanks to that, we are able to make large variety of materials. And however, you see that the energy density of lithium batteries are here, and our materials are still, a little bit behind that because of the thermodynamic reasons. And we have to look for the materials design challenge, how to improve it. And I particularly want to focus on the cathode because this is the main limiting factor to build high energy technology. Obviously, there are large variety of materials being developed last 10 years, and two main class of materials are in serious pursuit for the practical application. One is this layered oxide, analogous to what is being used in the practical lithium batteries, lithium cobalt oxide. So the good advantage of this material is about 120 to 200 milliampere per gram capacity you can give. However, if you see the chart, the most of the materials operates below or about 3 volt. So this is not really good for a battery, high voltage battery. Then it undergoes multiple phase transition during cycling, which will degrade the capacity over the time, and then it has suffering from air instability issues, a major problem for battery manufacturers. On the other hand, you have polyanionic material, meaning you have some phosphate or sulfate units in the material, so which gives a high chemical stability, structural stability and thermal stability, and intercalation voltage also high because of the inductive effect. However, it has a moderate capacity, storage capacity compared to the layered oxide, and little limited rate performance. So how do we enhance this? Our group particularly works on this kind of Nasicon sodium superionic conductor, this type of material. In fact, it was discovered by Professor Goodenough in 1976, well before he discovered lithium cobaltate or other material. So the beauty of this material is you can tune the composition with the first row and second row transition metals, and the sodium can be between 0 to 4. So it have a high stabilities and then high sodium ion mobility. So this value is at room temperature, so you get high rate performance, and you can achieve high theoretical capacity about 220 milliampere per gram. However, at present we are suffering with 100 milliampere per gram. Okay, the structural details are given here. So you have basically a building block, what we call it as a lantern unit, which stacked along C-axis. And there are two sodium sites, sodium 1 given in the yellow ball, and sodium 2 represented in the green ball. And during the battery operation, the sodium diffuses from one side to other side through what we call as a bottleneck. I will give more details about that in the upcoming slides. So this slide summarizes the major research activity occurred in the field for last 7-8 years. So what scientists have done so far is to choose a single transition metal compounds, let's say vanadium, chromium or iron. So vanadium is kind of appealing because you have high voltage, a moderate capacity, chromium, high voltage is good, but limited capacity and toxic, maybe not suitable for practical application. Iron could be very interesting. However, the low voltage operation is another major issue to build high voltage systems. Now, if you can also build systems with a mixed transition metal, so you can have two different redox couple for this vanadium manganese or vanadium chromium or manganese manganese. So compared to the top three, the bottom three have a slightly higher operation voltage, so you get a slight improvement in the energy density. That's good news. However, the reality is we are still in the 2 electron transfer. That means you are about 100 milliampere per gram only we can achieve. So this is not really improving. So when I joined JNC, with my student Mr. Subham, we started to look at how to improve the design aspect. So we want to make some sodium-rich compounds with the different allovalent and isovalent cation substitution. Initially, we are struggling with a lot of this decomposition, not able to make the material with quantity. So two major systems come into the play during this journey. One with again with vanadium manganese and vanadium magnesium. I will give more details about this first system because it was somewhat very interesting to look and then push forward. So the approach is very simple. You want to substitute manganese in this vanadium system systematically. You have to look at what is happening to the structure, what is happening to the electrochemical properties. And we choose specifically this solid state synthesis method to make a large particles in the synthesis. We've avoided carbon coating or nanosizing because those factors definitely will enhance the performance, but then we may overlook the impact of manganese substitution. So we avoided in our approach. So these are the major results. So this XRD pattern is given for this system as a function of manganese substitution. For all the pattern we can index as a single phase except y equal to 0.5. I will give more detail on the next slide. And if you look at the SEM analysis, we create a micron size particle. This is really good to get high dab density for battery application. So let's see how it behaves in the battery. As I said, that y equal to 0.5 something we have a peculiar behavior. You can see is a phase decomposition occurring, and in fact we conducted an temperature dependent XRD. We still see even at high temperature the phase immiscibility gap exists. In fact, Professor Sapan computed this phase stability with DFT. We see an overshoot in the composition, in corroborating our experimental observation also. So these are the main results we gathered from Rietveld refinements here. So as you increase the manganese substitution, your A parameter increases, C parameter decreases. A increases, you can understand the Mn2 plus is slightly higher ionic radii compared to V3 plus. As additional, you have sodium 2 filling, so you have a expansion along A axis. For C axis decrease, you start to fill more amount of sodium in the Na1 side. So the electrostatic repulsion between these oxygen layers becomes less or reduced. So you create a lesser C axis for the material. And Zanes proved there is no change in the oxidation states of vanadium and manganese in both of this material, irrespective of the amount of manganese substitution. Okay, so in terms of electrochemistry, so this is a busy curve. Let me walk through very carefully. So the baseline compound is given in the black curve. This test results is like you apply a constant current to a battery and you monitor the voltage changes and as well as the number of sodium you take out from the system. It's like a Coulombic titration. So for the baseline compound, you are almost taking about 1.7 mole of sodium, which is in line with your literature values. And we see this plateau responsible for vanadium 3 plus 4 plus operation. And when you increase the manganese content, there are two notable observations. One, the capacity start to decrease, it goes, and still one plateau. And if you further increase y equal to 0.75 and 1, the capacity start to increase on this way, and you start to see another redox feature appearing at high voltage, manganese 3 plus to 2 plus redox couple. You can also see all of these changes in the DQDB curve, and we have done a comprehensive analysis on with EXAFS technique to probe what are all the elements are active, redox active. What we found is for the low manganese content up to 0.5, we don't see the participation of manganese. It's just silent. Okay. Whereas if you look at the manganese-rich composition, 0.5 or 1, the redox participation of manganese 3 plus 2 plus is proven by our exhaust analysis, which I will explain with the DFT results also later. Then, obviously, as I said, I want to get more capacity. So, the obvious, the way to do that is to open up the upper cutoff voltage. So, you remove more number of sodium. So, for the manganese lean composition, you have additional redox couple. So, you have little additional capacity and the curves are very symmetric. So, you can say this process is very reversible. Good. Now, if you look at the manganese-rich composition, you still see kind of additional capacity, which also now the manganese 4 plus 3 plus couple are active. This I will prove it by examples in the later slide. And however, on the discharge process, the pulse does not come back in the exact shape. So, meaning there is something going on in the structure. We have to probe with a complementary technique. So, we have done studies of XRD and exhaust of all the composition, but due to the time constraint, I will pick up this 0.75 material, which is very interesting for application point of view. So, we have collected the XRD in 2 voltage window. For the low voltage window, what we found, the XRD pattern of the pristine and the cycled one is almost the same, meaning there is no structural transformation, no degradation, the process is highly reversible. Now, when I do the same thing for the high voltage region, this pattern, although looks very reminiscent, but in terms of peak posture is not the same, meaning your cell parameter is different. That means some irreversible transformation occurs. It's an indication we got from this study. Going forward, we also probed the participant redox couple. The top panel shows the vanadium exhaust, the bottom panel shows the manganese exhaust. So James and exhaust, sorry. So the oxidation of vanadium to 3 plus to 4 plus we clearly see on the high voltage, even the plus 5 also appearance in the high voltage region. Same for the manganese. What is very interesting is if you look at this Fourier transform spectra in the low voltage region, the black and blue curve, which is representing the pristine material and the cycled electrode, nearly superimposes for the low voltage region here. So, meaning you are recovering the electrode even in the bulk scale, which is proven in the XRD, even in the local scale, no problem. It's good. Now, if you look at the same spectra in the high voltage region, you see a losses here in terms of amplitude or even the position. So, there might be some losses in the second or third coordination cell. At the time, we have some qualitative analysis only, which is due to some loss of sodium 1 and sodium ions which triggers the structural collapse. Now, we go forward to test this for a kind of practical application. So, what we have to do is we have to test for different cycling rate. As you increase the rate, you are meaning that you are taking out the capacity faster, or restoring that energy faster. So, for the baseline compound, the decline is very minimal. Whereas the other end member, there was a rapid drop when you have a high current applied. And the y equal to 0.75 copper was something surprising. It was not declining that much faster compared to the y equal to 1, but some decline is there. So, how do I understand this material? I must remind you again, we did all of this experiment with this bulk particle, no special electronic coating or a nanosizing is there. And there are two-fold reasons for what we propose. One is this electronic structure for this material. The vanadium and manganese redox centers are nearly superimposed, even superseding the activity of the other materials, and the local crystal structure also have an optimal bottleneck, that is when you hop sodium 1 to sodium side. So, due to these two reasons, we have better rate capability. In fact, this material performance is compared to the existing some polyanic material even better than the oxide material is being pursued in the industries also. Okay, performance-wise, we still have a problem for these manganese-rich compounds because mainly the Jantler activity of this. So, recently we came with another approach. You substitute some amount of inactive cations in the place of manganese. You get a very cycling stable performance. During this process, we naturally create some sodium vacancies in the material, so we get a even higher rate performance also. However, we never able to solve the high voltage degradation so far. It still exists. So, how do we understand? In fact, other research groups also having the same problem. So, the major issue is The moment you activate this vanadium redox couple on higher voltage, the sodium comes out. So you can view this material as a columns of this octahedra. The moment you remove this, structure start to collapse. So at present we have a rough idea about average structure. We don't know what is the exact structure in terms of local distortion and how these bottlenecks are arranged. This we have to probe. So for that, what we have done recently, again, we made that manganese part as silent. We want to focus only on the properties with respect to vanadium redox activity. So again, we are still having the same problem, but now we have an advantage. We can pinpoint where the problem occurs using the inapparent XRD and solid state NMR and DFT. The calculations are underway, so we'll get some new features soon. Okay, to sum it, I want to give two main messages. I want to first, I hope that you have convinced that the substitution of the transition metals plays an important role to develop the high energy material. And secondly, the open question is the interplay between the structure and the redox activity and mobility going to play to design new material in this direction. And finally, I want to show if we can hypothetically make a material with a high capacity, we can slightly push the limits closer to the practical lithium system, not beating the system, but closer to the practical systems. I would like to thank my students Subham and Nabhuti for carrying out these enormous experiments, and then Professor Swapan for DFT calculation, for Professor Clement for sodium NMR, and Gwen for structural analysis, and finally funding from DST and Petra for synchrotron use. Thank you. I'm happy to take questions.
This talk. Is there anyone who would like to ask a question here? Sir, I have a doubt.
Yeah.
Sir, in the slide number 14. Sir, over there the plateaus are changing their position, and also there's a shift in the hysteresis loop, right?
Yes, I haven't mentioned about the hysteresis. So what we found at some particular composition, this hysteresis is lower. What we believe is the mobility becomes very facile, or maybe the kinetics become much better. That's one reason. Okay. And the why it is merging is like in the crystalline material, particularly batteries. The moment you start to substitute some other elements, your the crystal field comes into the play, so it will tune your redox potential. How it goes, it depends upon the material or the substituent. So I can, but this is an effect from the crystalline field.
Okay. Sir, there are a few questions from the online attendees. One question by Professor Maji is, what is the advantage taking two or more redox active transition metals in stability, cyclability, energy storage capacitance? And what about copper in the place of magnesium? Copper 2 in the place of magnesium?
Yeah, so I forgot to mention, so we also did with copper 2+, actually we screened down pretty much in the first row transition metal, nothing was working due to the thermodynamics. So the substitution, as far as my understanding, it is not going in the way with respect to the ionic size, because more or less all the ions have similar size, so one would expect everything will work. However, in our experience, except the manganese 2+ in the first row transition metal, nothing was working. We don't know the exact origin why it occurs. However, we believe some thermodynamic reason may not be that compatible. And to attain the high energy density, so what one would need to have is a high number of sodium in the structure, as well as high participation of redox activity. So meaning, you say per transition metal, if you have two redox couple, that's what we are trying to achieve here. So if I have activate this vanadium 5+, you get 2 electrons per transition metal, and manganese all the way to manganese 4, 2 redox electron per transition metal, I get 4 electron. That means I can remove effectively 4 sodium from the structure. That means higher capacity. That's what I want to achieve, but it is far from the
so there's one last question by Professor Sundareshan.
Yeah.
In terms of redox properties, manganese is not as good because of ion-teller distortion. What about cobalt instead?
So I agree with him, because this is the main reason even spinel has been overlooked in lithium battery. Ion-teller, you can certain degree you can stabilize with this inactive substitution, what I was telling in the last couple of slides. But cobalt we tried, I mean in the system, it was not solubilizing, it is not, it's coming out as a phase segregation. Even we have little solubility, then it is not acting in this particular system, but there are, let's say, sodium cobaltate, other materials are there which is having, not high voltage in the sodium battery, that's the main problem in the layered oxide, but of course that can be also looked into.
Sure, okay. Okay, thank you sir, thank you for this wonderful talk. So the next set of talks are from students from different departments in JNCASR. Our first speaker here is Jyotsna Karan. She is a student of Professor Ranga Uday Kumar in MBGU. She is going to speak on like mother, like child, transmission of an HIV variant.
Good afternoon. Transmission of HIV is a crucial factor in determining the success of the virus. The underlying principles of transmission are not well understood and are still being explored. To understand what kind of viruses get transmitted from one person to the other, in today's talk, I will discuss one variant of HIV, and the focus of my presentation will be on the selective transmission of one variant over the other. Now I mentioned kind of virus and viral variants. To explain this further, I will first introduce to you the intrinsic diversity of HIV. HIV is highly genetically diverse and is classified into various subtypes from A to K. Among these, subtype C is predominant, causing almost half of all global infections, while the rest of the subtypes cause the rest half of the infections. This clearly shows that there is something different in HIV-C, which is giving it an advantage over the others. What is different in HIV-C? Throughout its genome, HIV incorporates various subtype-specific variations. But a unique feature of subtype C is the presence of frequent sequence duplications. Two such hotspots of sequence duplications are the transcription factor binding sites and the P6 protein. So these variants, which contain variations, are known as variants of the type C virus. And I will talk about one such variation, which is the PTAP duplication in GAP protein. PTAP amino acids are responsible for budding or emergence of the virus from the cell, which is an important part of the virus's life cycle. So as you can see here, many of the type C viruses contain a duplication of the PTAP amino acids. Now the question arises, is the double PTAP variant advantageous in nature? In our lab, we have seen that the PTAP duplication does have an advantage associated with it. In the sequences present in the database of the population, it is seen that most of the subtype C sequences contain a PTAP duplication, that is almost 30% of them. So this shows that there is a high prevalence of double PTAP variants in the population. This trend continues within individuals wherein sequences extracted from patients when analyzed by NGS showed that the double PTAP variant represented in black bars here were always dominant over the wild type 1. This shows that there is a replication advantage associated with the double PTAP variant. This led us to ask if the replication advantage within individuals can be translated to a transmission advantage at the population level. To understand the significance of this question, I will first introduce to you a major concept in the transmission of HIV, which is the transmission bottleneck. There exists a stringent bottleneck at the level of HIV transmission. This image depicts viruses being transmitted from the donor to the recipient. And although the donor contains many different variants of the virus, only one or few of these variants are able to establish a successful infection in the recipient. This is known as a transmission bottleneck, and these transmitting viruses are selected for transmission. Based on this, we propose that if we put all of the other variations aside, then the double PTAP variants represented in black dots here will be the ones that will be transmitted from the donor to the recipient preferentially. This is because, as I mentioned, that within an individual, the double PTAP variant has a replication advantage because of which it is more abundant than the wild type virus. And it is because of this abundance that it is getting a transmission advantage. How do we test this hypothesis? By studying transmission of HIV, which comes with its own set of challenges. So the major requisites for studying HIV transmission are unambiguous donor identity, availability of sample from both donor and recipient, and information of time of transmission. One of the models used to study transmission are serodiscordant couples in which one partner is initially HIV negative and it contracts the infection from the other partner at a later point of time, and at this point transmission can be studied. However, a major limitation of this model is that it does not fulfill all of the aforementioned criteria, mainly because of the lack of confidence of donor identity. The other model, which is the mother-child cohort, is the one that we have adopted. In this, the transmission occurs from an HIV positive mother to the child, and this cohort robustly fulfills all of the criteria. An added advantage of our study design, which I'll explain later, is that we have done sampling at multiple time points, which makes it a longitudinal study. Moreover, we are using a powerful technique of single molecule sequencing to study transmission. A limitation associated with the study is that there is limited sample size, which leaves us at a statistical disadvantage. However, the results that we'll get from this study will still provide us novel leads to take ahead in the future. As I mentioned, we are studying a mother-child cohort, which is being done in collaboration with Dr. Sanjeeva at IGICH. And we have recruited 75 children and mothers of 25 of these children for the study. These children are being followed up before the initiation of drug treatment at 0 months, and at 6 months, 12 months and 18th month post initiation of drug treatment. This schematic here shows the strategy for sequence amplification from these samples. So of the 25 mother-child pairs that we have, we were able to obtain sequences from 10 of them, and preliminary data shows that 3 of these pairs contain the PTAB duplication. The 3 mother-child pairs containing the PTAB duplication are depicted here. So these string of letters depict the amino acid sequence, and the dots represent identical amino acid in the child. The blue box shows the original sequence and the red box shows the duplication. So in 2 of the pairs, IG76 and IG90, there is an exact duplication from mother to child. This shows that the double PTAB variant is being transmitted from mother to child. In the third pair, IG53, only the child contains the PTAB duplication, not the mother. This is interesting because it suggests that in the child, a de novo duplication event has occurred. A phylogenetic analysis of all of these sequences show that the mother-child sequences cluster together, which indicates common ancestry. To summarize, from our results we can infer that in 2 pairs, double PTAB variant has been transmitted to the child. In the third pair, only the child contains the double PTAB variant, which suggests de novo sequence duplication in the child. And no mother-child pairs were found in which only the mother contained the PTAB duplication, which is again indicative of transmission being occurred when the double PTAB variant is present. However, these results are not conclusive enough because we still need more numbers to strengthen our inferences. And moreover, the results that we have obtained till now are from Sanger sequencing, which is a relatively lesser sensitive technique, and we need higher sensitivity of next generation sequencing to be able to pick up both the viral variants. So the future direction would be to amplify full-length sequences from these samples and subject them to next generation sequencing and do an ancestry determination to find out which virus is being transmitted. Thank you.
So what's the evidence to believe that PTAB duplication may have a transmission advantage?
So what we are proposing that because there exists a bottleneck at the level of transmission. So all of the viruses will not be transmitted from donor to recipient. And we have already seen that the double PTAB variants are more abundant in a mixed infection. So that is why we think that if we put all of the other variations aside, then there is more chance of the double PTAB variant being transmitted to the recipient because of its abundance.
Okay, I was wondering whether you know any molecular term that, whether it's binding more efficiently to some receptor or something. I don't know.
That will not be a property of the PTAB motif as such. That is a property that would be associated with the other parts of HIV. So these same variants can also contain those specific characteristics. We will analyze those sequences in the future to understand if those motifs are present in them or not.
One of the reasons is that it's not selected against. So that's your hypothesis. And this high prevalence in the population itself is an indicator enough to say that there is selective advantage as opposed to. So why do you want to go to this cumbersome mother-child pair where numbers are going to be very, very small and may just leave you hanging one way or the other?
That's because only in these kind of cohorts we'll be able to say which is the donor, because we want to study that the donor should also contain that variant and then establish that it has come from the donor. That same variant is the one that has come from the donor to the recipient and established an infection. So even though it is being selected for in the population, there still exists this bottleneck, and the bottleneck has shown that some variants are specially selected for transmission.
So from donor to child, parent to child is one of the indicators. Numbers small, in some sense you are having a confounder there. But on the other hand, child itself or an individual itself is an ecology of its own type. And if something survives in that milieu more and is not eliminated by the dynamics of many variants which may evolve, I think that serves the purpose too. In any case, I think I'll stop here. There may be other questions.
Yes. But the relevance of transmission is still there. I mean, this is one case in which we are seeing that there may have a de novo duplication may have occurred here. But in the other two cases, we are still seeing that the transmission is happening from mother to child. So there are tools available which can show that it has indeed been transmitted, and these are not de novo duplication events in themselves.
Yes. So, okay, sir, one quick question. Yeah.
De novo duplication may not be de novo duplication because in sequencing you might have not exhausted all the viruses which are present in mother.
Yeah, that is correct, because this is Sanger sequencing, it does not have that sensitivity. So that is a distinct possibility that if we sample again and we do next generation sequencing, we might find that the mother also contains a duplication.
Correct.
Yeah.
So that possibility
exists, yes.
Sure. Okay, thank you, Jyotsna, for this wonderful talk.
Thank you. Yeah.
But the questions had already taken a longer time, so I thought I will. Okay. So the question says, why does the motif confer a selective advantage? What is the biological basis for such a selection? And are there any other motifs that are transmitted like this?
Okay. So motifs for transmission, there have been studies that show that specific characteristics in envelope of the virus. Okay, the presentation is not open, otherwise I could have shown you. So that is one part of the virus, and envelope has certain characteristics which make it more transmissible. But the actual advantage associated with the PTAB duplication is something that we are still investigating, that is not well known.
Sure, thank you. So our next speaker is going to be Viveka Singh. She's a student from Neuroscience Unit working with Professor Shiba Vasu's group. Her talk is titled, Can Cyclic Food Availability Serve as a Time Cue for the Drosophila Circadian Clock?
Good afternoon all. I hope I'm audible. Today I'm going to talk to you about the relationship between food and circadian clocks. Circadian clocks are internal timekeepers that run with near 24-hour periodicity, and there are several cyclic cues in nature like light and temperature that can serve as time cue to the circadian clock. The clock integrates this cyclic information and brings about rhythmicity in various behaviors as well as physiology, and also temporally separates these rhythms to specific times of the day. Now, apart from these abiotic factors, food can also be cyclic in nature, and for example, in the case of honeybees, the availability of pollen and nectar becomes cyclic depending upon when the flower opens. it is also well documented that mice display food anticipatory behavior in response to cyclic presentation of food. So here I ask, how is food information in the environment integrated into the circadian system, and more specifically, can food availability act as an input to the circadian clock? In order to address this question, we made use of Drosophila melanogaster because of its well-characterized behavioral rhythms and also very well understood molecular clock. We utilized Drosophila activity monitors to record the activity of the fly, and this activity record was then represented in the form of an actogram, where on the y-axis you have time of day, and on on the x-axis you have the time of the day, and on the y-axis you have activity on subsequent days. Now, if you the activity here is represented, the activity here is represented in black bars, and if you notice that the start and the end of activity on subsequent days is occurring rhythmically around the same time, and this makes this behavior rhythmic. Now, this rhythmicity in behavior is also seen in the absence of time cues, and such a rhythm is called as a free-running rhythm, and the period of this rhythm depends upon the intrinsic period of the clock, tau. When you subject the flies to a light-dark cycle of 12 hours of light and 12 hours of dark, the environmental cycle T is equal to 24, and the activity synchronizes to the environment such that now the intrinsic periodicity is also equal to 24 hours. Now, if I shrink the day to 21 such that the environmental cycle is now 21 hours, or I expand it such that the environmental cycle is now 26 hours, in both the case the intrinsic periodicity tau changes to match that of the environment, and this is called as period matching. To test period matching, we subjected our flies to a T21 feeding starvation cycles in the absence of all other time cues, and this pink window over here represents the window of starvation. After subjecting them to these cycles, we release them in constant conditions with ad libitum food. In a similar fashion, we also provided long food availability cycles by providing T26 cycles. And in each of our experiments, the experimental flies were maintained on agar during starvation, and our disturbance controls were were given ad libitum food access. Now here I show you representative actograms of a control fly and an experimental fly that underwent a T21 cycle, and you can see that the experimental fly is unable to synchronize its activity to the environmental cycle. This becomes more evident from this graph, where a large proportion of flies, experimental flies, show two distinct periodicities. One that is closer to the environmental period, and the other close to their own intrinsic periodicity, instead of a single dominant environmental periodicity. This suggests that the internal clock period does not match the T21 cycles. Now we also looked at the change in period during the FS cycles, and we found that the change in period in the controls was negligible or close to zero. However, in the case of our experimental flies, this period was significantly different from that of the controls, and also in the negative direction, suggesting that T21 results in small but significant shortening of the intrinsic period. Similarly, in the long food availability cycles, we found that the experimental flies were unable to synchronize their activity to the environment, which is also evident from the fact that there are two distinct periodicities in a large proportion of experimental flies, one that is close to 26 hours and the other close to the intrinsic periodicity, and so the internal clock period does not match these cycles. The change in period in the experimental flies is also significantly different from the controls, and this time in the positive direction, suggesting that T26 results in small but significant lengthening of intrinsic period. Now I also looked at another criterion which is stable phase relationship by indirectly looking at phase synchrony among individuals. Now here I show you a schematic of two individual flies that have their activity synchronized to a light-dark cycle or to their environmental cycle. Okay, and in here you can see that the blue dot indicates phases, and both these flies have similar phases, and these phases are reproducible across individuals that get the same treatment. And in such a case, you see that most of these phases are clustered together, and this is called as inter-individual synchrony. Now, when the activity is not synchronized, these phases are governed by the intrinsic periodicity, and you see that these phases are dispersed as depicted in these polar plots. So, when finally we increased the starvation duration, and in the case of 14 hours and in the case of 16 hours, in both the cases, again we saw that the activity is unable to get synchronized to the environmental cycle, and most importantly here from these polar plots it becomes clear that our experimental flies are showing dispersion of phases to the same degree that the controls show, which suggests that these flies do not show inter-individual synchrony. And this is true of both the cases that we saw, where we increased the starvation hours to 14 hours and to 16 hours. Increasing starvation duration does not result in improved synchrony. So I summarize here that feeding-starving cycles do not synchronize the activity-rest rhythms. However, feeding-starving cycles do modify the period of these rhythms, suggesting that clocks are indeed sensitive to food availability cycles, and this helps us to conclude that food cues are indeed integrated into the circadian clock. However, the extent to which they can modulate clocks differs among different organisms, which also makes us, it is important to appreciate that we've looked at only one output of the clock, which is activity rest. It would be very, very interesting to see how other outputs of the clock get affected by food availability cycles. And I'll stop here. Thank you for listening. Yeah.
From you, there's a question from Prashant.
I have one question. So you are correlating food availability to the circadian rhythm. Correct?
I want to see if food availability cycles can serve as an input to the clock.
Correct. But your assay is basically assaying the activity itself.
Yes.
Correct?
Yes.
So what are the chances that starvation is leading to decreased energy production in the fly and leading to sluggishness?
Okay, actually we see quite the opposite. I'm sure that there are various other physiological processes that are changing because of these cycles that we are providing, and actually what you say is sort of true, because these the opposite is true, because these cycles lead to excessive activity during the starvation period. So there are things that are changing.
But if you go down number of days, then it changes, no?
Yes, yes. So in the beginning, at least they respond by showing excess activity, and over time that activity dies out. So yes, there are immediate changes to starvation.
What I'm saying is, due to food starvation, there is anxiety in initial time?
I wouldn't call it anxiety, but usually food-induced hyperactivity is also termed as foraging-related behavior, and yes, that has been seen independent of the clocks also.
Any more questions? There's a question from Professor Amit.
Sure. There are various hunger circuits that we know of, and one can always go and check if these known hunger circuits are actually communicating with the clock circuitry that we have, but we've not gone ahead and looked at any of this. Yeah.
There's one question from Professor Amitabh Joshi. Why not first check a food starvation cycle of 12 to 12 hours to ascertain entrainment instead of a shorter and longer than a 24-hour period food availability cycle?
Actually, we did do that, and we found that those results were a little confusing. We couldn't arrive at a conclusion whether it is indeed proper synchronization or not. and that's why in subsequent assays we went ahead with these results.
Sure. And there's one last question from Sri Lakshmi Joshi. Do the flies get habituated to starvation?
It appears so from these graphs, at least with the 16 hours of starvation. It feels like initially they showed excessive activity and then they reduced it, so it appears so, but we don't really know how that happens.
Okay, sure. Thank you, Viveka. Our next speaker is Anirudh Mirmira, and he's a student of Theoretical Science Unit working with Professor Vidhyadhiraja. He's going to be speaking on interacting quantum dot circuits.
Good afternoon. Today I will be speaking about interacting quantum dot circuits. So you might be wondering what are like interacting quantum dot circuits. Okay, so before I go to that, let me like just give an outline of the talk. I have like 3 parts. In the first part I talk about what quantum dot circuits are and why are they interesting. The second part I'll talk about the method we have developed, also like, and to study them and what that involves, what does studying them involve. And third one is in the future, how do you take it to look at more interesting systems and so on. So I'll come to quantum dot circuits. So this is essentially a schematic of a quantum dot circuit. So the orange thing you see in the center is a quantum dot, and you have 2 leads, a left lead and a right lead. And this is a picture of Coulomb blockade. I'll just explain it in a simpler way. The thing is like, you can have an electron sitting on one of your leads and it wants to go into the dot, but if there is already another electron, or whether depending on the occupation of the dot, the electron can go or not. So this is the Coulomb blockade thing. And so I just showed you a picture. Now I'll tell you what a quantum dot is. So you might have heard the morning talk also, where there were references to quantum dots. When generally you hear references to quantum dots, they are the 0D nanostructures. So most of the times, at least in JNC, people work on colloidal quantum dots, which are like collections of 10 to 100 atoms in a suspension and stuff like that. Because they are so small, quantum mechanics becomes very important. And in particular, confinement. So confinement effects come into play. And if you remember like a particle in a box picture, you see that the level spacing becomes uniform and that becomes tunable. So when I say a circuit, what do I mean? A circuit is basically you just connect 2 leads and apply a potential. So this could either be a DC bias or an AC bias, or a pulse and a quench, those kind of things. So how do you model a quantum dot circuit? So there are, as I said, there are 2 leads and a dot. So the dot for us is like a single level, and it can either be occupied by 2 electrons given spin, or 1 electron with like no spin. And there's a on-site interaction on the dot. That means if 2 electrons are sitting on the dot, then they feel a repulsion and they don't want to sit together. And there is a hybridization between the leads and a dot, which connects it and allows your electrons to hop from one to other. So mathematically, you can represent this by this Hamiltonian. So this is called as the single impurity Anderson model, and this is the lead terms, this is the hybridization, and this is the dot term. So now, why do you want to study quantum dots, and what are they useful for? So this picture I've just displayed is like it's from an experiment published 3 days ago. So this is the first time that I've actually been able to capture the wave function of what a quantum dot. This is something called as a electrostatic quantum dot, where this is not in solution, but this is on a bilayer graphene, and people have captured the wave function and how it looks. So interest is again. So I'll take a step back. We are looking at quantum dots, and we are looking at quantum dots out of equilibrium. This is because we have a bias, and we'll have a current through the quantum dot. So the interest in quantum dots is that because of the U, or the interaction, there is something called as a Kondo effect, where magnetization might disappear due to many body effects and so on. And also, as I explained, there is a single electron. So each quantum dot can have 1 electron, at most 2 if you give spin. So for a spinless quantum dot, it's 1 electron at a time. So this is like a miniature single electron transistor. And Coulomb blockade is what I just explained. If there's another one already there, it cannot move. And so what about non-equilibrium? Non-equilibrium in general is extremely rich, and it's also very, very ubiquitous, because you do a lot of things to get away from non-equilibrium, but most realistic experiments have some effect of non-equilibrium in there. And also there are possibilities of accessing phases which are not accessible by equilibrium methods. So this is like why you want to look at also, and there is also like these phases could also include topological phases. And also when I say leads, you can just have two metallic leads, or you can have a bit more complexity in that. You can have something like spin orbit coupling, which is what I'll be talking about in the talk. And there's also like things like Luttinger liquid leads, where the lead electrons also interact, and you can have superconductors as your leads and so on. And there have been many experiments. One is, as I said, the metallic quantum dots, where they have looked at confinement in a bulk system. And also there are pump probe experiments where you have a laser shining at one frequency and you excite it and you get a like a readout. And then also you have cold atom simulators of these systems. Okay, so I'll come to now the main part of the talk, which is like solving an interacting quantum dot circuit. So method, let me just talk about like what solving involves. So what do you mean by solution? So here what we are looking at is like we do something called as like Green's function based approaches. So you want to calculate an object called as a Green's function, which encodes the basic physics of the problem. And the Green's function are directly connected to observables, because things like susceptibilities and all can be directly calculated from Green's function method. And one of the most important equations here is something called as the Dyson equation, which is given by this. And here sigma is the self energy which encodes interactions and in some sense, the interactions of the system, and G is the without the interaction, the free Green's function. So, and in this particular talk, I'll be talking about the steady state. So, what do you mean by the steady state? Is that the current into the dot and current out of the dot are the same. So, there is no charge buildup, and we need to account for current through this dot. So, that is the meaning of steady state, and it doesn't vary with time, and it enters as a time difference only. There are other methods like master equation, renormalization group, quantum Monte Carlo, etc. So this is the IPA, is our method. I'll just quickly run through this. So this is a diagrammatic perturbation theory, and it's a second order perturbation theory. What you do is like you take a second order interaction and you use an ansatz where the self energy is modified, and the ansatz is such a way that it interpolates between a high frequency and the atomic limit, the high frequency and the atomic limit. So this is the ansatz, this is the high frequency part, this is the atomic limit part. And the implementation is like you look at the hybridization function, and once you have the hybridization function, you need to calculate the self energy. And the self energy is because it's second order, involve convolutions of your Green's functions, which we use Fourier transforms to do that. And you also have to take into account the dot occupation and the current. So these are done self-consistently. And so this is like the under bias, what happens to the something called as the Kondo effect, which I mentioned. So this is the zero bias peak, and you can see that there's a clear splitting as you increase the bias in the leads. And so when you have spin orbit coupling, what happens is so spin orbit coupling gives you like a multi-terminal scenario. Because of the spin orbit coupling, you can do an angular momentum expansion, and you will get multiple leads connecting to the same dot, and this will split your hybridization function in this way. So here this has been plotted assuming like, so this is the hybridization function assuming a k independent v. One moment. So assuming a k independent v, when you do that, it's like a little harder to track numerically, but otherwise yeah. So it's easier to do analytics, but it's much harder to do analytically. Sorry, numerically. And so I'll just finish off with extensions of the method. And one is like DMFT, where you can map on a lattice system to a dot by looking at the effective medium being evolved temporally, and where you self-consistently evaluate your Green's function of the lattice and the dot. And so this is the DMFT result, where we have changed the particle hole symmetry, and you can see that the asymmetry is coming in. And the last one is like, how do you go beyond the steady state? One is like, as I told you, this was a perturbative solver, so you can go look at non-perturbative solvers like LMA in steady state. and then there is a, you can have the full time dependence, go away from steady state using like the full both T and T prime, and also look at lattice systems by doing a DMFT. So thank you.
So thank you, Anirudh, for this wonderful talk. Go on to the next talk. This talk is by Dr. Jayashree Sanwal from the Geodynamics unit here at JNCASR. So I request Dr. Jayashree to please share her slides.
So good afternoon, everyone. First of all, I would like to express my deep thanks to President of JNCASR and organizing committee to give me this platform to share some of my results with you today. So I would like to drag your attention into a very different field of science. It's earth science, and I think many of you are not aware with the present ongoing research in the geodynamics unit. So I would like to give you a glance at the activities we are involved with. So the main focus of my research work centers around the most active, topographically highest and the youngest mountain range in the world, the Himalaya. So as this diagram illustrates, the titanic forces of compression, which begins between 40 to 50 million years ago, and the still ongoing northward movement of Indian plate and eventual collision with the Eurasian plate gave rise to the 2,400 kilometers and 250 to 300 kilometers wide mountain range or mountain arc, as you can see here in this picture. And this mountain rose up to 500 to 8,000 meters above the mean sea level and is still undergoing. So this ongoing movement triggers frequent earthquakes in the Himalaya and adjacent plain. So one of the objectives of my research is to date the past event of large earthquakes using multiple geological proxy. Well, due to the time limitation, I can't elaborate this part of my research, but any of you are interested to know more about it, you are most welcome to Geodynamics unit anytime. So as I said, the Himalaya has not only witnessed the unfolding history of the past earthquakes, but also vitally affect the atmospheric circulation over the Indian subcontinent and makes the barrier for the moisture which rises from Arabian Sea, which is known as Indian summer monsoon, and also obstruct the moisture which rises from Mediterranean Ocean, which is a synoptic scale extratropical cyclonic winds known as western disturbances or westerlies. So the Himalaya from west to east, if you go, you will see the diverse precipitation regime. We have the diversity in the precipitation. So what kind of climate we are seeing at the like Western Himalaya, we cannot expect the similar climate in the Eastern Himalaya, Central Himalaya, or any other regions of the Himalaya. So if we see the overall pattern of climatic changes or today's climatic pattern over the Himalayas, so we receive about 60 to 70% of the rain during Indian summer monsoon, which is during the month of July to August, September, and the maximum precipitation in the form of snow, which we receive during the winter time, and this gets mostly influenced by the winter westerlies. So if I talk about the Western Himalaya, since my work is focused in the Western and Central Himalaya, the westerlies plays a very important role to sustain the glaciers, which are indeed very important to contribute the most in the groundwater, the southern plains. So so the winter time, of course, so my focus is mostly on the westerlies, because the role of westerlies has not been understood very well in the past, how it has behaved in the past. So this is what is the main objective of my research work, and perhaps for my talk also today. So well, I don't have enough time to explain the climatic changes from the beginning of its evolution. Like as I was telling you, beginning of the Himalaya has changed the overall climatic pattern over the India, which I may not be able to speak today because due to the time limitations. So I will be mostly discussing about the climatic changes for the past 20,000 years. and geologically, which is a very young age. So the talk of my title is Deciphering Clues to Past Climate Changes Lodged in the Geological Archives. So, everybody, most of us, we always talk about the global warming caused by we human. There is no doubt that we contribute to the warming of surface to an extent. But beyond that, nature is a much powerful to control the cycle of glaciers and interglacial period. So the climatic changes, when you see the natural cooling and warming of the continents, this has been happening, throughout the geological time. Caused primarily by the reoccurring changes in the Earth's Milan-COVID cycles, the irregular oscillations of sea surface temperature conditions and conditions of the equatorial Indian and Pacific Ocean, the Indian Ocean dipole, and the El Nino southern oscillations, and albedo variations also influence the intensity of and behavior of Indian summer monsoon. The change in synoptic scale cyclonic circulations have been influencing the climatic behavior over the land and mountain in the past, like today. So today we see a lot of changes around us. So these changes have been happening in the past as well. So, today we have a lot of equipments to monitor the precipitation, temperature, I would say overall climate, what is changing around us. But what about the past, beyond the instrumental era? There comes the need of a geological proxy to go back in time and unravel the past climatic changes. So as a geologist, we use a number of proxies. As far I am concerned, I mostly use the sediment core and the cave deposits in Himalaya. So these are the tree rings which of course we have started using in the Western Himalaya for some of our sites, and ice core so far I have not used. So my focus will remain mostly on the sediment cores of the lakes and the cave deposits. So we have collected a lot of corals from Andaman Ocean, and we also use biological proxies, but of course not in Himalaya because we don't have such kind of marine sediment, especially the Quaternary period. So we mostly concentrate on the cave deposits and the sediment core. Now, here you can see the picture very clearly. This is a photograph which I took inside the cave. So cave deposits are basically the secondary deposition of carbonate, mainly formed by two minerals known as aragonite and calcite, and with some few traces of other elements. So the formation of speleothem starts in the limestone cavities, which are like deep and dark silent void rooms of carbonates. And the silence of the void is mostly broken by a drip of water forms either by the meteoric water or the groundwater, which dissolve the topsoil and the bedrock, which trickles through, holding most of the environmental information stored within a small drop of water, and it drops over the cave floor, with time it gets deposited in several fine annual lamines, and the deposition grows upward from the surface called stalagmite. So here you can see the picture of stalagmite, the water dissolving all different kind of minerals and trace elements. With the water, it drops on the surface of this particular structure, which is called stalagmite, and the stalagmite grows through the time. As well, the stalactite, which hangs down from the roof to the bottom, is very important feature, and these are also known as soda straw. So they also form a similar kind of pillar structure, but this is not as important for the climatic studies as the stalagmites, because stalagmites have most of the material, most of the deposition within it, whereas we lose lot of sediment or a lot of carbonate, lot of information when we study only the stalactites. So stalagmites are much more important for us, which we use for our climatic studies. So, now if the long-term, high-resolution, annual to decadal scale climatic changes, we can understand by using the different kind of experimental technique on these samples. So I use the chemical analysis, trace element analysis, stable isotope to understand how climate has been changed in the past with the signature and looking at the ratio of oxygen isotope composition. And so these are the areas which I mostly concentrate on: Uttarakhand Himalaya, Himachal Pradesh and Jammu Kashmir. So these are some of the samples which I have collected from Vular Lake. So now I would discuss a bit about my results and the climatic interpretations which I used using the sediment and speleothems. So first, let me take you to some of the lake deposits which are in Kashmir Himalaya, Ladakh Himalaya, and central and western Himalaya. So this lake, Vular Lake, I have sampled I was in JNC, and there are few sections from Ladakh Himalaya which I have done during my doctoral thesis in 2000 to 2002, and then this is a Dwarahat Paleo Lake section which is in central Himalaya, which also I have done during my tenure in JNC. And let us see the result now. So this is a profile, this is a paleo lake profile, as I showed you earlier. These kind of sediment, this is actually was a lake long time back, about 50,000 years before present, and now this lake is no more, but it has left behind the thick pile of sediment. So we explore this sediment to understand the climatic variation. So here, in this particular section, I have used the carbon isotopic variation to understand the vegetation pattern. So mostly we divide like the isotopic ratio in terms of broadleaf plants and shortleaf plants, C3, C4 plants. So this profile, approximately this particular lake has formed around 30,000 years before present. So if we see the bottommost part of this particular profile starts with a warm and moist climate. And then slowly you can see the peak and the curve goes towards the arid climate, showing the abundance of C4 plants, which are the short-leaf plants, and they survive mostly in the alpine and very cold climate. And then slowly this graph again goes towards a warmer and moist climate around 12,000 years before present. Then again we have a drastic change in the vegetation approximately around 8,000 years before present, which is also known as very well known event of cold excursion, cold and arid climate. So likewise, we have one more section again in central Himalaya, and this is a palynological data which I have used. So if you see, this lake was also formed approximately 21,500 years before present, and if you see the distribution of vegetation, so the lower part of this profile is dominated by a kind of vegetation which lives or survives in the warmer condition. And if you see this second zone here, this zone indicate towards again the cold climate. So all the plants which survives in the warmer conditions were vanished slowly, and the domination was the plant which survived during the cold climate. Likewise, we have a third zone which again indicate a long spell of warmer climate. So likewise, we have different whatever we have worked in Himalaya and some other people's work I have combined in this slide and tried to show, and when we compare the results, whatever we have gathered from central Himalaya and western Himalaya, they matches very well with the results which people have obtained from Ladakh Himalaya and even in Tibet mountains, Tibet plateau. So now I will come for the lake cave sediment. This was a part of our research on lake sediment. So we have different caves in western and central Himalaya. So recently we have worked on a cave in Chalapathy, which is in Jammu Kashmir, and there are several caves we have in central Himalaya. I'm not going to show all the caves, but only few I will talk about today. In this particular map, I have shown you that some few more sites of which has been worked in China, Oman and Israel. So if you see the Israel, this place is also under the influence of westerlies as our western Himalaya. But the Oman only receives the Indian summer monsoon, get influence under the Indian summer monsoon, at the Dongyi cave, which is situated in China, also get mostly affected by the Indian summer monsoon and northeast monsoon. But our sites here are also under the influence of Indian summer monsoon during the summer season, and during the winter it also gets affected by the winter westerlies. So this is the photographs, some of the sections, some of the caves here in Uttarakhand Himalaya, and one is in Himachal Pradesh. So this is a field work which I have done in the month of January. I was actually very lucky to do the field work just before the lockdown. So I have sampled few caves during that time. And for cave research, it is very important for us to understand the water chemistry, because until we understand the present conditions and the water condition, it will be very difficult for us to go back in time and interpret in terms of climate or temperature. So this is a cave passage which you can see from a long distance, and this is a collection. This is how we collect the water sample which drips down at the entrance, and this is a collection of snow, fresh snow, to see the stable isotopic signature. And this is a cave morphology, how the cave looks from inside. So this cave was full of water, and the sample was done, inside the deep passage, the second passage of this cave. And this is another cave morphology, and this is I'm collecting some water, dripping water sample. After I come to the lab, so I start with understanding the lithology or the stratigraphy of particular sample. So I have made the thin sections of this particular sample. So after making the thin sections, and I go for SEM studies to understand whether this
Dr.
particular
JC,
sample
you have 2 minutes
is...
left. Could you please conclude the talk?
Okay, sure. So this is exactly, we see how the speleothems are made up of, what kind of minerals are there. So after doing this, we go for the sampling, close sampling, and we do the dating part. And these are the results which we have from one of the cave which is in northwestern Himalaya. I was talking in Kalakot area, and this is our result. So this particular sample gives us the data of about 16,500 years before present, how the climate has been changes since then. And this is another site. So when we compare the site, we see, if you remember the map, so most of the data, our data matches with the Sorak cave in Israel due to the westerlies effect. So these are another result. And this is a conclusion of my studies from lake and cave. I can't read it all because don't have much time. So a part of it, we have done some kind of climatic modeling using our cave data, which I'll just quickly go through. And these are the precipitation during the different times which we have done. And these are the overall conclusion of my studies. So since I don't have much time to read all these things, so I can now conclude my results, like my talk, with an acknowledgement to Jawaharlal Nehru Center, which has given me the place to work and continue my research. Indian Institute of Science, I was there for about 4 years before coming to Jawaharlal Nehru Center, and I'm very grateful to DST Young Scientist Scheme, SERB scheme, and DST Women Scientist Scheme now to continuously supporting me for my research work, and these are my collaborators. So if I have some 4 minutes, 2-3 minutes, I was asked to give a small tribute to Professor K.S. Valdia. Is it possible, or?
Sure, please continue.
Okay, thank you so much. So at the end of my talk, I would like to pay my tribute to Professor K.S. Valdia, who departed unexpectedly this year on 29 September after battling with cancer of about 4 months. The legend among geologists, Professor Valdia was a great visionary who not only shaped our understanding of the geological making of the Indian subcontinent, but also spread the environmental awareness among the society and students. His great love and passion for geology can be explained as an appeal of his meticulous nature. In recent years, he had devoted himself to writing books, popular articles, and in social services related to the science outreach program. blending remarkable curiosity, fundamental skills in diverse area of geology, and harboring desire to improve geological education for students, struggling researchers, and public. So encompassing broad array of information, his profusely illustrated books have become textbook in academic across India. Subsequently, more than 120 research papers, authoring of 21 books, and extensive popularization of science in India have continued to heap credit and award upon him. He has been honored by many precious national awards, including Padma Bhushan, Lifetime Excellence Award, Padma Shri, S.S. Bhatnagar Award, and many more. A million years of mountain building, plates of bedrock grinding against each other fascinated him the most. And I am indeed very fortunate to get a chance to learn the geodynamics processes during several field works with him in the rigid terrain of almighty Himalaya. I first met him in 1998 when I was a master's student and did a long day field work around Nainital Hills with him. Since then, I became a great admirer of his work. It was a 22 years long association with him, and I still can't forget the experience I had working with him across the Himalayas, starting from Gangetic Plains to higher Himalaya, crossing the Shivalik foothills and lesser Himalayan mountain. Especially the experience working along the Kali River on the way to Kailash Mansarovar and the Milan Glacier during my PhD and post-PhD training. There I learned the fundamental of the active tectonics in the field, which we later compiled in a form of most comprehensive book on neotectonics in India. I feel much privileged to work each chapter of this book as his co-author. As I mentioned earlier, he was not only a great orator, he was a great orator and also was a great narrator also, everybody knows. So by the end of the field, every time he used to narrate a lot of stories, which still I remember, but I don't have much time to share today any of the experience. So I would like to conclude my talk with giving him a heartfelt tribute. Thank you so much.
Okay, so there looks like there will be no questions from the audience here or online. So we would like to thank you again for this wonderful talk. Thank you.
Yeah, thank you so much. Thank you indeed.
Good afternoon, all of you. Professor C.N.R. Rao, Professor Kulkarni, my faculty colleagues, students, their friends and families, and the members of my academic office here at JNCASR. On behalf of JNC, it's my pleasure to extend a very warm welcome to you to a very important function of the year today, the degree award function. Typically, this hall is absolutely packed on a degree award function, but because of the ongoing pandemic and the restrictions associated with it, I must thank Professor Kulkarni who allowed us to have this function as lively as possible, but within those constraints. And I must appreciate all of you to be here with us for this function in person in spite of these difficult times. So we'll get started with the function now. This year, 35 students completed PhD from JNCASR and 23 students completed master's degree with a thesis from the center. Out of the total of 58 degrees to be awarded, 24 of them are here in person with us today and will receive degree from the hands of Professor Kulkarni, our president of the center. May I now request Professor Kulkarni to come on dais, please. So we'll start with PhD degrees. And I call upon name of a student, and then the student should start, or the nominee of the student who will receive the degree should come to the stage. Korlepara Divya Bharati. She completed her PhD with Professor Balasubramaniam on the thesis Computational Investigations of Mechanisms, Pathway Complexity and Dipole Dynamics in Supramolecular Polymers. And Srikanth is receiving the degree on her behalf. Thank you. Next, Ragesh A.V. He worked with Professor K.S. Narayan on electric field assisted growth and control of morphology of films for organic devices. Mr. Purohit Sumukh will receive the degree on his behalf. Thank you. Sankalpa Nambiar, who worked with Professor Ganesh Subramaniam on swimmer suspensions, fluctuations, microstructure and rheology. His brother, Mr. Siddharth Nambiar, will receive the degree on his behalf. No, please don't talk like this. It's okay. Suchismita Adde, she worked with Dr. Tapas Kumar Kundu on role of nucleoplasmin family of histone chaperones NP1 and NP2 in the regulation of transcription. Krishnendu Guin, he worked with Professor Kaustubh Sanyal on chromosome level genome assembly of the human fungal pathogen Candida tropicalis. Lakshmisha K.N. worked with Professor Hemalatha Balaram on biochemical and physiological investigations on adenosine monophosphate, diminase and haloacid dehalogenase superfamily members from the Plasmodium spp. Saloni Sinha worked with Professor Manisha Inamdar on elucidation of the conserved role of OCIA domain proteins in regulation of Drosophila and mouse blood cell homeostasis. Professor Manisha will receive the degree on her behalf. Shreyas Sridhar worked with Professor Kaustubh Sanyal on assembly dynamics and structure function analysis of an unusual kinetochore in the pathogenic Basidomycetes budding yeast Cryptococcus neomorphans. His parents will receive the degree. S. Sundar Ram worked with Professor Kaustubh Sanyal on centromere-mediated genome rearrangements and functional analysis of an outer kinetochore protein in human fungal pathogens. Kaushlendra Kumar worked with Professor Umesh Wagmare on influence of solutes on the planar faults in nickel-based superalloys, a first principle study, and his sister will receive the degree on his behalf, Mrs. Aradhana. Pawan Kumar, who worked with Professor Umesh Wagmare on Phonon's nonlinear elasticity and first principles theory of martensitic structural transformation in metals. Thank you. We now will give away the certificates for MS in engineering. Pulkit Kumar Dubey, who worked with Ganesh Subramaniam on instabilities of rotating liquid columns and orientation dynamics of spheroids in shearing flows. And Mr. Pratik Anand will receive the degree on his behalf. Rohit, he worked with Professor C.N.R. Rao on investigations of the tunable electronic properties of 2D borocarbonitrides and of the epitaxial thin films of nickel oxide generated by ALD. Next, we have Master of Science degree in Material Science as a part of integrated PhD program. First person is Anjali Gaur, worked with Professor Balasubramaniam on molecular insights into a fluoride-based ionic liquid, a search for better fluorinating agents. Dhimahi worked with Professor Bivas Saha on the development of scandium nitride thin films for thermoelectric and electronic device applications. Next, we have certificates for Master of Science in Biological Sciences as a part of integrated PhD program. First is Ranabir Chakravarti. He worked with Professor James Chalaya on elucidating the role of astrocytes in SYNGAP1 plus minus mediated intellectual disability. Sharma Pragya Neeraj worked with Professor Shiba Basu on preliminary characterization of activity bifurcation observed in Drosophila melanogaster and the use of novel light regimes in probing the flexibility of the fruit fly circadian system. Next is Prathamesh Rajesh Dongre, worked with Professor Manisha Inamdar on elucidating the role of ASRICH/OCIAD1 mediated organelle homeostasis in hematopoietic stem cell aging. Jyotsna Karan worked with Professor Ranga Uday Kumar on understanding the significance of PTAB duplication for the replication fitness of HIV-1C. Padma Laya, she worked with Professor Kaustubh Sanyal on understanding the role of homologue of yeast YTA7 in chromosome segregation in the human pathogenic yeast Cryptococcus neoformans, and her sister Ms. Pragya Rashmi will receive the degree. Rahul Madan worked with Professor Hemalatha Balaram on towards structural and functional characterization of Plasmodium berghei halo acid D halogenase superfamily members and localization studies on Plasmodium berghei ionisin monophosphate dehydrogenase. And Ms. Akshaya Nambiar will receive the degree on his behalf. Akshaya Nambiar worked with Professor Ravi Manjitaya on elucidating the role of myosins in itinerary of autophagic flux. Then we move to Master of Science degree in Chemical Sciences. So as a part of integrated PhD program, Ritendra Singh worked with Professor C.N.R. Rao on investigations of catalytic properties of covalently linked 2D nanosheets and atomic layer deposition of thin films. Sudeep Mukherjee worked with Professor Jayanta Haldar on the development of cationic macromolecules to tackle drug-resistance bacteria and fungi. Now we have degree awards in absentia, so Professor Kulkarni will take a little break. He will remain with us. But as I call upon the name of the student and the name of his or her advisor, the degree certificate will be displayed on the screen. So you will get to read the title of the thesis of that particular student. So I will not spell out the details of the PhD thesis for this category. You are ready? First is Sudeep Das, who worked with Professor S. Balasubramanian. These are PhD degrees. Next, Badri Vishal worked with Professor Ranjan Datta. Next is Abhijit Sen, worked with Professor A. Sundareshan. Sonu KP worked with Professor Ishwar Murthy. Avani Mittal worked with Professor Amitabh Joshi. Hansraj Gautam worked with Professor Vidya. Shashank H.J. worked with Professor K.R. Srinivas. Muhammad Atif worked with Professor Santosh Anshumani. Gaurav Ramanand Barve worked with Professor Ravi Manjitaya. Aditya Mahadevan Iyer worked with Professor M.R.S. Rao. Palak Agrawal worked with Professor Namita Surolia and jointly with Professor Manjitaya. Sunayana Singh Rajput worked with Professor Ravi Manjitaya. Soumya Vats worked with Professor Ravi Manjitaya. P. Lakshmi Prasuna worked with Professor Hemalatha Balaram. Abhik Paul worked with Professor James Chelaya. Manisha Samanta worked with Professor Kanishka Vishwas. Krishnendu Jalani, Professor Subi George. Ananya Mishra worked with Professor Subi George. Saurav Chandra Sharma worked with Professor Sebastian Peter. Shikha Dhiman worked with Professor Subi George. Rajdeep Banerjee worked with Professor Shobhana Narasimhan. Wasim Raja Mondal worked with Professor Vidhyadhiraja. Debadipto Acharya worked with Professor Shobhana Narasimhan. And Shruti C.K. worked with Dr. Meher Prakash. We now move to the category of degrees of Master of Science in Engineering. Prashant Ramesh worked with Professor Alam. Alvin John worked with Dr. Divakar Venkatesan. Tanu Moy Dhar worked with Professor Alam. And Dheeraj Kumar, who worked with Professor Srikanth Sastry. We will now see degree of Master of Science in Material Science as part of integrated PhD program. Swaraj Sarvottam worked with Professor C.N.R. Rao. And finally, we will have a Master of Science MSc in Chemistry degree. There are 5 candidates. First is Acharya Yash Sanjay. Subhajit Das. Arnab Sinababu. Abhishek Rawat. Shubham Singh. That completes the award of 58 degree certificates today, and we now have a very important last part of this function, award and medals for the year 2020. I think we can close that part. Yeah. So the first one is Professor C.N.R. Rao Medal for the best PhD thesis of the year 2020. It is given in 2 categories. The first is the best thesis in physical sciences, and this year's prize goes to Dr. Manisha Samanta of New Chemistry Unit. Her thesis was on thermoelectric and ferroelectric properties of metal chalcogenides, oxychalcogenides, and topological quantum materials. She worked with Professor Kanishka Vishwas, and Ms. Sushmita Chandra will receive the medal on her behalf. Now we will have Professor C.N.R. Rao Medal for the best thesis in biological sciences, and this year's award goes to Dr. Krishnendu Guin of Molecular Biology and Genetics Unit, who worked on chromosome level genome assembly of human fungal pathogen Candida tropicalis. He worked with Professor Kaustubh Sanyal. Next we have Professor Radha Narasimha and Family Awards for the Best PhD and Master's Thesis in Engineering Mechanics 2020. For the PhD thesis, the award goes to Dr. Muhammad Atif who worked on essentially entropic lattice Boltzmann model with Professor Santosh Anshumali, and the medal will be received, scroll and the cash prize and the certificate will be received by Mr. Akshay Chandran on his behalf. The Best Master Thesis Award goes to Prashant Ramesh. He is not here with us, and his scroll and award will be collected later. Next we move on to another award, Srimati and Sri Bapu Narayanaswamy Prize 2020 for the Best Master's Thesis in Chemical and Material Sciences, and this was instituted by from a donation given by Dr. Indumati Rao to the Corpus Fund. And this year's the Best MS Thesis in Chemical and Material Sciences goes to Mr. Ritendra Singh of New Chemistry Unit, who is now an integrated PhD student. He worked with Professor C.N.R. Rao. There are two more small prizes which students are not here with us today to receive them, but I will just announce them for the sake of information. The first is Bapu Matru Prasad Scholarship 2020 for the Best Integrated PhD in Chemical Sciences, first year student with the highest CGPA performance in coursework. And this year the award goes to Mr. Animesh Das of New Chemistry Unit. And this year's Dr. Indumati Rao Prize for the Best First Year MSc Chemistry student with the highest CGPA in coursework goes to Mr. Acharya Yash Sanjay, and he is now working with Professor Jayanta Haldar. He will receive this prize later. Thank you very much. And it's my pleasure duty to thank Professor Kulkarni for being with us and giving away the degree award certificates. Please. This concludes the function for award of degree certificates and other medals today. I wish to thank JNC administration, the support staff here, and also my colleagues in the academic office to make this possible and on time. Thank you all for being here with us for this very pleasant function. Good evening.
Good evening, everyone. So now we are going to start the last session of the day. We have three speakers in this session. We'll begin with our first speaker, Akash Singh. Akash is a PhD student in Professor Tapas Kumar Kundu's lab, Molecular Biology and Genetics Unit. And today he is going to talk about an epigenetic modulator as a promising therapeutic option for intellectual disability.
Good evening, everyone. My focus of research is epigenetic modifications during brain development and neurological disorders. So this schematic shows the number of neurons and synapses present at different stages of life, few at birth, maximum between 1 to 15 years, and this is the period at which most of the brain function develops. That is also known as critical period. And at adolescence, most of the unused synapses or weak synapses gets eliminated out, leading to reduced brain plasticity. This schematic shows the different regions of brain at which time they picks up their corresponding functions, and if the brain development is fine, good or normal, the child will be normal, and if there is any deviation in the brain development, that due to genetic changes or epigenetic factors, this results in acceleration or delayed development of brain, and this results in improper processing of information, leading to severe defect in cognitive and behavioral deficits, such as reported in intellectual disability. So SYNGAP1 is a gene that encodes for a neuronal protein and is involved in neuronal plasticity, and mutation of this gene has been observed in patients suffering from intellectual disability, autism and epilepsy. And the mice having only single copy of this gene bears or phenocopy most of the behavioral deficits that has been observed in intellectual disability patients. So we use these mice as a tool to study intellectual disability and therapeutic potential of a small molecule HAT activator CSP-TTK21. So previously we have reported that interperitoneal injection of CSP-TTK21 in normal mice in adulthood promotes adult hippocampal neurogenesis and also extends long-term memory retention. So from this report we hypothesized that increasing the survival and maturation of progenitor cells that are left there may benefit functional recovery in neurological disorders. So keeping in this mind, we asked whether this molecule could improve these synaptic and behavioral deficits seen in SYNGAP heterozygous mice that models intellectual disability. And one major limitation of this ID therapeutics is that the correctness of this synaptic and behavioral deficits during adulthood. So we have done oral ravaging of CSP-TTK21 in SYNGAP heterozygous mice, and we have done behavioral analysis. We have done we have used 3 doses of CSP-TTK21, 1 dose per week for 3 weeks, and then 1 week after the last treatment we have performed different behavioral studies. So to check the memory, first test we did was novel object recognition test, where we exposed these mice to 2 similar objects, and during the testing period we replaced one of the similar object with novel object, and we calculate the discrimination index depending upon the interaction time. So the general tendency of mice and humans are to interact more with novel object or new toys rather than older ones. So if the mice is interacting more with the novel object, the discrimination index will be higher. So we got this result where we found that SYNHET group or SYNHET mice that were treated with saline or the vehicle controlled CSP, we found that there is severe defect in the recognition memory as shown by a less discrimination index, and the group that were treated with CSP-TTK21, we found that this group is behaving similar as wild type mouse, depicting that CSP-TTK21 could improve this recognition memory in SYNGAP heterozygous mice. One major issue with this SYNGAP heterozygous mice or intellectual disability patient is that they display lack of social norms. So for that we use this 3-chamber test, where we habituate after habituating the testing mice in this chamber, we expose this mice first to stranger 1 for some time, followed by stranger 2. So in this case, stranger 2 will be a new relative to stranger 1. So general tendency of wild type mice is to spend more time with the stranger 2 because it is new, and what we got that wild type mice are spending more time with the stranger 2, whereas the 2 group SYNHET treated with saline and CSP, we found that these 2 groups are spending almost equal time with both of the mice, depicting that these 2 mice or these 2 groups are socially inactive. And the group that were treated with CSP-TTK21, we found that the interaction time with the stranger 2 mice has significantly increased. This depicts that this treatment with CSP-TTK21 in adulthood could rescue the social deficits associated with this mice model. To further validate our finding, we also check for working memory and spatial learning through the classical Morris-Otter maze test. So for this we train the mice in this experimental setup, where we train the mice to locate the hidden platform in order to escape swimming. So first the mice will take longer time, and upon subsequent training across days, the timing to find the platform will decrease. So depicting that there is memory formation regarding the location of the platform. So once the memory is formed, we check how long this memory is stayed in this mice. So for that, we track the mice during the testing. So this we have done after 3 days of the last training session, and we found that this SYNHET mice and the mice that were treated with CSP, they did not show any memory because they are moving randomly across the experimental setup. Whereas the mice that were the wild type mice and the mice that were treated with CSP TTK21, this is wild type mice and this is synhet mice. All of them are showing localized movement around the arena where the platform was put initially, depicting that there is memory for this location. We also quantitated this and we found that indeed these two groups are spending less time in the target coordinate, depicting that the memory is not intact, and the mice that were treated with CSP TTK21, they have significant improved memory as depicted by the percentage time they are spending at the target quadrant. So from this experiment we conclude that CSP TTK21 can alleviate the long-term memory deficits associated with this mice model. We also checked for working memory in this mice. So for that we followed this protocol where we continuously change the location of the hidden platform across days, and we give 2 trials, and then the third trial we use as a test. So this will take the working memory of this mice, and we performed the test and we analyzed, and we found that the latency time to find the platform is more in these two groups, that is synhet, saline and CSP, depicting that there is severe defect in the working memory. But the mice that were treated with CSP TTK21, this is synhet group, they are showing similar phenotype as wild type. So we are concluding that this molecule could also improve working memory. To summarize my work, we have found that upon oral delivery of CSP TTK21 in this mice in adulthood, we could restore histone acetylation, also restore synaptic deficit. These two results I have not shown here. And we also found that most of the behavioral abnormalities are getting rescued. So the significance of this study is that we can use this molecule as a potential therapeutic drug for patients suffering from intellectual disability. I would like to acknowledge JNCASR and the 2 labs in which I have performed most of these experiments. Thank you.
Thank you for presenting. We have time for 2 questions. We have one offline.
Akash, you can hear me?
Yes, yes.
First question is, when you inject CSP TTK21, did you analyze expression of SYNGAP?
We have analyzed the expression of SYNGAP and it is not changing.
It is not changing.
No.
And if expression of SYNGAP is not changing, do you think the pathway downstream to it getting
Yes,
affected?
we are working on that field. The downstream pathway, like make-R pathway, that is.
That is
changing. Yes, we have just started that. So we have only like 1 or 2 N number, but from that we cannot conclude anything.
So what is this molecule? What it does?
So this molecule is an activator of P300 and CBP, that histone acetyl transferase.
I get it. So how do you think those changes are getting transmitted through?
Yes,
SYNGAP
so downstream of the SYNGAP gene, this make-up pathway gets activated and they recruit this CBP and P300 as promoters of some of the neuronal genes like BDNF and C-FOS. So we are thinking that in this mice model, this histone acetylation is decreased and might be the level of these 2 important enzymes, CBP and P300, might be also reduced. So by restoring this activity or increasing the activity, we can direct act at the molecular level, at the gene level.
I get it, but you know, SYNGAP pathway works through translational changes rather than transcriptional changes.
No, it has role in transcription also.
Okay, so you think it is working through transcriptional pathway?
Yes, yes.
Thanks.
Professor Kesman.
Yeah.
Hello.
Interesting work, Akash. So, in your behavior experiment,
yes, sir.
You are using an indicator for long-term memory in terms of how many times it goes around and remembers.
Yes, yes.
Right? So, is there any other parameter like the time it takes to complete the journey?
Yes.
Which is also indicative of some other alertness or maybe some the memory aspect may be one of the consequence or a side effect of something else happening. So can you have any other parameters in your experiment?
Yes, we measure different parameters. Like here I have shown the percentage time that they are spending in the target quadrant. But we have also the percentage distance they are traveling in that target, as also the latency time, that what is the lesser time that they are going first in that target quadrant.
Okay.
So that will also
time, maybe the speed. Okay, that is similar.
Yes, that also we can analyze from the same behavior, but we have not.
And what stage this mouse? How old is this?
We have started the treatment from 2 months, and these mice are during the behavioral experiment. These mice are ranging from 3 to 5 months.
And if you do this at a later stage, you will see the effects of your drug to be different.
That is an interesting question, but we are thinking about that, how long this effect is there in the mice. But if you can, if I go to this,
maybe I think it's already late.
Yeah. Yes.
I'll talk to you.
Yeah. We have time. I can ask one interesting question from Dr. Ravi Manjutia. He asked, does the molecule work in absence of its target hat?
We have checked in different mice model that in absence of this P300 and CBP, this molecule does not work. But not in SYNGAP heterozygote. We have not checked the P300 and CBP knockout.
Okay, thank you, Akash.
Yeah, Govindraju here. So in your, the novel object recognition, the data showed the improvement in the memory. How significant it is?
So if I go back,
it looks kind of. I mean, there is some significant, but.
So
it's okay. I can remember. Yeah.
So we are saying that with respect to the wild type level.
Especially, can you go back one slide where you have a bar diagram? Not in this.
Okay. This one.
Yeah, here. Yeah.
Yes. So here we have done the emotional memory test. So we are saying 2 star in this SYNHET CSP TTK21, that there is significant improvement in the interaction time with the stranger too.
Yeah, if you compare the treated group with the one with the controls, I'm not sure how much. Maybe you can.
I would like to clarify one phenotype associated with this SYNGAP mice, that these SYNGAP mice are hyperactive. So they move randomly in the apparatus. So if we see that due to their random movement, the interaction time within these 3 groups, SYNHET, saline treated CSP and TTK21, the interaction time with both of these mice are already decreased. But wild type mice, they are not hyperactive, so they have more interaction time. So this might be due to the hyperactivity of SYNHET mice, that we are not seeing so much significance.
Okay. And how is the treatment here? Is it like a regular? You have to treat the mice, regularly, or?
And one oral delivery for 1 week, and we have carried on for 3 weeks.
Okay.
Yes.
Thank you.
Yeah, thank you, sir.
Thank you so much, Akash, for the talk. Our next speaker is Ganesh from Professor K.S. Narayan's lab, CPMU department. He'll be talking about understanding metal hybrid perovskite interface in lateral device structures for photo detection application.
Good evening, everybody. Today I'll be talking about some of the recent work that we had done towards Today I'll be speaking about some of the recent work that we had done towards understanding the metal hybrid perovskite interface in lateral device structures and how it can be used as a photo detector. Okay. So to begin with the introduction to perovskite, I think most of you are familiar with it. I mean, most of the the materials community is familiar with it. So basically it consists of a chemical structure ABX3, where A is an organic cation, B is the lead in this case, and X is a halide. And so if you were to look at the crystal structure of MEPBI3 over here, you see that there is a Ma cation which is surrounded by the PPI6 octahedra. Now this kind of materials have are semiconducting in nature and have a characteristic band gap, also a PL emission associated with it. The advantage of this perovskite is that they are easily solution processable and single junction efficiencies up till 25% have been achieved in the solar cell. Now, depending on the application of these devices, there can be different device structures. So mainly it can either be a sandwich device or a lateral device. Sandwich device basically consists of these different stacked structures for hole and electron transport. Whereas if you look at the lateral device, it has got electrodes which are placed laterally and perovskite ink deposited subsequently. So what is the advantage of these kind of lateral devices? So some of the advantages are that it reduces optical absorption losses because of the absence of stacked layers. Secondly, it has got low dark current, which increases which reduces the noise in these devices, allowing for small signal detection. Thirdly, it has got very low device capacitance. So basically this helps in faster RC lifetime of the devices, which are useful for high speed operation. And now these kind of metal semiconductor, these kind of MSM devices that we are studying basically can be classified into either symmetric electrode or asymmetric electrode. In the case of asymmetric electrode, we have got two different metals, M1 and M2, of dissimilar work function. Now, so this is a small preview of the fabrication of these devices. That is, basically we employ the two photon the polymerase photoresist onto which we coat either of the metals. So one is first we coat the gold, then we deposit another photoresist of a smaller channel length, followed by aluminum coating. So what we see over here is the effective device area for forming back contact devices of a channel length that can be varied. In our case, we are able to vary it from 3 micron up to 150 micron. And so this is the optical image. Which shows an asymmetric device of a channel length of about 5 micron. So, what is the necessity of having an asymmetric electrode lateral device? So the first thing is that the first thing is to look at the interface of the metal hybrid perovskite junction. So So this interface is not clearly understood, and the potential mapping as well as the photocurrent contribution from these interfaces is not clearly understood, and it helps to study this interface in order to make high performing devices. Secondly, having an asymmetric electrode allows for either electron injection extraction or hole extraction injection using the different work function of these materials. Now we are able to make these devices of different channel length. So I would like to show you a long channel length device. So basically what you see here is a long channel length device. So the channel length is about 55 micron in this case, with gold and aluminum on either sides of the perovskite. And what you see is that the IV behavior is not very different when you compare a symmetric device versus an asymmetric device. But if I were to make a short channel device, that is, if I have a device of about 12 micron, 10 to 12 micron, what you see is that the reverse bias current reduces a great deal, about 3 to 4 times it reduces. So what does this indicate? So this shows that there is a depletion layer which is formed in the device upon having a reverse bias, which is resulting in reduced current. So further we did the CV measurement also to determine what is the approximate barrier height, and we see and what we say is that the Schottky barrier height is close to half electron volt. Yeah. So in continuation, these are the dark rectification characteristics, where we see that the current that the dark current increases in the case of a short channel device. But what is more important is that we see a rectification kind of behavior in the case of a channel length of 4 micron. So this is so as you can see, this rectification ratio increases. Increases drastically high with where we see that the rectification ratio is about 17 for the case of 4 micron channel length. Yeah. So this is the light IV, and what is important is that even at zero bias we see a short circuit current. So to find out how does the interface looks like, we did the Kelvin probe microscopy on these devices. Kelvin probe microscopy basically consists of an AFM tip, which is in intermittent contact with the sample. A current flows through it, and then a contact potential difference is measured when the Fermi level equilibrates. So this is a symmetric electrode device with gold on either side, and what we see is that the work function difference is not drastically high. It's about 20 to 30 milli electron volts. Which basically indicates that the perovskite that we are dealing with has a p-type character, and this is also inconsistent with the previous reports on these kind of perovskite. Now the device of interest, which is the asymmetric electrode device, shows that. So if you look at the KPFM of the asymmetric electrode device, what you see is that there is a drastic reduction of the. There is a drastic potential drop across the aluminum perovskite interface, and similarly the electric field, which is the differential of potential, also is very high at the aluminum interface, but this is not true in the case of the gold, which has an ohmic contact. So essentially what we have is that about 5 to 10 micron from the aluminum interface, we have a depletion layer, which is because of which is attributed to a Schottky barrier. And then, so this is the potential distribution upon having an applied bias. So this is the potential positive bias and negative bias. What you see is that in the case of a negative bias, there is a very high potential drop. So the red is the potential and the black is the electric field. There is a very high potential drop at the aluminum interface, which indicates that there is an accumulation of carriers due to the extraction barrier of electrons in this case. So similarly, so this is also data for a 10 volts applied at the gold and aluminum. A similar observation is made, and what this kind of an observation allows us is to get an equivalent circuit of the device, which has got both the interfacial as well as the bulk contribution to study the IV behavior. In the case of the long channel device, what happens is, in the case of the long channel device, what happens is the bulk resistance is significantly higher. Hence we get a linear kind of behavior, whereas in the case of a short channel device, the interfacial resistance as well as the capacitance influences the net IV behavior, because of which we see a rectification kind of a behavior. So lastly, so these are the device the detector characteristics of these devices, where we see a decent responsivity of about 1 ampere per watt, and also the detectivity increases. So this detectivity takes into account the dark current, and so this increases in the case of reverse bias condition also. So finally, to conclude, what we see is that we see a rectification behavior, following which we have done the local potential mapping, which shows a barrier at the aluminum interface, and this kind of a device structure allows for photocurrent mapping, either the drift dominated or the diffusion dominated photocurrent. Lastly, this kind of the low capacitance of these devices are a suitable candidate for high speed detectors. Yeah. So thank you.
Device, right?
Yes, sir.
And you always have Schottky barrier.
Correct.
And you're dealing with long and short channel configuration.
True.
I don't understand why you should have different behavior. I mean, the acquisition ratio is hugely varying. What is the basic reason?
Yeah, so the basic reason is, the basic reason is, yeah, so this is the reason, that is, so here we have done the potential mapping of a 60 micron device, and what we see is that the barrier extends to about 7 to 10 micron into the device from the aluminum barrier. So if we were to reduce this channel width and up till here, then most of the devices is under the influence of the Schottky barrier, and the built-in potential is throughout the device. So that is the
question is, if you walk into the barrier, then you'll see it.
Yeah, exactly. So the barrier is assisting in photo detection.
Oh.
Okay, there are no more questions. Thank you, Ganesh, for giving such a nice talk. We'll move to the next speaker now, Dr. Ranjan Datta. Dr. Ranjan Datta is Associate Professor at ICMS JNCASR. His research interests include understanding the concepts associated with solid-state physics through structure and property correlation. Today he'll be talking about atom counting in zinc oxide by atomic resolution inline and off-axis electron holography.
Okay, so the good evening everyone, to Professor Kulkarni and also to the organizers, Professor Anand, Shiva and James, for your kind invitation and also to arrange the meeting in such a difficult time. So the title of my talk, as you can see, atom counting in zinc oxide by atomic resolution off-axis and inline electron holography. So this is a work we published in Journal of Applied Physics last year. So these are actually two advanced microscopy techniques which we use generally to answer very specific materials questions. So I prepared kind of broad general overview on the two techniques. So I'll start with the HRTM or phase contrast microscopy, and then introduction of the off-axis electron holography. Then I'll go through concept of resolution HRTM. Then what does it mean by quantitative imaging, different approaches and the results published by different groups. Then our small contribution in the area in terms of your atom counting in zinc oxide by two different your aberration pattern microscopy techniques, and lastly conclusion. So phase contrast microscopy, you all I'm sure aware, was discovered by Janicke in optical microscopy and also awarded Nobel Prize in Physics in 1953. So to understand phase contrast microscopy, you see there's a comparison of the tissue sample without any chemicals staining, right field and the phase contrast image. Here, if you can see the cursor, so you can see if you use a phase plate to do the phase contrast imaging of a weakly scattering tissue sample, you can see lots more details which are not available in the bright field image. So you can understand how phase contrast works with the help of this of the phasor diagram. So you know the wave or the vibration MV and MV prime are represented by using the complex diagram, and the horizontal component MP, MP prime are the amplitude, and the angle from the horizontal component is the phase. So if you have a strongly scattering sample, then illumination MA changes from MA to MD prime, and the compounding MP is MD. So the feature appear dark in a white background. But if you have a weakly scattering sample, so if you don't have any chemical staining, then you don't change the amplitude, you only change the phase. So amplitude changes from MA to MD. So the compounding image is MD prime. So to be able to see this effect, you need to rotate the phase of either MA or MD to MPH to be able to see the contrast, and that is performed actually by using a phase plate. The phase contrast microscopy, can you hear me? Hello, can you hear me?
Yes, sir. Please go on.
Okay, thank you. So phase contrast microscopy in HRTM means the periodic dots, and these periodic dots actually represent the lattice structures of the crystals along high symmetry orientation. And here are some examples from our own work: nickel ferrite along 1GG orientation showing the spinel structures, and A-side cation defects. 2D material MOS2 grown on C-plane sapphire cross-sectional image showing the stacking and the interfacial binding. MOS2 RES2 alloy showing the phase transition between 2H and 1T. So this is also another technique called atomic resolution jet contrast technique, which also can give you the similar kind of dots, like HRTM, but with added information, but you also get the chemical contrast. For example, silicon and nitrogen to graphene, you can see the brighter dot has silicon and the nitrogen, so you have chemical contrast. So just why I'm showing this image actually is to mention that your HR team is also able to give you this kind of information, but not widely used. Slide on inline and off-axis holography introduction. Holography was proposed by Denis Gabor in 1948 and also awarded Nobel Prize in Physics in 1971. So holography means the complete information recording of the wave field. So the purpose of Gabor was basically to get rid of the aberration from the electron micrograph, because at that time the quality of the instrument was very poor. So it's a two-step process, writing and reading. So Gabor's proposal was inline holography, and he had to abandon his method because he could not get rid of the twin image issue. Until Leith and Upatnaik used a tilted beam illumination, which separated the DC component and also the twin image components. And holography is a very well-established and a widely used technique in many branches of science and technology. But to do the holography with the electron, you need electron biprism, and the electron biprism was discovered by Gottfried Mollenstedt, and this is one of the first electron interference fringes. And here is the schematic geometry of the electron interference fringe under off-axis geometry. So basically, in the off-axis geometry, you add a carrier frequency, and the intensity pattern is given by this expression, and Q is a carrier frequency of the hologram. And here is the basic schematic of the light optical analog of the electron biprism, which is known as the Fresnel biprism. This slide is showing the schematic principle behind HRTM and the off-axis electron holography. So for the HRTM or the inline holography, the defocused HRTM actually is equivalent to inline hologram. So you basically have to collect lots of images, at different focus. And for holography, you have a biprism. But to work at atomic resolution, you need double biprism, because the field of width is very small at atomic resolution, and the microgravs suffer from the Fresnel fringes and also vigneting effect. And the double biprism setup actually to help to get rid of these effects, to give you better micrograph and to extract better numbers. So at the end, what you are interested actually to recover the object exit wave function of the form psi equal to a to the power I pi. So the holography at atomic resolution was performed in the tube Berlin microscope. This is a special microscope, aberration corrected, and also equipped with the double biprism. And the HRTM we have recorded in our own microscope in JNCASR. Both are aberration corrected, both are spatial resolution better than 0.1 angstrom, 8 angstrom, and then we have variable CS. Holography at medium resolution is a well-established technique to image electromagnetic fields in materials. And here are some examples from literature. For example, doping profile in the NMOS transistor, then vortex lattice in niobium superconducting film, also ferrotic polarization boundaries and domain in the barium titanate. And also holography has been used to image the flux exposure and also remnant field in the cobalt nanoparticle, and also to image the Skyrmions lattices. At atomic resolution, you have to record hologram at the sub-angstrom length scale. There is an example of silicon along 110 orientation showing the lattice of silicon, and in that you can see the fringe is at the sub-angstrom length scale. And here on the right hand side is the amplitude and the phase extracted from such atomic resolution hologram with a gallium arsenide sample along 110 orientation. So what does it mean actually? You have amplitude and phase information from the atomic and the subatomic length scale. So that not only helps to identify and count the atoms from the individual dots, but also you have information from in between the columns. And in between the column information is very, very important, because you have electrons residing there and you have a lot of chemistry going on there. So now coming to the microscopy and the concept of resolution. You all know that to be able to distinguish, we define resolution by to be able to distinguish or discern between 2 points. And you all know the human eye can resolve max 100 to 200 micrometer, and optical microscope is used to be able to see your lens color feature below 100 to 200 micrometer. And if you have ideal lens, then you you image point, you image the point as a disk because your diffraction limited, and this disk is known as AD pattern, and the expression for the AD pattern is gained by 0.61 lambda over mu sin beta, where lambda is the wavelength of the illumination and mu sin beta is the numerical aperture. And the radius criteria of resolution is defined by a distance d naught. So it's not a very strict criteria. So it's typically defined by the distance between two such AD pattern, where the minimum of the first pattern falls right below the maximum of the second pattern. And the d naught for optical microscope is gained by this particular equation. So aberration. So in the electron microscope we have aberration. So your we have severe blurring from the aberration. Here are the two examples of the spherical aberration and the chromatic aberration. So you can see the point object is blurred in the Gaussian image plane significantly, and the spherical aberration is because of the inhomogeneity of the lens, and the chromatic aberration is because of the spread of the lambda in the illumination. But there is a plane called Sarger plane, which can be accessed by applying a little bit of focus. And this plane is known, or the image is known as disk of least confusion. So in the presence of the aberration, but mentioned that we don't have Jani-like phase plate in the electron microscope. So we make use of this combination of the CS and T focus to basically apply phase contrast. And in the presence of aberration, we define resolution by using the PCTF function. It's known as phase contrast transfer function. So the first zero crossing of the PCTF will give the point resolution GS, and GI is the information limit. So the information between GS and GI is not straight. It cannot be accessed directly. And the ideal shape of the PCTF should be like this to minimize the gradient of the PCTF function, to minimize the localization in the image. If the environment is not very stable, if the noises coming from the environment, for example, stray electromagnetic field, vibration and all, they appear as incoherent aberration, and they basically lower the point resolution of the system. So in the aberration corrector microscope, we have Rose corrector. And this was developed by these three professors, Harold Rose, and the Hyder, and then Urban, and also awarded Wolf Prize in physics in the year 2011. And so the principle behind of aberration corrector is that you don't make lenses aberration free, so the principle is that geometrical aberration adds up. So you have to nullify the effect of one lens by another set of lens. So we have double hexapole and the two transfer doublet. This is for the imaging system, for the broad beam illumination, and the bottom one for the probe corrector system. So same mode. So I'll not go through the details of that because there is a long history and struggle in this field. So here's a brief comparison between the off-axis and the inline holography of the HRTM. So your HRTM basically acts as a band pass filter. So it only transfers information with the high contrast only for specific frequency range, and that you basically align it to the interatomic spacings. And for holography, actually can transfer all frequency range information. To understand this, you can take this example. Is a photograph of the gold-thread Molenstret. You can see that he's doing something, and if you do the Fourier transform of the image and then filter out some of the frequencies and then back Fourier transform to form the image back again, you can see that you can still make out person is there, he's doing something, but you lose a lot of information. For example, the contrast, so the contrast difference, so the shade difference between the hair, your hair and the wall shot and the coat. So your HRTM actually is something like this, but it's like this actually it's likely based on the present methodologies. So now there are examples in the literatures. So you can do the quantitative imaging following different route. You can follow holographic approach. You can follow HRTM approach, and also there are other methods like electron probability current. Some examples from literature. Here is an example of nitrogen doped graphene. So it is not only the imaging of the atomic dot, but it's showing actually how one electron of nitrogen is shared by surrounding carbon atom. So one electron wave function actually is imaged by this technique. And from one micrograph, the complete reconstruction of all the atoms in the MgO crystal has been shown, and also for the bilayer graphing by another theoretical method called big bang tomography. So, what is the eventual goal of the quantitative imaging? Like, can we determine materials properties through imaging? And if you want to do that, then what does it take? Because materials as atoms, they have particular arrangements, and the materials can have defects, dopants, etc. And if you have atoms, then you have electrons around it, and you have electrons, you have field around it, potential around it, and if you can determine the potential, and once you can fit the orbital, you should be able to basically tell the properties of the material in terms of magnetic moments and other things that you're interested. So there is no restriction or limit posed on the theory. And it's quite possible because nowadays tremendous advancement has been made, both in the field of microscopy and also in the field of detectors. So I'm sure that people can take up this kind of difficult challenges. Now coming to the result part, so we have studied zinc oxide thin film, epitaxially grown on zinc oxide substrate, on the C plane of the substrate, and our initial goal actually was to understand the native defects by imaging in the between the N-type and the R-type sample, where we have carrier difference 10 to the power 19 in one case and 10 to the 16 in another case. But due to some limitation at that point of time, we restricted ourselves only for the atom counting. So experimentally for HRTM, you have to collect your series of images at different defocus. And if the sample is thin, then you are within the linear imaging condition, and there exists the analytical solution within the weak phase object approximation. But if the sample is thick, then your dynamical scattering, then you're within the non-linear imaging condition, and you have to follow some iterative approaches. For example, PAM, MAL, to retrieve the amplitude and the phase of the object exit wave function. In case of holography, it's quite straightforward. Once you do the Fourier transform of the hologram, you have three bands. You have central band and the two side band, and two side band are the two in image to each other. So you can see that you can separate them out in the frequency space. Now you take one of the side band out and do inverse Fourier transform, and you have the complete wave function information. It's not straightforward, will come, but you have to feed to the model calculation. Here is a schematic flow of the data analysis. I already said. So for the off-axis, you do the FFT, take on the sideband, do inverse FFT, get the complex image, and get the phase and amplitude out. And for HRTM, you collect through focal series, and you follow certain iterative. If the sample is thick, algorithm, then you get object exit wave and get the phase and amplitude. So there is one important parameter called phase detection limit. So it's like resolution. Phase detection limit also is very, very important because it will tell you what is the smallest gradient of the electromagnetic field you can determine. So I'll not go through the details of it, but from our experiment, we have phase detection limit about 0.007 rad, which is actually good, much better than the requirement, because to count incremental oxygen and the zinc on the column, you need 0.1 and 0.2 rad. So the numbers we have actually will allow you to count the oxygen and zinc atoms. So in this context, the other report reported 2 pi. So Cooper et al. They reported 2 pi by 1000. So, but none of them actually have used the double bar prism and the aberration vector microscope, and the numbers also not better than us. So, and the phase detection limit in case of HRTM not discussed, except the EZMAS paper, the peak phase value of nitrogen boron 0.0 to 0.022 dimension, and the difference of 0.004. Anyway, I'll not go through much on that. And you also need to model the system, how electron and the wave and the matter interact, and how it get basically further change due to the lens parameter or the lens aberration, to calculate the intensity, the phase and amplitude eventually. So I'll not go through the details, but we have followed the Hartree-Fock potential, and we calculated intensity by using this particular equation from certain source, and we calculate the projected potential using the Hartree-Fock, as we mentioned already, and then calculated phase by this equation. And also we took care of the inner bound and the outer bound of potential, because potential is asymptotic function. We found that beyond certain inner bound and beyond certain outer bound, the atomic scattering factor and the intensity and phase do not change significantly. But experimentally, you are restricted on the inner bond and the outer bond because of the limitation on the interatomic spacing. So for zinc and oxygen, they are closely situated to each other. So we have selected 1 to 50 and 1 to 25 for zinc and oxygen for the mean phase. So you can basically consider two different phase value, peak phase and mean phase. Anyway, so now, so this is the result. You can see the reconstructed wave function both from the central band and side band. So central band, again, I forgot to mention, is equivalent to the HRTM or the Indian holography for the off-axis holographic data. And side band actually is the off-axis hologram. So we have the amplitude and phase, and the arrows are showing along which we have counted. We have evaluated the phase and the corresponding atom number. And zoomed in image showing the red one is the zinc atom and the yellow one is the oxygen atom. So is a summary plot showing central band, side band, your comparison. For very thin area of the sample, you see the systematic increase both in the phase value and the atom number with the sample thickness. And the nice thing is that zinc and oxygen, though the contrast is different and the atomic number difference is very high, but in the neighboring column, we have obtained the same number. This is a very nice result, and the methods that people have used. But for thicker area, the trend is not very good with the sample thickness. That may be because of dynamical effect and also how we basically handle the data. But we don't have very good result actually from the HRTM image series and our and the commercial MacCampus code that employs the Gauss-Saxon algorithm, particular algorithm. It doesn't give any systematic trend. So thin and thick, respective thin and thick area, we obtain almost the same number atom. Anyway, so now coming to conclusion, because I just try to make it simple and then and briefly. So, but the major conclusions were for thin sample area and the central band side band reconstruction yield good agreement. However, for thick sample area, agreement no longer holds. And 3 to 4 times more atom numbers is obtained considering mean phase value compared to the peak phase value. HRTM reconstruction gave almost constant atom number, one irrespective of sample thickness, and both HRTM and the off-axis holography at atomic resolution offer opportunity both in material study, method development, and also fundamental science from subatomic length scale. Acknowledgement, a special thank to Professor Sienna Rao, founder president, for the advanced electron microscopy facility and also giving me the opportunity to work in such a microscope. And sincerely thank ICMA CPMO for research funding. A special thank to DFG for the work in Berlin. And lastly to all of my students for all the work. And then last to all of you for your kind attention. Thank you.
I would now like to end this session. I would like to thank all the speakers for giving such a nice talk. That is it. Thank you everybody for attending today's talk and all the attendees and the participants and the organizers. Thank you so much.